All right, everyone. Welcome to MEVconomics. We've got a ton of great research topics set up here at the intersection of MEV, Ethereum, all things economics. First, shout out to ETH Global and Flashbots for putting all this together, especially Tina and Sarah. And thank you again, Tina, for informing me that I volunteered to be Roastmaster for this. We've got a, sorry. So just a quick scheduling note, all the presentations here will have some Q&A at the end, so please submit any questions you've got. If you're on the live stream, we will be checking them. I'll prioritize the spicy ones, so please no softball questions. With that, I will get into the first presentation. There we go. So this will just be a very broad overview to kind of set the stage for all of the other talks today. This is basically the state of affairs for everything MEV right now. So basically, as everyone kind of knows, merge happened at the end of last year, completely changed the block production supply chain. This is broadly what it looks like right now. This picture comes from Barnaby, who's obviously working on a lot of the stuff over at the Ethereum Foundation. So broad transaction supply chain, users submit transactions, searchers will take a lot of those transactions, make specific bundles, they send them to builders, those go through relays, and eventually validators will take those blocks that builders make for them and propose those to the network. This kind of separates that specialized task of actually building blocks so that validators can have permissionless access to MEV and not have the centralizing pressures of needing to be sophisticated actors who need to do that more complicated task. So this is what the builder market has looked like since the merge. As you can see, it has diversified a lot since the start of it, or right around the time of the merge. It was rather centralized in the beginning where there just weren't a whole lot of parties there yet. Since then, it has broken up very, very nicely, such that you have a lot of different participants who are all taking, 10 to 15, 20% market share, and then a long tail of much smaller ones as well. So as you can see kind of in this graph below at the bottom, or the table below at the bottom here, some of these builders are able to take a nice margin on that for some of the bigger ones. These are the profits that some of them have picked up over the last week for some of the big builders. Some of them do run at a profit, like as you can see with some of the bigger ones like Beaver here, rsync, Builder 0x69, and others just run at flat where they pass everything through. Which is the illuminate, democratize, distribute. That one's Flashbots. That's what they do. One of the other exciting things with builders as well is we'll start to see going forward, hopefully, is their ability in their kind of role here to add a lot of additional features going forward, which I would recommend you to see Alex Stokes' talks on those topics, because that is a very long topic in and of itself. So the big question here is that everything looks pretty good from like the start of the merge. I think most people would agree that we're pretty happy with the way that the builder market is shaped out, that there's a good amount of decentralization now in that. There's a lot of different participants in there who are acting pretty competitively. So I would say it's a good start, but there's obviously concern that there are very natural, very strong centralizing tendencies in this over time. So that's where it comes in, trying to build an actually fully decentralized block building network that kind of plugs in here and is able to have many, many participants who actually contribute to even building a single block. And that is exactly what Suave is, as I'm sure everyone here has heard of by now. Here's just a very quick overview of it. So moving on down to the next step of the supply chain. Relays is basically kind of just the pipes in the middle between the builders and the validators who are sending those blocks along. Again, you see the very similar trend where at the beginning it was very centralized. It was basically everyone was using Flashbots for the most part. And since those first couple of months, we have seen a lot of diversification in there, which has been really nice. And the biggest one now is actually not Flashbots. And it is, I believe, last I checked, it is the ultrasound relay, especially after they launched very recently, I believe a week ago. They're optimistic relays. So that is kind of a new concept where you start to realize that there's a meaningful latency advantage if you cut out that kind of step of not requiring the relays to actually validate the blocks that they are sending along to the proposers. That cuts off, 100, 200 milliseconds of latency, and that does add a meaningful benefit So it does come along with some risks because now they are no longer checking the blocks that builders are sending them to the full extent. But they're also collateralized by these builders. So builders who want to be able to get that extra latency edge and give their blocks a little higher chance of getting accepted, what they'll effectively do is they will just put up some form of collateral. And, hey, if my payment that I said that I was going to give the proposer doesn't go through for some reason, if something was screwed up, then you could take my collateral, basically give it to them, and I get kicked off of that relay. So there's some element of trust in there, but there is also this fallback option to make sure that proposers don't just completely get rugged on it. And recommend checking out the MEVboost community calls. There's been a couple of them now where a lot of this stuff gets discussed. So the general trend on this, I'm sure everyone has seen this chart by now. And this goes kind of hand in hand with a lot of that diversification that we saw throughout the relay and builder market. Is early on, the large majority of relay and builder adoption that we saw was primarily coming from ones who filter out OFAC transactions, which obviously got a lot of people worried in the earlier parts of the year, particularly if that started to continue to trend up. You'd potentially have to wait a rather long time if you were one of those sanctioned listed addresses. Thankfully, a lot of the relay diversification and builder diversification has come from parties who are not engaging in that, ones like Ultrasound Relay, who are not filtering those types of transactions out. So the big question kind of here becomes, is the Ethereum protocol is very kind of simple today, and most of these types of actors are sitting outside of the purview of the core protocol itself. So the perfect example of that is something like in protocol proposer builder separation. So as of right now, we need those relays because there isn't this notion of that market structure and allocation mechanism for PBS actually built into the protocol itself. So we do rely on those other actors. And similarly with concepts like restaking, is it possible to bring those kind of commitments into the protocol such that the protocol is actually aware of those things? And that becomes a very big question of what is it actually the Ethereum protocol's job to guarantee? Should it be bringing all of these things in if we see this as a really important and potentially dangerous role that is sitting outside the protocol that has a lot of power, something like builders, should we bring that into the protocol itself? Something like in protocol PBS, the nice thing about that is it removes the need for relays. So you get rid of one of these vectors for censorship in the middle, you remove another party, you make that kind of engagement between the proposer and the builder more trustless, that you know that they will get paid. But it does also mean that you are now enshrining additional complexity into the protocol, and there's a possibility that you find out a year or two later, oh, maybe there's this thing that we haven't thought of on the incentive compatibility, on the economics of this structure. So there has to be a pretty high bar to actually enshrine something, and it probably looks like something like enshrining PBS will take some time if it is going to happen. So this is kind of the core idea behind a lot of what Barnabé has spoken about in the past year, this concept of Pepsi, which he has mentioned before, which is effectively making the protocol aware. It's an idea, it's not a specific proposal or anything that's like an EIP or anything, but it's an exploratory idea, at least, of what if we just make the protocol more flexible in understanding these kind of external commitments, as opposed to trying to enshrine everything into the protocol itself, like a very specific proposer-builder separation model. And this kind of relates to restaking a lot, because we're starting to have this idea where proposers can potentially opt into external commitments outside of the protocol that, hey, I'm saying I'm going to secure this other application, but the protocol is not aware of that at its core. So there are obviously a lot of risks that come along with restaking that people are concerned about. But the reality is it's here, and we just need to understand how to build with it responsibly. And one potential kind of answer to that is potentially just making the protocol more aware of it and being maximally flexible, as opposed to enshrining very, very specific and complicated mechanisms into the Ethereum protocol. So looking at the validator market here, I'm sure a lot of people have seen this before, but you see the similar trend of, we kind of realize that a handful of large operators do control a very, very large amount of the stake. And while we have high economic security, we also would like to much more decentralize the actual stake behind that, such that there are many operators behind it. And one of the things there is obviously liquid staking providers. They have a number of operators who are underneath the hood of something like Lido, something like Rocket Pool. And they obviously offer a lot of nice benefits to users. They're effectively a backdoor way of smoothing rewards for users. It gives them a liquid token. So there's going to be a lot of development here on things like, as Lido talked about with their staking router, being able to bring in things like distributed validator technology to hopefully decentralize kind of the operators under the hood there even more than they are today. So one of the big trends that we will definitely hear about later today, and probably a lot for the next year, is that users have mostly been not acknowledged a whole lot in a lot of the stuff that has been built in regards to MEV over the past year or two. There aren't a lot of options to really give users back a ton of value today. For the most part, you're going to send something to the mempool. Hopefully you set your slippage right such that you don't get sandwiched. But there's not generally this kind of competitive process where people are bidding you back the actual value of what your order is creating. And that's kind of the core concept behind order flow auctions, such as what Flashbots has proposed with MEVshare early on. There's a number of others who are building very similar solutions, whether that be block native and others. And this is basically that competitive process where searchers can say, hey, I realize that I can capture $100 if I have the right to back run this trade. So I should be able to bid in this auction. I'll bid $99 for the right to do that. And that kickback can then go to the user, returning them some of that value. It becomes difficult to do this in a trustless manner. And that's where a lot of the kind of programmable privacy tech that you hear about, that is going to need to be layered on over time, such that you're removing trusted components like something like the person who's running the auction effectively in MEVshare early on, or not technically running the auction, but the matchmaker who's kind of doing this, you are trusting them. And so removing those trusted parties is going to be a big part of fleshing out these kind of systems. Another trend is going to be wallets. They've been a bit of the sleeping giant for a while here, where they're in a very powerful position of aggregating user order flow and sending that through the supply chain. Like, that is effectively where everything comes from. So the simplest thing for them to do is you strike private deals, you do payment for order flow. Hey, I'll only send it to this builder. You execute these for me, you kick me back some money. The threat of that, obviously, is it becomes very centralizing. That gets back to the centralizing forces that we talked before with builders. So you would ideally like to see a much more permissionless and open system where they're not doing that. Otherwise, we've effectively just created a worse version of TradFi if you kind of play that out. At the application layer, this will be another trend that you start to see over the year, is most of these general purpose environments, like let's say a Uniswap or some DEX or whatever on a general purpose environment, most of the value from that is generally going to go to the Ethereum validators, some searchers, some builders, et cetera. But realistically, applications want to be able to capture that value for themselves, because that's one of the core values that they do create. So you see very custom ideas around this, stuff like Osmosis is implementing a module where their validators will just automatically do these arbitrages and capture that revenue for themselves to be distributed as they want. It's much easier to do in an app chain, something like that, where you can just actually customize the consensus. Becomes more difficult in a general purpose environment. And then lastly here, we have L2s. So you'll hear a lot of this for Hasus and Turinstock later on. But MEV is obviously going to be a big problem on layer 2s. The problem doesn't just go away once we kick it up there. And it already even is a problem today, even with the centralized sequencer. So even without decentralizing at all, there are meaningful problems that do need to be addressed significantly better, because the naive implementations of this, something like a first come, first serve, you just end up with these latency games. And as Tarun will explain later, the idea of fair ordering is a bit questionable. So decentralizing it will make it even harder. And you introduce a lot of new complexities. And hey, how do we try to maintain a private mempool anymore now that we have more participants in here, stuff like that. And the reality is, I think it's more important to deal with the MEV effects of something like first come, first serve than it is probably to decentralize the sequencers, particularly in the short term, because the whole point of rollups is, if they're implemented correctly, where you remove the upgrade keys, you have permissionless proving, et cetera, they're safe anyway, and users should be able to exit from them. And now you have this whole new idea also popping up of shared sequencers. There's a number of variations there, which we'll talk about later today. One of them is what Justin has proposed, called based rollups, which is kind of an idea based on what Vitalik described a couple of years ago as total anarchy, which is basically letting the layer one itself sequence for all of the rollups that are on top of it. Comes with a number of trade-offs kind of on UX and a lot of very different economics, which are very interesting. And then there are also other chains which are looking to provide similar services, ones like Espresso and Metro, who will be offering this kind of shared sequencing layer that many rollups on top of them can plug into. And they will be providing that sequencing service for all of them. And that gives you a lot of exciting benefits. It also, again, raises a lot of very complex questions around the economics and the trust in these systems, et cetera. And those ones also do give you a bit of an easier route to one of the nicest things that people like about rollups as a user is you want those really fast pre-confirmations. That's really difficult to do, possibly not practical at all to do with something like a base rollup where you probably are going to fall back to the L1 block times. So these are all very interesting ideas, which we're going to hear a lot more about later on today. And that is all from me. Were there any questions? No, it does not look like there are any questions. All right, so I'll transition it over a couple minutes early here then. We are going to have Elaine speaking next on MEV activity since the merge, strategies, searchers, and builders during market panics.
Hello. Can you all hear me?
Yep, we can hear you. You can go ahead.
Okay, cool. Just checking if the audio is working. Right, so in the next 15 to 20 minutes, I'm going to go through some of the MEV activities since the merge. I'll touch a bit on everything, including the strategy, the searcher strategy, the proposers, the builder competition market, and specifically touching to recent stress or market crisis events. Yeah, so let's get started. So before I go into the data, I'd like to highlight the concept of MEV because it's a theoretical value that sometimes it's difficult to assess and obtain all the data on chain to do this. So therefore, we introduced a concept of realized extractable value. So REV is the actual value that we can observe on chain that's from the MEV opportunities. So before the merge, we've done something similar by collecting the REV from the proposer balance change or the minor balance change. And after the merge, we are collecting the same data. So here we're using the ETH sent to the proposer as an approximation for the total REV. But bear in mind, the REV pie, which is only a portion of the MEV theoretical pie, also contains different parts. For example, we only look at the atomic arbitrages, the MEV opportunities. We don't look at any kind of arbitrages outside one block. There are also REVs on other domains, on cross domains, and also on centralized exchange, which currently we don't have too much data on these. So the numbers that we see currently in the ecosystem is mostly focused on atomic arbitrage or MEV opportunities on chain. And some of you might be aware of one of the products that we have from Flashbots, which is called the MEVexplore. And there have been many quotation of the numbers from MEVexplore. But just to highlight that MEVexplore only represents a small portion of the pie. So when you look at the data from MEVexplore, just bear in mind that doesn't tell you the whole picture. Okay. So let's have a look at the MEV activities since the merge on layer 1. Back in 2021, we have produced similar numbers using MEVexplore. Here we're showing on the right-hand side a 12-month coverage of MEV activities from liquidations and arbitrages, and that's in total 475 million. And bear in mind that the dollar value is based on the ETH price at the time, at the end of 2021, which is probably much higher than where we are now. On the left-hand side is what I'm going to show you in the following slides. This is the 6 months since the merge. And in total, we've seen the total ETH sent to the validators around 146,000 ETH. That's equivalent to around 260 million in dollar value today. Just looking at this number again, just to highlight that we are using the ETH paid to proposers as an approximation for the total MEV. And we've seen this number have been accumulating since the merge, but you can see two distinct bar charts on the right-hand side here, where the weekly numbers are actually much higher than the other weeks. So these are the two events that I will talk about later on in my slides. So these are the two market crisis events happened recently. One in November, the FTX collapse. One in March, not too long ago, the bank run on SVB, and also the shortly depegging of the stablecoins. Just to show you all the parties involved in the supply chain, we're talking about only the ETH paid to proposers, which is only one component or one party involved in the supply chain. And if we make a simple assumption to say the other parties, other than the proposer and the searcher, receives no MEV, which is not exactly accurate at the moment. For example, the builders, some builders do take a profit from building the block, but let's just assume the breakdown is only between searchers and proposers. We see a 48% MEV going to the searcher and 52% going to the proposer. So the numbers I showed in the previous slides only represent that 52%, roughly on average. Okay, so since the merge, what's happening with the relay? So we see the relay competition has been increasing. There are more relays in the ecosystem now than since the merge. At the beginning, we have just flashbots and no other relays in the ecosystem. Now we have multiple relays, and you see flashbots. Slot shares has been decreasing since the beginning of this year. At the bottom here, you can also see the ETH paid from Flashbot's relay versus the others. You also see there used to be a gap where Flashbot's relay pays more than the others, but now this gap is closing rapidly. Looking at the builder space, also at the beginning, we have since the merge, we have Flashbots and also builder 0x69 dominating the market, but then the share from Flashbots builder also started to decrease since the beginning of this year. And now we have shown just the top 10 builders in the space that we can identify. But at the same time, there are many other smaller builders I haven't included, which I will touch base on the later slides. So latency. So what do we mean by latency? Usually, among all the parties involved in the supply chain, we look at when the block submission happens. So this slide shows the time the validator asks for the get header from the builder. So this is around 400 milliseconds after the slot starts. So after this 400 milliseconds, the validator starts to ask for the bid from the block builder. And when was the block ready? On average here, we see that the average winning blocks means the blocks that actually landed on chain, on average, they arrive 149 milliseconds before the slot starts. Just going to show you the winning blocks, also the proposed, the landed blocks versus all the blocks submitted to a slot. So this chart shows you actually a very interesting picture. that most of the blocks actually submitted in the last 2 seconds of the slot. This is what we are talking about in terms of latency. So there is a delay from each involved party to submit the block as late as possible to the end of the slot, so they can include as much transaction as possible to increase the total profit. So here, this picture just shows you that most of the blocks that landed on chain arrives 2 seconds before, and also some of them are too late, 2 seconds after the slot ends. But at the beginning, let's say the first 10 seconds, there are not that many blocks being submitted. So high latency in block submission could cause some major issues. For example, the delay in the attestation and also the congestion in the last few seconds to the network. I believe there are speakers talking specifically about the latency problem in the later sections. So I won't touch too much details in this. So now zooming in to the 2 recent market panic events. One happened on the 9th of November when FTX and 3 Arrow Capital collapsed, and the other one very fresh in your mind, probably just a few weeks ago, that we saw the SVB bank run and the stablecoins such as USDC and Dai depegged shortly. So here's a chart showing the Bitcoin price and the ETH price during these 2 crises. Interestingly, you see the first crisis actually lasted much longer, all the way until almost the beginning of February, whereas the recent event recovers very swiftly. So why do we want to look into these 2 events, and what is particularly interesting? So here we can see the daily MEV paid to the proposers have reached all-time high since the merge in a recent event. And that's like 9 times more than the average daily MEV. And that's due to the USDC depeg events shortly happened after the SVB bank run. Whereas before in the FTX collapse event, we see a slightly less severe in terms of the MEV sent to proposers, but still 6 times more than the average. Also looking into the MEV from a searcher's perspective, we collected the data from EigenFi. This is showing the arbitrage, sandwich, and liquidation specifically during these 2 events. You can also see the same pattern can be observed from this chart where the arbitrage volume on that day skyrocketed. And interestingly, looking at the cross-domain, so the cross-domain shows a slightly different story. You can see the FTX event has more impact on the cross-domain, whereas the recent bank run, SVB bank run, and the depeg event is more contained within the Ethereum network. So interesting data from Semiotics cross-chain MEV. Specifically, we are going to look at how much ETH were paid on these 2 days to proposers, and what's the builder competition look like during these 2 days, and also the latency in block submission, and these are on Ethereum. And we're also going to look at the cross-domain strategies on these 2 days. So on the 11th of March, when the bank run happened, we see that 6,000 ETH has been sent to the proposers. So this is equivalent to, or even more than, the average weekly total ETH paid to proposers. So at the bottom here, you see the weekly average is around 4,000, where on that single day, on the 11th of March, you see 6,000 paid. Similarly, on the 9th of November, when FTX collapsed, you see around 4,000 ETH paid. So these are extremely large single-day MEV activities that I'm highlighting here. On the right-hand side, I have a breakdown by the builders in terms of the total ETH paid to proposers. So back in November, we see that the top builders, Flashbots, Beaver Build, and Builder 69 dominates the market, taking about over 60% of the market. But in a recent event, the top builders portion have actually decreased. We see more builders coming into the space, and the non-top builders or the smaller builders actually takes 60% of the total ETH paid to proposers. So you see a kind of decentralization happening, a diversification in the builder market from the recent event compared to back in November. Now, what about the searcher strategies? So we also look at these 2 days. So on the left-hand side, you can see the arbitrage on these 2 days. And on the right-hand side, you can see the liquidation. So bear in mind, I mentioned the MEV Inspect Pi, which powers the MEV Explorer dashboard, is only counting liquidation and arbitrage. So it's only a small portion of what's happening on that day. Just to highlight that EigenFi also provides this data, and they also cover a wider spectrum of the MEV types. They also cover sandwiches, and also probably more protocols are included. But here I'm just sampling the data on these 2 days from MEV Explorer. You can see that most of the arbitrage happened among Ethereum, Bitcoin, and stablecoins. So in terms of the token that's been arbed, they're very similar between these two events. But in terms of the liquidation, it's more event-based. So as you can see, the recent event at the bottom here, we see the curve pool actually have gained a lot more portion in the whole pie, whereas the November event is also simply arbing through across different tokens. Okay. In terms of the search strategy by protocol, this is also looking into MEV Explorer data, where we have included 9 different protocols in this data. Just comparing the 2 days, we see the same story, basically. Back in November, when FTX collapsed, most of the arbitrages happened on Uniswap v2 and v3, whereas the recent event, we see an increase in the percentage in arbing on the Curve stablecoin pool. And in terms of liquidation, the recent event has not much in terms of dollar value of liquidation. That's kind of obvious because the recent event is not highly correlated to a liquidation event, whereas the FTX has a wider effect in the market where more liquidations were happening. Okay, in terms of latency, here on the left-hand side, we see the November FTX event, and then on the right-hand side, we see the recent event. Very interestingly, the chart on the right-hand side is very similar to the overall chart that I've shown at the beginning of this presentation. And it's probably showing that the latency gain is more severe if we compare it to the beginning of the merge, because most of the blocks, if you look back to November, are submitted quite evenly across different time frames of the 12 seconds, whereas now most of the blocks are submitted in the last 2 seconds. So just in a short span of 4 months, we see the latency gain is more severe. So this is probably not related to the market panic events, but more of a time comparison in terms of the relay and the builders getting more sophisticated and competing on landing the block. Now looking at the cross-domain, we have two different types of events happening also on the cross domain. The top arbitrage tokens are very similar to the single domain or on Ethereum. You can see most of the hopping paths happened or initiated from either the stablecoins or Bitcoin or ETH. So this is also very similar in terms of the percentage. So it's probably not that different across different market events. Just one thing to highlight, again, the cross-domain MEV in terms of US dollar value is much higher back in the FTX collapsing events. But the recent event has a much lower MEV value. Looking at the chains and the particular path, we see that Ethereum and BSC are the most frequently arbed chains. And also, one thing to notice is back in November, we also see Polygon and Arbitrum, whereas in the recent event, it's mostly between Ethereum and BSC. Okay, lastly, just a little bit more detail on the top 10 arbitrages by profit. We have shown the top 10 arbs conducted across different domains. So this is the exact path the bots have simulated where the bots can detect any arbitrage opportunities. Just to bear in mind that the data provided here is not actual cross-chain MEV realized data. It's based on simulations across different 8 different chains and around 40 different decentralized exchanges and 60 tokens. So there might be inaccuracy in the simulation where the missing arbitrage opportunities or the missing data could cause the value to be even higher. So just to summarize, I've talked a lot about different activities, MEV trends in L1, in cross-domain since the merge. So what we can summarize is that we know that MEV estimation is very difficult. We have only limited data from Ethereum and on-chain data. There is a lack of data in the estimation of MEV in the centralized exchange activities. We also observe like more relays and builders coming into the ecosystem since the merge, and the space is more diversified. The top builders market share, interestingly, during the high MEV periods have actually decreased. So this is also a sign showing that the builder market is more diversified than since the merge. In terms of search arbitrage strategies, we don't see too much of a difference between different market crises. Most of the arbitrage strategies focus on arbing across Ethereum, Bitcoin, and stablecoins. The liquidation strategies are actually event-based. So if it's more of a crisis that's related to liquidation of certain assets, then you will see the liquidation number in terms of MEV goes up. But in the recent event, this is not the case. Cross-domain strategies also have the same pattern. The MEV activity spiked during the crisis. But in terms of the magnitude, on average, it's much higher than the daily average, probably because a lot of the cross-domain arbitrages on a daily basis are not as much as on Ethereum, but when major events happen, the bots are searching everywhere for opportunities. So that's why you see much more of a spike during these events. And also the strategies differs from different market crises. It's event-driven. And lastly, just want to mention that because of the lack of data, we have a lot more room to improve in terms of the estimation of cross-domain MEV, the centralized exchange to decentralized exchange MEV. And there's still a lot of work to be done to collect the accurate MEV activities and total values. So here is a list of the references and also some of the interesting readings that I recommend. Lastly, special thanks to Tina from Flashbots and Eigen5, Bloxroute, Metrica, Semiotics, and Block Native for helping me preparing the slides and contributing to the charts and the data. Okay, I think that's the end of my presentation. I can take any questions if there is any.
I think we are running a little bit tight on time, ran a couple minutes there. So we're going to turn it over to Phil for the next talk. But I did see there were some questions in the chat. Flashbots has also posted a link in their research forum. So you can go there with any questions for follow-ups on this talk or any other talks, and we'll be checking there as well after the fact. So we'll bring on Phil now.
Hey, everyone. Can you hear me? All right, I'm going to assume yes and kick off my timer. So today I'm going to be talking to you all about hyper-MEVization, or information is the new money, or why everything is MEV and it always has been, or why geography and privacy, these are the two memes I want you to walk away with, run the world, or why your project is now an MEV project, which if you've been developing in the space, you may have noticed in the last year or so. So having heard my talk title, Shin on Twitter got really excited and said, man, will we see a complete theory of why information is the new money tomorrow in Phil Daian's talk? And maybe that could have been the talk, but today it's not. Sadly, I didn't have time to quite polish all the ends on a complete theory. So instead, I'm going to try to zoom out like 10 levels from our previous talk, which contained a lot of amazing data, and talk about some high-level concepts around MEV, information theory, privacy, decentralization, and all of these things that we're trying to build together. You should see this talk as like some informed trolling, which I think should be super fun for you. So take off your skeptic hat and put on your fun hat, and let's get started. Okay, so what are we going to try to do in this talk? We're going to try to marry these two different areas of study, these two different areas of research and modalities we've seen in academia. And when I was putting together these slides, I realized I don't really vibe with the institution of traditional marriage. So I at least need to use like, a same-sex marriage at the very least to represent this. But even so, not fully on board with this meme. But anyway, on the left here, we have kind of information-based fields of studies or technical fields-based of study, where you reason about entropy, bits of information, kind of computational algorithms on top of this, etc. Things like information theory, cryptography, and privacy. And on the right, we have economics, which traditionally has been also a modeling-based field, but in a kind of very different direction, attempting to model human interactions, attempting to organize human systems, much more political kind of bent. And here we have like the study of economics, cryptocurrency, and also MEV auctions. So we're going to try to marry these two disparate fields today with a single unifying set of abstractions that'll make both able to talk to each other better. And hopefully we'll have good communication and a lifelong relationship. So why do we think this is possible? Well, here I stole the Wikipedia descriptions of both information theory and money, which are two things that I want to draw some very high-level connections today and apply to MEV. So information theory, according to Wikipedia, is the scientific study of the quantification, storage, and communication of information at the intersection of probability theory, statistics, computer science, statistical mechanics, information engineering, and electrical engineering, like we just said, all very kind of technical or logical pursuits. Whereas money is this kind of nebulous economic concept. It's any item or verifiable record, notice the or here, so that's a very interesting or, that is generally accepted as payment for goods and services or repayment of debts. And generally people kind of flag these three properties as being interesting: medium of exchange, unit of account, and store of value. But you could argue that all of these three things, medium of exchange, unit of account, and store of value, as well as payment, are really just quantification, right? Quantification is unit of account, storage, store of value, and communication, aka medium of exchange of information, which here is called payment. So you really see some like direct correlations between reasoning about information and reasoning about money that become particularly salient once you apply them to blockchains. So to unify these two things, it would be nice to have a clean mathematical transform where reasoning about money can be translated into information theoretic models, frameworks, and results, and vice versa. I'm not at all claiming this is original. Many people have been trying to do that for a long time. And I'm going to talk about a little bit the history of these mathematical transforms and how we can apply these to MEV and maybe get somewhere. So in this talk, I'm going to argue, and this is really the outline for the rest of the talk, that the key to unifying these disparate concepts lies in both MEV and specifically in privacy primitives useful in MEV auctions. So in how specifically we define the MEV auction that we're running on chain and in kind of the real world. That is going to allow us to use both information theory as well as money to create the best systems for users. So let's talk about the history of these attempts and what's happened in the past. So one kind of strong existing attempt at this, oh, I think my camera probably crashed. Did it not? Oops. Don't want to show the green room either. It's okay. We'll continue without a camera. YOLO. Exchange attempts, existing attempts have kind of all been under the umbrella of this thing that we call mechanism design, which is kind of a 1960s field that was started by this person called Leonid Herzwig when he was kind of thinking about policy. How should central planners reach decisions on policy when the quality of the decision kind of relies on these information silos, right? And this kind of aggregation of information into a single output is what we call mechanism design. It studies the economic as well as the flows of incentives and information to make these kind of decisions for everybody. So some fun conclusions that underpin this whole field of mechanism design, etc. So first one is this thing called the Gibbard-Satterwhite. I'm probably butchering this because, it's been a while since I've taken a class on this theorem from 1973 and 1975. And this is two kind of philosophers as well as one philosopher and one economist that were attempting to study the same problem of allocation and voting and making decisions based on voting systems. And they basically, in their own model of voting systems, noticed that there was a tension between three properties, where kind of all three properties seem undesirable to a voting system. So the first property is if the rule is dictatorial. So basically, if we're all deferring to one distinguished voter, if there's one voter whose input completely determines the outcome of the vote, that seems super bad, right? There's this critical point. You can imagine like the one swing voter in the US election that ultimately chooses the outcome. We're giving this node a lot of power, and that surely seems undesirable, specifically to decentralization, etc. So that's bad. Let's say that's bad. The second tension is between the rule limiting the possible outcome to only two alternatives. So in their model, you can get past number 1 and 3 if you only consider two alternatives. Obviously seems bad, right? We live in a very complex world, and only kind of eliciting information or choices between binary alternatives is super limiting. And the last one, which kind of underpins and is the fundamental result of mechanism design, is if you kind of want something that's not dictatorial with more than two alternatives, you're always going to be subject to tactical voting. So in many cases, a voter will not be incentivized to vote their sincere ballot. They'll be incentivized to strategically play based on their model of what other people are playing, aka play the metagame, as we call it in crypto. And for voting systems, this is super undesirable because you collapse into this world where everyone is reasoning about the metagame, people are never truthful, and it's very hard to think about what actual outcome the vote is eliciting if everyone's playing strategically rather than giving input that's correlated to themselves. So a fun result that actually underpins the fundamental mechanism design studies of like the 70s and 80s is that if you just add one property here, you add utility functions to these individual agents, and you allow the mechanism that you're designing to do transfers over these this kind of shared set of integers, you can do things like model human rationality. You can build much more complex mechanisms using things like auctions and assumptions about how people will behave against these transfers that allow you to bypass many of the results of classic social choice theory. So basically what this says is that by adding transfers, by adding money, we can do much more than we can with pure voting. We can do much more than we can just with information elicitation if we don't have money. And that kind of kicked off the whole field of mechanism design. So money is a very powerful primitive. That being said, around the 80s and 90s, people actually started questioning this result and thinking, can we actually take half a step back here? And rather kind of going pedal to the metal on money and adding rationality to our life, maybe we can look at other models that allow these nuanced kind of transfers of information that let us achieve the same results as money does and bypass all these classical voting impossibilities, but do so in a different model. So this is one paper that kind of looks at this. I think the kind of paper itself is mostly irrelevant, but I thought the intro was like a very good phrasing of the problem. Specifically, this paper looks at continuous mechanisms, which is one modification you can do to the model rather than looking at discrete utilities, kind of allow continuous functions, etc. Same for transfers. Again, that's kind of a sidebar to what we're talking about, but the core of what they were saying in this intro is like, let's look at mechanisms without money and tweak them and see if we can still do things without at least classically what's considered money, this transfer of like a shared unit of account in this exchange, right? So what did they say? They basically said, in many contexts, these monetary transfers simply aren't available, and we still want to solve mechanism design problems. So specifically, they were looking at things like delegation within a single firm, where you can't like transfer really money within a single firm, or incentives aren't as clean or more political. Political science, so direct politics incentives, where often money is viewed as corrosive, or regulation, where like money transfers may be prohibited in certain contexts, among others. And they actually found that basically, if you tweak the model slightly, where you basically have principles commit to the principle of a mechanism, commit to a rule, and then the agent report private information that executes on this rule commitment, you can basically achieve a lot of the same properties as you can with money. So they're saying even if you don't have money, as long as there's a commitment to a rule that determines the outcome, and then there's information fed in that is kind of acting on this commitment by the agents, we can still get a lot of the same beautiful properties as if we have money. So this is kind of what I'm going to be talking about for the rest of the talk. How does this reasoning about commitment and information relate to money as we view it in cryptocurrency? How does it relate to on-chain tokens as we call them money? And how does that relate to kind of like the bull monetary case for cryptocurrency itself? A fun other connection, which is in the CS 700 UPenn lecture, dope class, highly recommend you check it out if you have some free cycles. It talks about how you can actually use differential privacy in mechanism design. So by tweaking the model to allow for differentially correct outputs and differentially private inputs into these commitments and into this information, you can also achieve like a whole class of different mechanisms that aren't possible without differential privacy. So basically what I'm saying is information theory is this framework that's tying together partially through mechanism design, which is one application of information, but also in all these connections with privacy and with economics and with money, trying to tie together reasoning about these different contexts and these same outcomes we want to achieve. So how does this make sense for crypto? Well, it actually gives us a roadmap for crypto. Like we need to marry information theory with money through commitments and privacy. It's a clear roadmap of what's happened in the past, what's been successful in like reasoning, and we need to port this over in a more clear, formal way into the systems we're building in cryptocurrency. So this is a little bit of the trolling I'm doing here. I have a lot more slides that I'm not going to get through, so I'm going to go through it slow because I think this is actually one of the fun ones. This is presented without proof, so shout out to Rune, who's probably triggered by this without proof part, and also, you know, maybe you can help us prove all this. There's a few kind of intuitive results that seem obvious once you start thinking this way. One is that if you have trusted private smart contracts, so let's assume we have this magic privacy box that we all trust, that gives you strictly more expressive power than public smart contracts from a mechanism design framework, from a modeling framework of like how powerful is our model, which is what we've been talking about with these various frameworks. You can prove this really easily. So look at just instantiating, like, let's say a VCG, sealed bid second price auction in crypto. If you don't have trusted privacy, it's impossible to do this securely with two untrusted parties. Let's say ETH and Solana and Avalanche want to run a sealed bid auction together with like the output of the validator set being the bids. You could see how you could build this with private smart contracts, but it's very difficult to imagine building it securely without, unless you have centralization, which is also private smart contracts, but in a much more ad hoc way. What does this mean? This means that once you have privacy, you can build many more auctions. So you can make auctions more secure and more powerful with privacy as a tool. Not only that, but there are many auction structures, for example, the one I just mentioned with VCG, not all auction structures, but many, that require this privacy interface to be able to be trusted, to be executed on a chain. So private smart contracts are strictly more powerful, otherwise known as informationally better money. They can give us more options to approximate more properties of more powerful money than we can without privacy, assuming the privacy comes with no downside. So this is the big asterisk here. If the privacy centralizes our whole stack and self-defeats its own goals, this doesn't work. If privacy can't be built and comes with like a huge cost, this is much less clear. So we're assuming here we have this magical privacy primitive, but assuming we have this, the world becomes amazing. And the last thing is that if we build systems that are interoperable and have global reach, we have more efficiency, right? This is the basic premise of decentralization. The pie is bigger when more people participate. Even if a system becomes less efficient, the economic value of participation shines through and gets borne out. So thus, the best efficiency feedback loop we can build is this loop of interoperability and trust and global reach. Proof sketch, this is trivial. So if people don't participate in mechanisms they don't trust, obviously a global mechanism is more valuable than a local one. So we're not in such bad shape here because crypto actually already has transfers. And transfers in crypto are fully trustless, whereas privacy in crypto is not right now. So we're in kind of this gray zone where there's a few classes of mechanisms we can build, anything that requires public transfers that can be satisfied by the blockchain, but there are many things that we can't build, the ones that require privacy, the auctions that are really more efficient if you have privacy. And this is what's causing externalities in the economics of our systems today, because many of our mechanisms require trust. So we're seeing this privacy because this privacy is economically useful. It lets us build more mechanisms. But because the privacy is not trustless, we're resulting in trust and we're resulting in externalities. So how can we solve privacy? What is the abstraction boundary here? What does privacy actually mean? And how the hell do we solve it? That's kind of the focus of the next part of my talk. So first, giving you the bull case. Let's say we do solve privacy and we come up with this magic black box that I just showed, and we have universal trusted privacy. Amazing. What will we gain if this happens? Well, first of all, powerful network effects for this better class of mechanisms I just talked about. This is going to embarrass the crap out of TradFi. So TradFi doesn't have universal trusted privacy. That's why you see regulation. That's why you see broker-dealer conflicts. That's why you see these auctions that nobody knows how they execute, because you don't have this concept of universal trusted privacy. So we should make this look embarrassing. That's my opinion as a space. This is our mission. The other thing is we should embarrass classical mechanism design, because a lot of the results, even regarding transfers, assume you have a trusted auctioneer to do these transfers. And if you have privacy and blockchain, with some asterisks that we can get into in a separate talk, you can kind of go beyond what's possible there. That would create a clear adoption case for crypto, right? Because many markets would just start working better than they do otherwise. Better for users with better commitments and better mechanisms and more efficient dApps. And, you know, that's how crypto eats the world, by building privacy that is actually better for users and universal. So where are we today? We have this kind of MEV supply chain. We're going to talk about various components here, including MEVshare and MEVboost. Both of these components rely on privacy. So the reason we can separate these roles and gain the efficiency of separation of duties and keep the decentralization of the validator set, of the builder set, of the searcher set, etc., is because we're able to have these abstraction boundaries. MEVshare and MEVboost being two examples of money reasoning abstraction boundaries we have today. But the privacy here is not perfect. The privacy here is flashbots just saying, trust us, and that makes it super suboptimal. And you can see that if you look even at the MEVshare flow here, which kind of shows you the transactions that a user makes, which represent commitments, and the selective data sharing, which allows them to define privacy. This is how we build a more efficient MEV mechanism that we believe is best to redistribute value back to users. And this is what we believe is the economically best way. However, it relies on these two very centralized concepts to achieve this economic output we want. So from the information theoretic point of view, it's super subpar. And from the kind of decentralized system reasoning, it's extremely centralizing, which makes it very suboptimal. Okay, so here I talk a little bit about how to use various techniques to go in depth and get out of this, including committees, SGX and TEEs, crypto economics, MPC, FHE, and the centralized systems that we're seeing today. Our belief is that you layer all these things together in a maximally decentralized way to truly achieve decentralization. So I'm going to skip this part of the slide, which kind of talks about how to use TEEs, how to use economics, how to combine them, and get to this world where basically we're going beyond SGX and we're achieving decentralized privacy. I will leave you with this to say that this is the goal of our Suave project. It's to achieve this defense in depth on this boundary between the ideal mechanism design for MEV extraction and allowing users to have these abstractions to control their privacy that can then be implemented into cryptography, that can then be implemented into differential privacy, into information theoretic reasoning frameworks directly. So we see the Suave primitives, the very formal core of Suave, as being essentially the translation layer, where expressing your transactions through these primitives allows for a direct translation to and from mechanism design and reasoning about the class of mechanisms we can build, the types of money we're building as a community, and where the basis of this money comes from, and how that relates to MEV. And in the other direction, translating into information and privacy and asking the question of how do we implement this and how do we protect this information. MEVshare and MEVboost is kind of the solo cup to our holy grail. It's good enough for now, it does the job, but it's centralized, so it tastes a little bit like plastic, right? So it allows us to start experimenting with these translations, but it does need to be replaced eventually with the holy grail, and that's what we want your help with. That's what we want you to help us with at Flashbots, and that's what we're doing. So this is real. We're already experimenting with introducing more decentralized techniques and more decentralized guarantees, including economics, including SGX into our existing market. Come join the conversation. We believe this forms the bull case for all of crypto, where MEV feeds into these Suave primitives. People start expressing and leveraging their privacy in negotiations. This fuels developments of SGX, TEEs, and encryption technologies like fully homomorphic encryption. Eventually, cryptography wins and beats TEEs because it's better. And I was criticized for putting the AGI bullet point last because I was told AGI feeds MEV and not the other way around. But there's your bull case for the economics of growth in the future. Join us at flashbots.net, and I am over time. So that is all the time I have today. Thank you very much.
Awesome. Thank you very much. So we have a couple of minutes before Vitalik comes on. One question I wanted to ask you earlier on is like, what are kind of your initial intuitions on you were describing how it's strictly better if we assume that we have this magical privacy thing that comes with no costs and it works perfectly and everything.
Yes.
But particularly based on where we are and where development looks like it's headed, what do you think is the kind of practical state of that? Is it's good enough, but it has some cost associated with it that's outweighed, etc.?
I think it's an extremely nuanced question, and I would love to give a talk on this. This is kind of the extreme version of like the reasoning. But I think that what I would say today is like the pressure for privacy, like the economic side, is really powerful. Like people want to build the types of systems that can only be built with privacy. That's why MEVboost exists. That's why MEVshare exists. That's why custom DApp layer centralized order flow auctions are being deployed. And that's why people are talking about things like builder features and using that for PBS and dank sharding and things like that. At its core is because like privacy and commitments together enable like new classes of mechanisms, and people really want this. And so what we've seen today is the centralized stuff has kind of been good enough, quote unquote, for now. Like it hasn't collapsed. It's somewhat economically diversified, but it is a huge centralizing pressure on our systems. And fundamentally, I don't think that's good enough. Adding SGX, I think, is a better step in that it kind of shackles these actors a little bit more and restricts what they can do, and limits them. But it's also not a silver bullet because it's still centralized. It still relies on Intel, etc. Adding committees or crypto economics similarly has like its own downsides. So I think we need to like do a combination of these things that just maximally decentralizes every single technique we can use, and then put the max decentralization pressure on, because the economics is not going away. So if we don't build like the decentralized mechanism for that to express itself, we're going to end up in TradFi. So that was like a very compressed rant, but that's kind of the state of things today, in my opinion.
One of the other slides you were skimming through, because we thought we were tight on time, it's talking about kind of the post-relay world and how we have to remove all the centralized components. Part of that starts to become kind of out of the hands of people like yourselves, where let's say that Ethereum doesn't actually end up implementing, for example, in protocol PBS. Like how bad would that be, quote unquote, in your mind? Or are there just other ways that we would have to figure out how do we decentralize that role in a better way if it's not built into the protocol itself and we keep the protocol super simple?
Yeah. So, I mean, I think in many futures, it's not critical that Ethereum Foundation pushes hard on this. Maybe the community is just aligned enough around making it like decentralized enough. And assuming we can decentralize things like much more than they are today, and predictably, like it will play out okay for the L1. Maybe it's okay for EF to take a step back and we're not like totally screwed. So maybe we can do a lot of this without the EF in terms of removing the relay, building decentralized alternatives, building like, sharing primitives for users and things like that. That being said, I think if the EF in practice doesn't have that in its back pocket as like a nuclear option, things get really bad, because like the worst case would be some angle of centralization entrenches here and we're like in a textbook Moloch. And so that's why I think PBS is super useful, because like many things the EF can do will like reset that Moloch. And I do think it's a little bit their obligation to stay on top of that, just because otherwise their own objectives will be defeated. I do agree with you. It's beyond my pay grade in this case. So like I can say what I think is the right thing to do, but ultimately like it's up to the community, and we'll try to maximally decentralize whatever is left, basically.
Awesome. Thank you very much. We will be moving on now. So we have Vitalik up next. He is going to be speaking on protocol economics, the Ethereum protocol's perspective.
Okay, thank you guys. Are you guys hearing me well?
Yep, we can hear you. You can go.
Okay, perfect. So what I wanted to give today is a brief overview of like what protocol economics looks like in general, and focusing on Ethereum and some of the changes that have happened to both the Ethereum protocol and the Ethereum application ecosystem over time, and touch on some of the issues of how that interacts with some of the things that might happen with both the Ethereum protocol and the Ethereum application ecosystem in the future. So some of the protocol economics questions that matter, this is pretty basic. So one is, what are the incentives facing users? Two is, what are the incentives that are facing consensus actors, so meaning miners and validators? What is the behavior of the chain, both average case behavior and extreme case behavior? And how does the behavior of the chain affect incentives at the application layer? So for example, if an application depends on the chain working in a particular way for its incentives, then if the chain ends up suddenly working some different way because of an attack, then that might cause the application to have some problems. And how do applications affect any of the incentives? Incentives facing users, incentives facing consensus actors, incentives to do things that might break the chain, and all of this stuff. So there's some pretty complex interactions between all of these, right? So users send transactions to the chain, users read data from the chain, the state of applications lives on the chain, and so you could say the state affects or the chain affects the state of applications. Applications give incentives to users, and applications are the reason why users send transactions that have particular strings of data instead of other particular strings of data. Consensus actors maintain the stability of the chain, and the chain provides some intentional in-protocol incentives to consensus actors. So this includes mining rewards, validating rewards, various fancy and protocol-defined rewards. It also includes penalties, and applications also provide more incentives, right? So there's in-protocol incentives, and then there's also extra protocol incentives. And ultimately, this whole MEV situation is a situation about extra protocol incentives that arise mostly accidentally, and how they end up affecting some of the incentives to run the chain. So some of the risks to watch out for are, I mean, one, I think, and the one that we've focused on for the longest is just the incentive for validators to act correctly instead of acting incorrectly. And in particular, the incentive to keep advancing the chain instead of trying to 51% attack, or, for example, trying to censor the chain, right? And the kind of battle between the user's incentive, which is the transaction fee, and now just a priority fee to get included in the chain, versus potential bribes to censor. And might bribes to censor happen accidentally, or bribes to censor are something that might happen intentionally, and like trying to set economics so that the user incentive has the upper hand, and so that side incentives don't have the upper hand, right? Like that, a lot of that was a big part of the discussion in things like PBS censorship resistance. But aside from that, there's also economies of scale in incentives. And one example is that if user incentives are complex, then that might lead to wallet centralization, right? So for example, pre-EIP 1559, the incentives facing users in terms of how the user sets the gas price were pretty complicated. And a user got a pretty complicated trade-off curve between getting their transaction included quickly and waiting a very variable and unknown amount of time for their transaction to get included. And this both caused a huge amount of deadweight loss because a lot of users waited for their transaction to get included for no good reason. And it also, I think, made it harder to create wallets and probably ended up contributing somewhat to dissuading new wallets from getting created. Post EIP 1559 incentives for users are generally a lot simpler. You just set a reasonably high max base fee, and then you set the priority fee to some probably constant number, or if there is an active situation going on, you could set it to something higher using a much dumber algorithm, and you get penalized much less, right? But generally, the situation is simpler for users. We also see economies of scale for consensus actors, right? And that leads to consensus centralization. So if the strategies that consensus actors see are something that's constantly complex and shifting, and especially requires access to proprietary information and all of these things, then that's going to be really bad for solar staking. It's going to be really bad for decentralized pooling even. It's even going to be really bad for small centralized pools. And so it's just going to lead to big pool domination, right? And I think we even saw near the end of the proof of work era, Ethereum's centralized pool domination was something that started to get pretty bad, right? We got to the point where like 2 mining pools were enough to get over 50%. And Bitcoin is like a little better than Ethereum proof of work, but it wasn't that much better than Ethereum proof of work. And like I think we want to really make sure that proof of stake goes in a healthy direction as well. And then finally, incentives to have low latency are also a different kind of centralization incentive because they are a geographic concentration incentive. They're also a cloud computing incentive. And both of those things actually contribute to jurisdiction risk, which is another really important and big risk to the credible neutrality of a blockchain, as I think we've seen over the past year. So a lot of this started basically with the rise of DeFi, right? So burst MEV, meaning a kind of these opportunities to grab up a large amount of money by being the final actor that constructs a block. A lot of those actually existed even all the way back in 2017. So there were these pretty famous ICOs that happened in 2017. The picture on the left is a graph graphing the gas price. And it got to an extremely high number, and there was just like a huge amount of deadweight loss. I think this was specifically during the basic attention token ICO. And had there been MEV collection infrastructure at the time that could have just been collected by whatever mining pool was sophisticated enough to have that infrastructure, right? But realistically, at the time, there were just not enough of these incidents to probably justify paying the fixed costs of building the infrastructure to try to capture all of this MEV. But then in 2019, 2020, we had DeFi summer, and at that time we had basically kind of the start of essentially permanent combination of kind of ongoing MEV that would happen pretty much every block, and even bigger and even crazier spikes than we saw in 2017, right? And that created economies of scale for consensus actors, which ended up creating the necessity for things like PBS to try to kind of split up the economies of scale heavy role so that the remaining role would not be so economies of scale heavy. And the chart on the right is daily extracted MEV gross profit, which shows how MEV basically is a constant, but at the same time it is very spiky. EIP 1559, right? So that greatly reduced waiting times for users, and it also greatly reduced the incentive to use complex gas price strategies, as I mentioned, which reduces barriers to entry for wallets. The merge actually reduced waiting times for users even further, and I think there's going to be some research on that coming out fairly soon. And that's something that's going to improve further over time. The merge actually does a lot of strange things at the same time, right? So the merge, first of all, it completely changes the class of participants maintaining consensus, right? Which means that the side incentives of people maintaining consensus change a lot. Before it was miners, now it's ETH stakers. Miners tended to be a group that was kind of off in their own corner and often not even very loyal to Ethereum because they would jump between Ethereum and other protocols. Now, there were some miners that were definitely very loyal to Ethereum, but there were also others that were not. It's people that had access to hardware, whose main expertise was in things like hardware. Meanwhile, ETH stakers, on the other hand, are a subset of ETH holders, and ETH holders tend to have less sophistication in hardware, but they also tends to be more integrated into the Ethereum ecosystem in other ways. And there's complicated effects, I think, from the change of like what kinds of people are doing the mining to what kinds of people are doing ETH staking on average, right? So I know a lot of miners actually ended up becoming ETH stakers, and so a lot of actors carried over from one side to the other. But on average, the composition did change a lot. The merge also made reorg attacks vastly harder. So there's this piece from myself and Georgios from almost 2 years ago that talked about how reorgs after the merge are going to get much harder. And then just also a very different incentive landscape in terms of things like centralization and joining a staking pool and what kind of pools are even possible and all of these issues, right? So the merge changed a lot. And, I think the merge is one of those things where even 10 years from now, if someone asks, what kinds of effects did the merge have, as the apocryphal quote about the French Revolution goes, the correct response is going to be, it's too early to tell. So that's existing changes. Now, upcoming changes. Withdrawals are going to get enabled in the next hard fork. Then stuff going beyond that, single secret leader elections, different types of in-protocol PBS, and finally, single slot finality. So withdrawals, basically two consequences, right? People can withdraw, and so people will withdraw, and that reduces the total amount of ETH staked. But then also people can withdraw, and so people become more confident that if they stake, they'll get their money back, which leads to more ETH getting staked. Which one of these dominates? We have no idea. Could go either way. Though ultimately, I think the main practical consequence of this is going to be a change to the total amount of staking and possibly also a change to the composition of stakers. My hope is that for solo stakers, things are going to become more friendly and withdrawals are going to kind of reduce the premium that pools have, because currently pools have this premium that they're the only way to get liquidity. And with withdrawals, you're going to be able to withdraw and get your money back in a couple of days. So it'll be interesting to see what kinds of consequences that has. But single secret leader elections, these are interesting, right? So only the proposer will know that they are the proposer before the block is produced. And though the proposer could voluntarily reveal that info and even prove that they're going to be the proposer. So the intended effect of all this is to reduce the DOS risk against proposers, right? If no one knows who you are until the block is created, then there's nothing that can be DOSed. And once you reveal who you are by creating the block, well, the block's already out there. And so even if everyone DOSes you, well, the block is already out there and it is going to join the chain. But there's this interesting research question of like, are there unintended effects? And in particular, especially in the combination of PBS, like, would there be incentives for proposers to pre-reveal their identity to anyone? I'll skip over like PBS for now because I feel like everyone is going to be talking about PBS, and it's probably the kind of primary subject over the next few years in some sense. But it's a fascinating rabbit hole. And then single slot finality, right? So single slot finality basically means instead of blocks finalizing after 2 epochs, every slot is just going to immediately finalize a block, with the exception of these special cases where you have an inactivity leak. Single slot finality means even more reorg security. It might make Ethereum more bridge friendly, but as we'll get into, with layer 2 pre-confirmations, single slot finality will not be de facto single slot for a lot of users. And I think that's going to be an interesting nuance. So finally, the switch to layer 2 and protocol economics, right? So how does the rise of layer 2s affect the incentives facing specifically actors in the protocol at layer 1? A lot of it depends on like how the whole layer 2 thing plays out, right? So one is sequencing style. So on ETH Research, Justin Drake made this post about what he calls based rollups, basically rollups that just let layer 1 directly do the sequencing for them, versus some kind of layer 2 controlled sequencing where you have a layer 2 defined sequencer auction and all of these things. What percent of layer 1 DeFi will move to layer 2s? If the answer is 0, layer 2s have no impact. If the answer is 100%, then everything depends on how the layer 2s work. And then the answer could be somewhere between 0 and 100%. Fraud-proof windows and censorship, that's a pretty simple one. Pre-confirmations that we'll talk about. And then this kind of final question, which is, will the switch where a lot of activity moves to layer 2s make layer 1 economics more boring, possibly by insulating the layer 1 from the side effects of some activity? Or will it make it less boring by creating more complicated interaction effects? So based rollups, right? So when I made my post on rollups about 2 years ago, one of the things that I zoomed in on is basically this question of in a rollup, you have these batches that kind of take a lot of transactions and commit them into the layer 1. And the question is like, who has the right to submit a batch? Option 1 is total anarchy. Anyone can submit a batch at any time. And here I said, this is the simplest approach, but it has important drawbacks. Particularly, there's a risk that multiple participants will generate and attempt to submit batches in parallel. Only one of them will get included. This leads to a wasted effort in generating proofs and wasted gas in publishing batches to chain. With PBS, a lot of these costs really get reduced, especially the gas costs get reduced, right? Because you can make the gas payment of a batch conditional on that batch getting included and getting correctly processed. And this is something that you will have to work through the builder ecosystem in order to do. But if the builder exists, then you can do it. And so suddenly what I called the total anarchy approach, or what Justin calls the based rollup approach, suddenly becomes viable. But then there's these also other approaches, right? Centralized sequencers, you could do sequencer auctions, you could do DPoS voting, you could do random selection from a set, you can combine sequencer auctions with DPoS voting to remove the sequencer if they're abusive in some way that layer 1 doesn't detect but still really matters to users, right? And so there's a lot of options that are not based. And there's an interesting question of like, do rollups want to be based or not? Could layer 2s absorb complex layer 1 MEV? If rollups are based, then they can't, right? Because layer 2 MEV just becomes layer 1 MEV because the layer 1 PBS system just does sequencing for the layer 2s. If a large part of layer 1 DeFi stays on layer 1, then also no. If there are other complicated interaction effects, so like for example, if rapid layer 1 transaction inclusion helps layer 2 arbitrage, and whoever the first transaction is to get included ends up just like becoming the first one that successfully can do a particular layer 2 arbitrage, or like if there's other interaction effects, then maybe no, and otherwise, maybe, right? And this is one of those interesting research questions. Fraud and censorship, pretty easy. If you can censor a chain for a week and that chain doesn't socially reorg you, then you can steal from optimistic rollups. But I would argue this is not too interesting because there's like much shorter term censorship attacks that are more realistic that can seriously hurt DeFi, right? If you can only censor for an hour, then you can do a huge amount of MEV extraction on all kinds of DeFi projects like rollups or like Uniswap-like systems, potentially even liquidations. You might even be able to force liquidate people and prevent them from filling up their CDPs, and you could do all kinds of stuff, right? And like that's also something that's worth thinking about. But that's like not a layer 2 specific problem, right? It exists on layer 1 or layer 2. Pre-confirmations. So users generally want faster confirmations than even 12 seconds. And a lot of rollups are not even doing 12 seconds because they want to save on fees. And also, single SWAT finality might end up increasing the SWAT time, maybe from 12 seconds to 32 seconds. And so what a lot of rollups are thinking about is doing these pre-confirmations, right? So you have an off-chain pre-confirmation protocol that pre-confirms layer 2 blocks, and then eventually you have a batch that kind of submits the rollup blocks, and then possibly some like proof, a compact proof of the pre-confirmation into a layer 1 block. All of that gets verified, and then that actually solidifies the block at layer 1, right? And so with this, even if you have single slot finality at layer 1, like the user's experience is that step 1, they accept their transaction gets accepted into a layer 2 block. Step 2, the layer 2 block gets pre-confirmed, and then finally step 3, it gets confirmed on layer 1. So arguably, this is a point in favor of SSF because if layer 2, everyone's using layer 2s and layer 2s have pre-confirmations, then it's okay for layer 1 to have longer slot times, and longer slot times generally make SSF easier, but still you have 2 tiers of confirmation. And I think the 2 tiers of confirmation thing might be fundamental because layer 1 is not willing to centralize as much as layer 2, and so layer 2 confirmations are always going to be faster. Like there's just always going to be some kind of curve where the user's knowledge of how confirmed their transaction is doesn't just jump from 0 to 100% immediately. It kind of goes up over time, and so you have some notion of pre-confirmation that's inevitable. Now, notice that layer 2 pre-confirmations are incompatible with based rollups, right? A rollup cannot be based because if it has pre-confirmations because, well, the submission protocol has to force the system to respect the pre-confirmation mechanism, and a set of layer 2 blocks that does not respect pre-confirmations, it has to just reject, right? And ultimately, like it would be the layer 2 and the pre-confirmation system that collects most of the MEV instead of layer 1, right? So based rollups cannot pre-confirm, which is I think an important thing, unless you do some kind of layer 1 universal pre-confirmer, which could be interesting. Will layer 1 be more boring or less boring? I mean, my hope, what I would love to see is for layer 1 to be more boring, but this is not guaranteed, right? Layer 2 could absorb functionality and risk, or layer 2 could create complicated interaction effects between layer 1 and layer 2. And I think ultimately, we need more analysis of a fully post-layer 2 world, and I think, like MEV economics with layer 2s in mind are just a really fascinating research topic that we need. We'll probably continue to need a lot more people thinking about for years. So thank you.
Awesome. Thank you, Vitalik, for the great talk. And that actually perfectly segues into our next talk by Hasu, who is going to be talking about decentralizing sequencers and PBS in the context of rollups. So Hasu, you can come on now.
Hey, thank you, Vitalik. Thank you, John. Hey, I'm Hasu. I currently lead strategy at Flashbots, and I will talk to you about decentralizing sequencers. Wait, it's all PBS? Yeah, always has been. So in this talk, I will convince you rollups are in the process of decentralizing their sequencer. So every rollup has a decentralization roadmap, and all of these roadmaps have some plans for decentralizing the sequencer. However, the way that sequencing works in layer 2, it actually combines what is the equivalent of a layer 1 proposer and a layer 1 block builder in the same role. And this creates a variety of problems unless we start to address it by separating these two roles on layer 2, just like we did on layer 1. In addition to that, even if we do PBS on layer 2, there are novel challenges involved around privacy, cross-domain MEV, and lower latency than we are used to on layer 1. And so we will get into these in the talk as well. And we will see PBS is essential, but it is in itself not enough. We also need to decentralize the builder role itself. So decentralizing rollup sequencers. What is a sequencer? There are basically 4 steps involved. So as a user, you send your transactions to a layer 2 sequencer who orders them according to some policy and then gives the user some receipt to the user. So Vitalik was talking about pre-confirmations. That is step number 3 here. And then the sequencer sends the ordered batch to the DA layer, where it basically becomes finalized from the perspective of the layer 2. So this particular diagram is taken from
Starknet, but the above is how it works in pretty much every layer 2. So there might be some small differences. For example, in Starknet, the sequencer is also the prover, so they have even more responsibility. But all of these can be stripped out and will be stripped out over time. So why is decentralizing layer 2 sequencers important? Well, because, as Vitalik was alluding to, because rollups are becoming more and more important, and more volume and liquidity is moving over to these new execution layers. And I don't think we have even started to imagine the end state of how blockchains will scale, as we are kind of seeing with these different rollup providers who are now not even just focused on building their own rollups. No, they are focused on, they've all pivoted to kind of rollups as a service. And I think it's quite possible that we will see a future where spinning up a new blockchain is kind of like spinning up a new smart contract today. And so we will have many rollups, and these rollups all will have sequencers. So we'll have many sequencers. And today, all of these sequencers are centralized. And centralized sequencers can censor the user. They can go offline. They can charge arbitrary prices. They are a regulatory choke point. And they can see the user transaction before it gets confirmed. And they can do various things with this transaction that is hard to attribute. And so while rollups have these great guarantees, so we can get always the transaction mined through the layer 1, and the sequencer cannot force an invalid state transition and so on, then there's still a lot of problems with them, and that's why we need to decentralize them. There are various proposals for how to decentralize sequencers. One is the layer 1, or quote-unquote other chain sequenced approach. So that includes the based sequencing that Vitalik was talking about. There are also other approaches, for example, around shared sequencing. So that's when one blockchain sequences many other blockchains. So shout out to Espresso, for example, who have put forward this vision. You have the optimism style sequencer/block auction, where the right to propose the next block or next series of blocks is auctioned off every now and then. And then what Starknet is planning, random selection from a proof of stake set. So in that case, you have basically a consensus mechanism on top of your rollup, and a proposer is selected randomly, and they get to propose the block. This is very similar to how it works in the layer 1. And then finally, you can have various committee-based solutions, and the most common one would probably be first come, first serve. This is where a committee just looks what transaction the different nodes saw first, and then come to some kind of consensus on that. And yes, we were saying already in the summary, in the layer 2 right now, what we understand as the term sequencer actually combines the equivalent of a layer 1 proposer and a layer 1 builder, especially in the leader election mechanism. So that is the proposer part. And then the ordering mechanism, that is the building part. And so if we go back to these different proposals that have been put forward, so they actually have different leader election mechanisms, different ordering mechanisms. But what I would like you to take away from this slide is only that the innovation that is inherent to these proposals is almost entirely in the leader election mechanism. So nobody has any credible plans about the ordering mechanism, right? So they are only focused on the leader election mechanism today. And that is a problem, because if you do layer 2s without proposer builder separation, then what you do, then you have the two roles bundled like they used to be bundled in Ethereum layer 1 before MEV was a big deal. But now MEV is a big deal. And what will happen is you recreate the dynamics of pre-PBS days from Ethereum layer 1 on these rollups. And what you get priority gas auctions again, you get front running, you get failed transactions in a clocked up P2P layer from the searcher strategies who are being forced to compete in inefficient MEV auctions for the MEV. And because the auction is less efficient, you will also get a lower proposer revenue that leads to a threat of vertical integration between searchers and block builders. So all of these problems that we talked about 2 years ago on Ethereum, boom, they are back now on layer 2, making their comeback. And so that's why I would actually say, when we talk about decentralizing sequencer today, sequencer as a service, I think it would be more accurate to actually talk about proposer as a service, because that's what it really is, right? We are only looking at the proposer today. So we need to start separating these two roles on layer 2, just like we did on layer 1. Here's a quick refresher for you what PBS actually does. So the effect that PB has on Ethereum is it shields the proposer role from the centralizing effects of MEV by making the most valuable block available to all proposers equally. And you don't, whether it's a small solo validator or it's a big staking pool like Lido or Coinbase, they all make the same from MEV, and that is a huge, huge achievement. It also unlocks competition on features from block builders that don't require any protocol changes to Ethereum. And this has created more privacy for bidders, more expressivity for bidders. And here I would particularly highlight the introduction of the bundle by Flashbots that decoupled the position of the transaction from the price. Because in the public mempool, you were only able to express basically these two dimensions through a single unit, which was the gas price. The removal of negative externalities from the chain that were the result of these bad searcher strategies, and maximizing revenue for the seller. And so we can see these map one-to-one to the problems that we laid out earlier, and PBS solves them all, which is amazing. So we need PBS and explicit MEV options to maximize protocol revenue and minimize negative externalities on these layer 2 networks and their users. But PBS on layer 2 also faces novel challenges that were not necessarily here when we designed PBS on layer 1. So a big one, arguably the biggest one, is privacy. So all of these centralized sequencers have gotten the user very addicted to the idea of quote unquote easy privacy, right? And now I think it's a very hard choice. Like, do you remove privacy when you decentralize the builder, or do you try to decentralize it? I think both paths are very, very hard. And it's not clear that either of them is necessarily better or easier than the other. And I think this kind of speaks to the difficulty of rollups just taking these shortcuts through a centralized sequencer in providing the users better UX. And now it's going to be very hard to either move away from that UX or decentralize it. So how do we recreate privacy in a decentralized way? So one is, maybe you still have centralized block builders, but at least these centralized block builders are competing with each other in a sort of competitive market, right? But the downside here is that these builders all have they all have their own unique form of trust. And so as a user or as a blockchain, you need to decide which builder do you trust, which builder do you not trust. And this really risks enshrining some builders over others. And it also creates a big incentive for vertical integration between different supply chain participants, because you're always more willing to trust yourself than you are willing to trust someone else. And so this option, I would argue, is very centralizing. Second one is, again, the aforementioned committee-based solutions like threshold encryption or first come, first serve. These might also work together. And then option 3, which is having one homomorphic. So I mentioned the second one because this is basically a way of privacy in easy mode, if you will, because it's much easier to stand under the idea of an encrypted mempool, or any system really where audio back, okay, any system really where different parties share the same type of privacy, where if you trust the privacy zone, then you can also trust everyone within it. And so, for example, what this would mean, you send an encrypted transaction to a mempool, and you know it's going to be kept private no matter who interacts with it going forward. And so this is what we're working on with Suave, but it's also super hard. Then you have cross-domain MEV. Just when you think you're out, they pull you back in. Even if you have competition between these centralized builders, you still have the problem of cross-domain MEV. The builder market is already naturally very centralizing due to economies of scale. But layer 2s, just because of their existence, they make the problem even worse, because the more fragmentation, the more domains there are, the more fragmented liquidity and trading volume is, the more cross-domain there will be. And this creates a strong centralizing pressure on the builder role through demand for atomic transactions. And then finally, there is latency. This I would put in the same category as privacy. So rollups, they all wanted to have, or at least I talked to Arbitrum, and they wanted to have based sequencing originally, but then it turned out that users liked faster confirmation so much that they had to switch to a centralized sequencer with faster pre-confirmations. And this lower latency, this is a big friction with decentralization. We need geographical decentralization for neutrality and decentralization and other things. But for that, we need our systems to be insensitive to latency. And if you lower the block time too much, then what you get is you encourage vertical integration, geographical integration between proposers and block builders, and you discourage participation from anyone who is not able to vertically integrate, who is not able to co-locate in that same geographical area. And so that's why PBS is essential, but it's not enough. We also need to look into decentralizing the builder role itself. So that's what we're trying to do with Suave. There are other proposals as well. So, but the idea is building the best MEV auction and making it decentralized, because that's what allows us to do the heavy lifting on ordering for these other chains. Removing all elements of trust in flashbots and searchers and block builders from the system, making it private so that participants have the ability to trust the auction and trust others and don't have this need to vertically integrate with others in the supply chain. And making it scalable, because by connecting many different domains, we allow for the expression of cross-domain preferences as well. So John Charbonneau, our host, has this great diagram here that actually shows the roll-up transaction supply chain in the future, possibly. And it shows that the sequencer really becomes the proposer, right? And you can have proposers that basically sequence many chains, but you still need the block builder. And because you have these centralizing effects on the block builder, you also need the block builder to be decentralized. So in the rollup endgame, we're going to need all three. We're going to need the decentralized sequencer, we're going to need the decentralized builder, and we're going to need the private mempool. Otherwise, it's not going to work out. And dear rollups, please make MEV a more central element of your decentralization roadmaps. Remember, sequencer equals proposer plus builder. Don't ignore the last part. We need to decentralize both. So come reach out to us to learn more about Suave, and come to our forum, collective.flashbots.net. That's it from me. Thank you very much. And yeah, I'm happy to take any questions.
Thank you, Hasu. We're running a couple minutes over, so we're not going to actually have any time for questions on this one. But we are going to be moving over. This transitions well into our next talk. We'll be bringing on Davide, Barnaby, and Justin to be talking about MEVconomics meets MEVconomics. And we'll be starting with the presentation.
Hello, can you hear us? Yeah. We are kind of gonna have like a fireside chat discussion on the lay of the land more broadly. Like we start with like a brief pitch introduction from me, then Justin, then Barnaby, and then probably gonna have like a longer Q&A. So I can go to the next slide. And I'm going to start at a high level defining MEV flows kind of from first principles. So if we go to the next slide. So essentially, what I want to start is that these MEV flows are actually a property not of the blockchain itself, but of the economy that we build on top of blockchain. So like the system of value transfers, which includes also like the economic and financial games that people play on top. And so they kind of affect the Ethereum protocol, but also the trustless infrastructure, or hopefully trustless infrastructure on the Ethereum protocol, and then like any other protocols that user may use. So essentially, when we think about how can we make Ethereum protocol MEV resilient, which is an idea that I put forth a few days ago, we actually need to think about how the whole system can be MEV resilient, right? And these properties, which I call blockchain SEC properties, so security, equity, and cost efficiency, like some of them are inherited directly from the blockchain, but some of them relate to the broader system, right? So essentially, like, what are these properties? Like the first one is economic security, which in the context of MEV, we know that it changes the incentives from validators to behave honestly. So we want to build incentives that are robust to MEV. With like some of the solutions we are developing is essentially to make these incentives robust to this process that arose, and that now it's a constant because people are playing these DeFi games continuously. The second property is equity. So here we think about equity both in access. So essentially, like people should not be censored, but also equity in distribution. People should have a fair game and have a fair distribution of value, like comparable to like the externalities they introduce into the system. So we want to minimize the losses for honest user. And then the third one is cost efficiency, which affects a fourth property, which is the utility of using the blockchain. And here, essentially, we want an ethical user that are just there to like play the game of extracting rent to have minimal rents. So this is kind of the high-level goal we are trying to achieve. And I'll argue there is like 4 ingredients to achieve this. So the first one is we need to reduce MEV with clever design. So essentially, both at the game level, so the economic apps that we build should be cleverly designed to account for MEV, and also at the meta game level, at the transaction inclusion game, also that one should be cleverly designed to account for MEV, and that's what most people in this group are working on. Then the second step is extraction. So like there is a potential MEV in the system. This can cause instabilities to incentives. So we need an efficient technology for extraction. Today, this is searchers and builder. Then the third one is capture. So once the MEV is extracted, we need to make sure that this is captured, and this needs to be captured by trustless protocol. It doesn't need to be entirely the Ethereum protocol. It can be order flow auctions or other protocol that are in the broader infrastructure, but it does need to be trustless because Otherwise, there is going to be capture, and like this mechanism will not be credible. And then finally, MEV allocation is very important, because essentially, like once we capture this MEV, we essentially need to make sure that this flows back to the users, or essentially, maybe we can talk about this a little bit more. What should be the goal of allocation of MEV? So if we go to the next slide. So here is a cartoon view of the block supply chain, which kind of includes, if you stare at it for a little bit, all the elements that we are seeing today, including the bad elements: exclusive order flow, vertical integration between searcher and builder, horizontal competition at different layer, maybe stronger versus not stronger. There could be segmentation. And then finally, MEV take can differ at different layers. So if you look at this, you realize that although we would want a clean supply chain, we actually have a supply network where like there is several connections across layers. So we kind of need to be aware of this. And essentially, if we go to next slide, what we started doing is like looking closer into all the important metrics of the supply network. We launched Rig Open Problem, which is essentially a way to advance research around like more complex properties of this supply network. So essentially, like what we are going to try to do is create an open source framework to both define and measure these more complex metrics that are related to inclusion delays, take rates for different segments of the market, validator deviations from honest behavior. And our goal is to bring together multiple parties in the ecosystem. We already have people from Flashbots, Block Native, AgenFi, Uniswap Labs that are looking with us at what's happening concretely into the market in order to then use this data to like design better protocols and systems. And this is all for me. I believe Justin is up next.
Okay, great. Thanks, Davide. So today I want to talk about MEV precedence, which I guess I just named today, which is what is the ordering in which MEV, to which parties the MEV should flow to, like who should have precedence on the MEV over other parties. And basically, in my mind, we have two types of precedence lists. We have the precedence list that we want and the precedence list that we have, and those are actually different today. So in terms of what we want, I think is we want to give users precedence over all other types of participants over the MEV. So if they create MEV, they should be the ones that capture it through this concept of rebates, called MEV share and things like that. And then my claim is that the next entity in the precedence list should be holders, the token holders. And the way that they receive these flows is through a burn. So we already have part one of the burn, which is EIP 1559. I think of the base fees as actually part of MEV, right? It's not fancy or sophisticated MEV, but it is extractable value, and it turns out to be extracted by ETH holders. And there's this other idea called MEV burn, which is kind of part two of the burn, where all the MEV, not just one part of it, goes to the holders. So already from these two items in the precedence list, kind of the way that I see where we want to be moving towards is users capturing all the MEV that they initiate, and then all the rest, or almost all the rest, going to the holders. And now the reality is that there is a whole MEV pipeline or chain or network, whatever you want to call it, of intermediaries And these intermediaries will capture a little bit of MEV, but they will capture a very small minority. And in the competitive market, these should the inefficiencies should go to zero. And the reason why I ordered these entities in the way here is basically the closer you are to the user, the higher the precedence you should have. So if you're an interface, for example, you're very, very close to the user. You provide value by bringing the user onto Ethereum, and so you should have precedence over the searcher. The searcher is doing complicated stuff in terms of building the bundles, and that's maybe more valuable than the builder, which is just bundle merging. And then the relay is doing something even less valuable, and then the proposer is just doing almost nothing. Like the only thing that they're doing is that they're receiving a few bids, and then they're picking the highest bid and they're signing it. They're doing almost no work. Now it turns out, in terms of what we have today for the users, I put the skull emoji here, that the users are being not receiving the flows, and so they're not being prioritized in this precedence list at all. And in position number 1, what we have is the proposer. So the proposer, who should be, in my opinion, the very bottom of the precedence list, is right now at the very top of the precedence list, and that is something that I think needs to be fixed. And one of the cool things of this kind of model is that we have a clean definition of toxic MEV, and it's basically this idea that it's MEV that doesn't respect the precedence list, or at least the ideal precedence list. So in this case, any MEV that should be going to the users but instead is going to the proposer is toxic MEV. So things like front running and sandwiches. And you can argue that maybe proposers, receiving MEV that doesn't originate from the users is also toxic. And I'll talk about that later, because it leads to all sorts of economic distortions that manipulate the incentives that we've tried to bake into the protocol as designers. And then in terms of what we have, again, we have these more commoditized entities that will receive a small portion of the MEV in a competitive market. Okay, now I want to talk about maybe what is the most controversial thing of this whole diagram, which is why should holders have precedence over the proposers? And this goes back to this idea of these economic distortions that happens when you give the MEV to the proposer. And so the way that we give MEV to the holders is through MEV burn. I won't explain how it works. That's for another talk, but I'll explain some of the advantages of it. So on the left, we'll have distortions that happen if you give the MEV to the proposer. So the very first one is this idea of reorgs, short-term reorg. So if you have a very valuable block, 100 ETH, 1,000 ETH, 10,000 ETH, 100,000 ETH, who knows? In a single block, then really you're putting a lot of pressure on the chain to do these short-term reorgs, and we haven't seen that yet, but it might happen as the market becomes more sophisticated and more mature. So that's the first thing that is not good when you give the MEV to the proposer. The second thing, which is not great when you give MEV to the proposer, is that you're basically introducing a lottery. All the proposers are lottery participants. They each have lottery tickets, and as in most lotteries, almost everyone is a loser, right? Almost everyone doesn't win the lottery, and then there's like the one person, the one proposer who wins the jackpot at the expense of everyone else. And in order to correct for this fact that almost everyone is a loser, the proposers need to pool, and that creates centralization vectors. It goes against solo validating and things like that. So that's a second economic distortion that we would avoid if we were giving the MEV to the holders as opposed to the proposers. the third economic distortion is what I call rug pools. So it's rugging the pools, and here the observation is that even if you have a pooling system, it's still not incentive aligned, and the reason is that the operator of a validator that's part of a pool has an incentive to basically not give the MEV to the pool if the MEV is large enough, specifically is larger than their collateral or their reputation. So if there's a massive block that comes in, 10,000 ETH block, and they only operate one validator with 32 ETH, they're happy to say, okay, the pool, you can keep the 32 ETH as my collateral, but I'm going to run away. I'm going to rug pool with the 10,000 ETH. And so even if you like the concept of pools, like Rocket Pool or Lido, MEV burn actually makes these pools better because it removes the rug pooling. And then the fourth economic distortion that I want to highlight is this idea of drought. So there's two use cases for ETH, right? There's the staking, which is economic security, and then there's this other very important use case, which is economic bandwidth. So, for example, we're going to need decentralized stablecoins that are backed by pristine collateral, by ETH. And if we're in a bull market, let's say, where MEV is just gone crazy, then what's going to happen is that the incentive to become a staker are going to grow, and all the ETH is going to be sucked into staking, and then that's going to dry up the ETH for the economic bandwidth, and is basically going to fight the Ethereum economy. So in a way, the chain is kind of too successful, and it's overpaying for security, and that leads to less economic bandwidth for the rest of the ecosystem. And then another thing that's not on this slide, but I just kind of remembered, is that if you're giving the MEV to the proposers, you're kind of incentivizing people to use derivatives as collateral. And my personal belief is that ETH derivatives are risky to use as collateral because they can lose all their value from one day to another through slashing. And so they're not high-grade collateral, and ideally they should be avoided if you're building things like decentralized stablecoins. And then in terms of the good things, if you give the MEV to the holder, you have basically more scarcity. You increase the Schelling point that ETH is money for the internet, and that Ethereum is the settlement layer for the internet of value. But ironically, you're also increasing the rewards for stakers, even though you're removing the MEV portion. And the reason is that the rewards are going to tend to the cost of value in either case. But for most people, because of this variance around the rewards, most people are going to be earning less than the cost of value. So actually, most people are going to be losing money staking, and a few people are going to be making money staking. So that makes everyone earn kind of the same rewards. And also, from a USD denominated perspective, presumably if there's more scarcity, the price of ETH is worth more, and so you actually have more USD denominated rewards, even though the ETH denominated rewards are the same. You also have more economic efficiency in the sense that you don't need as much issuance to pay for economic security. And the reason is that the amount of issuance grows with the total amount of stakers, and so we can reduce the amount of stakers and therefore have less issuance and still have enough economic security for Ethereum. And then the final thing is that this is kind of related to the scarcity. Even though the total amount of ETH staked will go down, it's possible that counterintuitively you'll have more economic security. And the reason is that, again, the price of ETH might be worth more, and so from a USD denominated standpoint, you might have more economic security. So all of this to justify this new precedence list that I think we should be targeting for when we redirect MEV to various participants. And now on to Barnaby, I believe.
Thank you, Justin. Hi, everyone. I want to talk a bit about protocol credibility and principal agent problems. I'm told that there's an echo, maybe. Okay, so can you move on to the next slide, please? In October, I released a post on unbundling PBS with something I called Pepsi, Protocol Enforced Proposer Commitments. It allows the proposer to basically commit to any kind of executable contract, and the commitment is fully defended by the protocol in the sense that block validity depends on the satisfaction of the proposer commitment. In particular, you can write PBS in Pepsi, but you can also do much more than that. So it's much more general. And Pepsi came from a feeling that I was somewhat unsatisfied, let's say. I thought we don't really have a theory of protocol upgrades, and so we might as well give ourselves as much optionality as we can. And Pepsi is really maximum optionality in terms of what the proposer can commit to. That's not to say that we shouldn't do protocol upgrades. I think we have a good intuition for them. We've done them in the past and they worked pretty successfully. And there's something to be said for being iterative, community-driven, this kind of diffuse, pragmatic approach to protocol development. But the arc of Ethereum is the arc of any complexifying economy. So processes get more sophisticated. You have a division of labor that we call modularization in blockchain slang. If you can move on to the next slide, Justin. And so this division of labor, it fractures basically trust domains. More and more things get delegated. You have delegation, and if you have delegation, you have principal agent problems, these PAPs. And if you have principal agent problems, you have potentially misaligned incentives. And so we can always choose to protocolize systemic PAPs, principal agent problems, but then we have to define what the system is. And in this conversation, I think we're often led to ask what is the role of the protocol in that larger system of protocol and infrastructure. And I don't think we can have this conversation properly without having a bit more theoretical background on basically protocol credibility. And so the discussion on credibility is really taking off at the moment along with commitments. To me, the groundbreaking work is Virgil's. Ethereum is game-changing technology, literally. But recently, Shin from Flashbot has revived this conversation. He has a much more holistic theory of credibility and commitments. And I think in parallel, very much in the zeitgeist, you're starting to see much more results on credibility in auctions and credibility in mechanism design, where you don't have, let's say, a central controller. And so what this conversation tells me is that there is this hierarchy of commitments, and the reason why we want to put things in protocol is because we see that as being more credible. And so I want to just go a bit into why we might think that. And basically, it's because the protocol gives us a shelling fence. The validator set says anything we put behind the fence, anything we put in the protocol is going to be defended with the whole might of the validator set. But the protocol can only defend what it sees. So most of the upgrades that we do, they're really done with the aim of extending the vision of the protocol. And I call it seeing like a protocol. We want to make legible certain outcomes and certain pieces of infrastructure so that the protocol can control and defend them. And so the aim is to get a credible signal. For instance, if we see a safety fault in the FFG gadget, if we have a base fee, these are all credible signals of things that are happening in the protocol. Next slide, please. And so this protocol credibility to me is the sum of two things. It's this first protocol introspection and also protocol agency. So the more introspection we have, the more control and the more we can have actionable responses to events that are happening. So sometimes we don't want to go through the diffuse process of community government if there's a fault that we can't control. For instance, people are driving base fee to 0. It's not something that the protocol can see as a fault, and we need to act as a community to defend against that. But there are faults that we can deal with pretty much automatically, like slashing people who are finalizing and doing safety faults. But the trade-off here is that when we build in this protocol credibility, when we extend the boundary of a protocol, it means that we also need to become opinionated about outcomes that we want. And so there is a higher risk that we lock in kind of local optima or mechanisms that are suboptimal. But more importantly, when we do that, we also start overloading the validator set with the duty to defend more and more things. And we can do so, but then we must be convinced that we as a community are going to defend these mechanisms basically with the protocol's life for whatever falls under its zone of controls. For instance, we commit to forking out validators who subvert the censorship resistance gadgets that we build in, the MEV burning, the finality gadgets, all of these gadgets. And to me, this feels like it gets harder as time goes on, because there are other domains like Suave or like EigenLayer that may directly shift the incentives of the validators, such that honest behavior and rational behavior start differing more and more, especially when the protocol has locked in suboptimal outcome. And by suboptimal, I mean non-welfare maximizing, because when this is the case, the welfare gap is basically a subsidy for bribing validators into doing the wrong thing. And so back to Pepsi, to me, the idea was nice because it creates this idea of programmable protocol credibility, but it may be at odds with the goals of zeroing in on a minimal set of gadgets that we are willing to defend with basically the protocol's life. And that question is still open in my mind. So yeah, I think we're getting closer to this theory of protocol upgrade. I think commitments, credibility, both have to do with that, and I'm excited to see what's next. I think we're a bit over time, but we should jump to the questions.
Awesome. Great presentations, guys. So we will have a brief kind of question section here before we move on to the next one. The first one I'll go with will be kind of basically getting Davide and Barnabe, your reactions a bit on kind of the MEV allocation and distribution type of convo for the most part. I know, Davide, like you've written previously as far as MEV allocation, the goal is basically distribute the captured MEV to participants in a way that is most beneficial to the protocol. So that last part is really kind of what hones in on the question of how do we define what is that objective function of what is beneficial to the protocol that we're trying to optimize here, whether that be MEV smoothing, MEV burning, in particular because MEV smoothing does address some of those points that Justin had spoken about as far as the reorg resistance and some of that kind of stuff. So like how you guys kind of think about what you're optimizing for here.
Yeah, good question. So I think the answer is nuance, and it ties to like parts of the presentation of Justin and Barnabe as well. So maybe I'll start and then they can continue. So like in the ideal world, like what does most beneficial for the protocol means? I mean, the protocol is just like organizing all the participants, like users and like service providers, validators in this case, right? So like on the user side, like the ideal allocation is essentially like a fair tax. So essentially like the MEV you contribute to the system and the MEV you get allocated, like if you subtract those, they should be proportional to the externality that you bring to the system, right? On the other side, you also need to use like part of this MEV to make sure that like the validator incentives are not distorted, behaving honestly. So I think this ties to like the kind of precedence hierarchy that Justin was talking about. Yeah, so I'm not sure if he wants to comment next, also because it doesn't need, the allocation doesn't need to be monetary, could be purely fiscal, but it could also be monetary in the case of burn.
Sorry, what do you mean by fiscal?
In the sense, it's a you could organize direct transfers, right? For example, in the type of allocation that an OFA system would do, there is a direct transfer back to the user. So essentially, the user is getting that MEV directly, not through inflation or deflation in this case. Yeah.
Right. I mean, there's a separation of the consensus layer and the execution layer, right? And like, I guess what you're saying is that the execution layer is the fiscal layer. And I mean, I don't think users would would get issuance, right? That's kind of the wrong layer because issuance is at the consensus layer, right? Okay. Yeah, I mean, John, you made a good point around smoothing, potentially solving some of these issues. Smoothing doesn't solve the economic bandwidth drought, basically, just the staking sucking egg. Yeah, and it's also unclear in terms of the reorgs, even the reorgs. Like, one of the ideas is that we have some sort of a small committee that's in charge of the smoothing, but this small committee is maybe not representative of the whole validator set. Or maybe it is, I don't know. But there's some nuance there a little bit.
Yeah, on that point, if I can comment, I think sometimes we also get the monetary policy that we can defend. And if we can't defend things like MEV burn or things like MEV smoothing, because they rely at the end of the day on this honest majority of committee to defend these things, yeah, it might be something that we can't get. But I wanted to also mention some research that is done by Anders in our group on the dynamic yield curve, and notably the idea of capping the size of a validator set and potentially even auctioning off the slots of a validator set. That's, I would say, another way of internalizing that MEV allocation in the protocol. And in particular, if you get rewards from like EigenLayer as a validator, you're going to be willing to pay more at this auction. And so you can even internalize more than the execution layer MEV via this mechanism.
Or you could do both. I think that would be the ideal.
Right.
I mean, one of the things that you mentioned is that MEV burn or smoothing requires an honest majority. I do want to highlight that EIP 1559 also requires an honest majority. And just for people to understand this, basically, if you have a dishonest majority, they control the fork choice rule, and then what they can do is that they can fork any block that increases the base fee, and so basically the base fee is like decreasing only, and it goes to 0, and then you've just essentially deactivated the EIP 1559. And actually, there's a lot of parallels between EIP 1559 and MEV burn. It's just essentially the same mechanisms, the same dynamics, is just on a different side of the coin.
Very good. So moving on to one of the other questions that we had. This one will be for you, Justin. It relates to several of the earlier presentations that referenced it, but your recent post on base rollups, where the basic idea is letting the layer one kind of do the sequencing for these rollups potentially. And TLDR, the very simple MEV implication here is, if you implement it in that simple form, basically the MEV that would normally accrue to rollup sequencers would start going to the L1 itself. So the question here is kind of, why is that such a desirable or undesirable feature of this? And then in particular, is there kind of a tension here between now all the value goes to Ethereum and maybe this is kind of the dominant solution to them, and compared to rollups should have their own incentives to continue to innovate and continue to grow over time? Is that kind of in any way a rejection of like the rollup centric roadmap, where we want this private market of people to be incentivized to go make these things?
Right. I mean, on the topic of incentivization, I'm not at all worried about the rollup teams. Right. There's like $10 billion plus kind of market caps. I think they're doing very, very well, and for good reason, because they're doing something very, very complicated that requires very big teams. It requires taking a lot of risk. And also the fact that we have these tokens is kind of fuel to kind of almost disrupt a little bit the layer one network effects and create new network effects at layer two. So I'm all for like this this capitalism as it were at the rollup layer. But I think what will happen is that what is capitalism in the short and medium term might become commoditized eventually. It will be just like running water and electricity. And there will be less and less of a need for incentivization. I mean, even the rollup teams themselves, right? They want to be credibly neutral. They want to be maximally decentralized, and so they go, for example, from centralized sequencer to decentralized sequencer. They go from governance, token governance for upgrades, and then they might remove the governance and become like Uniswap, fully trustless. And I think the move from being layer 2 sequence to being layer 1 sequence is part of this natural progression of progressive decentralization. And then once you've reached the base rollup, the ultimate maybe goal is to become an enshrined rollup. I'm talking to the Scroll founders, and that's one of the things that they're thinking about, like how could Scroll become an enshrined rollup? So there's kind of this spectrum of rollups. And by the way, my definition of a rollup is, when there is sufficient data on chain that you can recompute the state. And so, some of the rollups that people don't talk about is centralized rollups. So for example, Optimism today is a centralized rollup. It's a rollup because you can recompute the states, but it's centralized. And I think another type of rollup that people are not looking into, but I'm relatively optimistic about, is SGX rollups, where the security engine is SGX. But I think that what we're doing is we're progressively fleshing out this whole design space of rollups with rediscovering enshrined base, blah blah blah. In terms of the advantages, I think they really do lean highly towards credible neutrality, right? So it's like maximum security, maximum liveness, maximum decentralization, maximum simplicity, and so all of these things are tending towards the mature side of the rollup. So what I expect will happen is that the dominant rollups in the short and medium term will be the non-based ones, and then eventually maybe a based one. And actually, one of the ideas that we've been thinking within the ultrasound team is, like, should we launch an ultrasound rollup? And if we were to do such a thing, it necessarily must be a base rollup, because that's kind of like the natural selling point. Now, one of the things that I think will happen with rollups is that it's kind of winner take most because of the network effects. And so rollups need to be very strategic. Right. On the one hand, they need to have they need to move extremely fast, have the first mover advantage, have a lot of token fuel to do the boosting. But at the same time, they need to have this credible story that eventually they'll become maximally credibly neutral. And I think becoming a base rollup as one of the line items in their roadmap could be a very powerful strategic move for them. And one of the things that was highlighted about base rollups is that it's a little unclear how you get some of the services like pre-confirmations. But I'm actually relatively optimistic that with things like EigenLayer that we can actually have fast pre-confirmation. So we can have our cake and eat it too, have like all the advantages of non-base rollups and all the advantages of base rollups. So yeah, the future is bright for rollups for sure.
A lot of different options. I think we'll squeeze in one more since we started this a few minutes late. This one kind of gets to the question of what is really the protocol's job to kind of provide to everyone who's kind of using this ecosystem. So it's a question that I had actually asked Phil earlier as well. So curious to hear your guys' take. It's regarding enshrined PBS. And is this something that we actually need to do? Is this something that actually needs to be enshrined in the protocol at any point? It's clearly not a near-term action item that's happening imminently, but there is that real risk of you enshrine something, a very specific structure, and crypto has a strong tendency of finding new existential risks every couple of years, and you might find a new one of those a couple of years later and realize you wanted more flexibility. So what are the downsides if we were not to do that? And kind of how do you think about that? Starting with Barnabé on this one.
Sure. Yeah, I thought Phil's answer was quite interesting to say that basically our job is to do research on providing nuclear options, or almost like deterrence for people to not do bad things and for the market to stay clear. I'm pretty hopeful about, let's say, the development of PBS. Justin can probably talk more about this, but lately there's been like a lot of innovation, like optimistic relaying towards this roadmap to PBS. So to me, the risk was not to say that, okay, PBS is a bad idea. Clearly, I think you want this clean interface for the protocol to communicate with what's outside of it. And I think PBS is probably part of the right one. But I did want to see more data, more experimentation, more research. And it feels like we're at this point where, okay, every day there's like a new paper, not necessarily about PBS, but that can be applied to PBS, or new data sets, new findings. And yeah, that makes me fairly confident about figuring out that nuclear option, like the shape of it, before we actually need to use it.
Yeah, I mean, my take is that with enshrined PBS is going to take a long time, relative to how fast the blockchain space moves. It will take, let's say, 2-3 years at the minimum, and in 2-3 years, the MEV space is just going to dramatically change. Like every week, the MEV space dramatically changes. We're just speed running the whole thing, and I'm hopeful that we'll have some sort of reasonable equilibrium in, let's say, 1.5 years or 2 years. And then that will be, close to the end game of, the non-enshrined PBS, and then we'll be able to make an informed decision as to whether or not we really want enshrined PBS. But intuitively, as a roll-up operator, as a relay operator, I'd say we really do want enshrined PBS. Like being a relay operator is not good. Like on the one hand, it's kind of a lot of work. And there's a lot of pitfalls, but one of the things that I've been thinking about is, okay, how can the role of the relay be abused? Like, what happens if someone hacks our relay? And I believe that if someone hacks our relay, they can steal millions of dollars. So basically, it's a high kind of trust environment. You could collude with the builders, you could collude with the validators. There's all sorts of attacks, many of which are not documented. And really, you just want to remove this trusted entity as quickly as possible. But yeah, it is possible that there's some very, very clever technique that allows us to remove the trusted entity without enshrined PBS. And I think Flashbots, for example, is working on using SGX, to remove the relay. And I think, as Van Abe mentioned, there's this whole roadmap that we have now that's, been written by Mike Nuder, basically documenting, a progression for optimistic relaying, which incrementally brings us towards enshrined PBS. And I encourage you to read it, because it kind of shows you almost how natural the enshrined PBS should be in a few years.
Awesome. This was a lot of fun. I don't want to keep Patrick waiting any longer. So thank you again, all of you guys. This one was really, really great. And we will now transition on to the next talk. We're going to have Pat McCory coming on, and he's going to be talking about a closer look at the sequencer's role in MEV.
Everyone, so I was trying to unmute myself. I was enjoying that, by the way. I was happy to be delayed. That was great. Okay, I'll just get started then. So today what I'm going to talk about is layers of layers of layers, hopefully taking inspiration from layer 1 and applying it to layer 2. And what we're mostly going to look at is the sequencer and how we can think about MEV around the sequencer. So as we know, just a bit of background in MEV land, there's typically 3 agents that we care about. One is the honest user. All the honest user wants to do is buy and sell their mooncat. We have a proposer, and the proposer's job is to take a list of pending transactions and decide the final ordering of those transactions. And third, we have the searcher. Those MEV bots, those people living in their bedrooms where they're looking for these MEV opportunities, they bundle it up, and then they pay the proposer to include this bundle in the list of transactions, in the order list of transactions. So that's MEV land in a nutshell. So let's begin with Ethereum mainnet. And let's look at the life cycle of a transaction, and let's see what we can extract from this scenario. So we have a user, Alice, again, who wants to buy and sell mooncats, and we have the proposers. So the question is, how does the user get their transaction and communicate it to the proposer? So we have to consider the communication channel. By default, we will use a gossip protocol or the peer-to-peer network. Alice will send a transaction to a peer, they'll take the transaction and pass it on to their peers. And eventually, within 1 to 2 seconds, every peer in the network will get a copy of this transaction, including their proposer. They'll take this transaction and hopefully include it in their block. Now, the issue is that it's a peer-to-peer network, so anyone could be on it, including a searcher. So they could listen out for the user's transaction, inspect it, find an MEV opportunity, and then front run the user and steal the profit. So it's a bit like a dark forest in a way. And there could be, not just one searcher, but many searchers that are all competing for exactly the same, MEV opportunity, the same profit. And this leads to something called priority gas auctions, which I'm sure people have spoken about already, where the searchers will bid each other up, transaction fee 1, 2, 3, 4, 5, 6. And it's up to the proposer to pick the transaction with the largest fee that pays them the most money and decide who wins the auction. Now, I stole this from a blog post by totlasoda.eth. I probably didn't butcher that name a little bit. But you can see here in the graph, within a 10-second period, there's basically like hundreds of transactions being sent. Then eventually Mr. Blue wins, and he wins the auction and gets the MEV opportunity. Now, there's two problems with this approach. One, it's wasteful of gas. You have one transaction that's successful, followed by a list of failed transactions. And that's a waste of block space. And two, it's unrestricted MEV. You're taking the user's transaction, throwing it to the wolves, and just hoping it gets to the other side okay, because it's completely unrestricted what these bots can do. So a few years ago, a wonderful company called Flashbot, I wonder who they are, they came along and tried to solve the problem for Ethereum. We give the transaction directly to the Flashbots, and they'll give it directly on to the block proposer. So then the MEV bots, or the searchers, they can't find the opportunity, and they can't, extract value from the user's transaction. So stepping back a bit, what can we extract from this scenario? One, we have to consider the proposer's ordering policy. In this case, they're picking the transactions based on the fee. Highest fee first, lowest fee at the bottom. And they have around 12 seconds to do this, as we saw with the priority gas auction. What we need to consider as well is the communication channel. How does the block proposer learn about the transaction, and how do the searchers find it as well? And finally, sometimes we forget about the poor little user, but we have to think about the user experience. How long does it take for a user to be informed that their transaction is confirmed and how it was executed? Because at the end of the day, they want to execute and participate on this network. So that's Ethereum, Ethereum mainnet in a nutshell. We took some cool ideas from that. So now let's move on to layer 2 and rollup land. And in rollup land, there's typically three actors: the honest user, the sequencer, and the executor. Now, for once, we're not going to talk about the executor. They have very little to do with MEV. We care about the sequencer, who's basically the proposer and gets to decide those lists of transactions and their ordering. They have everything to do with MEV. And the life cycle is pretty similar. Alice gives their transaction to the sequencer. The sequencer will have a list of pending transactions. They'll run some ordering policy. They'll decide the ordering of the transactions. Then they'll post that onto Ethereum, into an inbox, and then picked up by the bridge. Now, in this scenario, we have this direct communication channel. There's no gossip protocol. Alice can communicate directly with the sequencer. And what we need to be concerned about is, when does Alice get a response from the sequencer, and what type of response do they get? And that's really going to depend on how the sequencer decides the order of these transactions. Then, of course, what we care about is the sequencer's ordering policy. They can keep the transactions private for as long as they want, decide the ordering, and then eventually make that public once they've made their decision. So what ordering policies could the sequencer implement? So we're going to go through three. The first is highest extraction first. The second is highest fee first. And the third is first come, first serve. So let's just dive right in and see what we come up with. Highest extraction first. And basically, when you talk about sequencers and MEV and layer 2, this is the first ordering policy that everyone talks about. And the reason is the sequencer has ample time to extract value. They could wait, a minute or hours before they have to publish that transaction publicly. So in practice, both Arbitrum and Optimism, they typically publish these transactions in about 20 or 30 seconds. But according to the smart contracts, Arbitrum can hold it up to something like 24 hours. And the Optimism, I couldn't actually find the value. Someone could probably drop it in the chat. But I'm pretty sure it's like 24 hours they could keep these transactions private for. So if you can hold a transaction, pending transactions for 3 hours, let's say, well, you have this big basket of transactions. You have your MEV extraction algorithm. You run it on the batch. And then you can order your transactions according to, the ones that you can extract the most value from. Now, in terms of user experience, there is a benefit to this. We can have a Robin Hood style experience. The user could transact for free because later on their transactions used to compute some MEV reward. So from the user's perspective, it's a free transaction, but they're really paying for it through MEV. Now, the issue with this approach is really the long delay. If we allow the sequencer to extract value for 2 to 3 hours, well, that sucks for the user. Think of Bitcoin. You have to wait 10, 20 minutes on Bitcoin and everyone hits that. It's a terrible user experience. So imagine waiting 2 hours just so someone can go extract value from your transaction. It's not a great user experience. Now, you could solve this problem. A lot of people think, okay, sequencers can extract MEV. Let's solve this and stop that from happening. So they can implement some fair ordering protocol. Maybe the sequencer can't see the transaction content. Maybe you introduce a consensus protocol. What does fair mean in this context? I don't really care. It's not important for this talk. I think Tarun's going to talk about it later. It's going to be pretty spicy. But for now, I'm going to argue differently. I'm going to argue we don't need to solve the problem, because if you look at proof-of-stake Ethereum today, you have this open market of searchers, PBS, and you have the stakers who are basically competing in a lottery. The searchers do all the hard work. They extract the MEV. They pay a bribe to the proposer. The proposer gets a transaction fee, and then they include the bundle. And so there's a very good chance that a sequencer can make more money by having an open market of searchers do the hard work, as opposed to trying to extract the MEV themselves. And if that's the case, then their financial incentive is not to extract the value, but allow someone else to do it. So we don't have to worry about the fair ordering problem for now. And if that's the case, well, that means the sequencer's ordering policy is the order transactions by transaction fee. Whoever pays the highest fee will get ordered first in the list. And so, this is basically payment for order flow. Maybe some MEV people hate me for saying that, but it's basically that anyway. The sequencer will get the list of pending transactions and give it to the searchers. The searchers can crunch and crunch and crunch, extract as much MEV as they want, and then eventually send a bundle to the sequencer with a payment. And they'll say, sequencer, if you include my bundle, you'll make this amount of money. Then the sequencer takes that bundle, they take the payment, and of course they order it according to the payments they receive. Very much similar to what happens on Ethereum today. You're sharing the MEV between the sequencer and the searchers. And again, the user experience is not very different to the previous case. Users could still have free transactions, because the transaction fee is actually the MEV that's extracted. But again, this could have a long delay. Users don't want to, and at least I don't want to build a layer 2 where users are waiting for 2 to 3 hours for their transaction to be confirmed. So this is why most rollups implement first come, first serve, because they want to prioritize the user experience. What do I mean by this? Well, the user will send their transaction to the sequencer will timestamp this, and then simply order the transactions according to the timestamp. And this has a wonderful user experience. It's a bit like transacting on Coinbase. You send your transaction to the service provider, and they return back a response to say, it's confirmed. This is how it's executed, under a second. And typically when people talk about first come, first serve, they say, oh, well, there's no MEV here, hiding under the covers. Well, of course there's MEV. There's MEV everywhere. You'll never get rid of MEV. So anyway, how do we have MEV? So what happens in practice, at least with Arbitrum, and I assume it's the same for Optimism, when a user gives their transaction to the sequencer will create a little block within 250 milliseconds and then publish that off in a feed. Now, the reason to have a sequencer feed is because external service providers like Etherscan, Coinbase, or Infura, they could pick up the block and present it to the user. So a user could send the transaction to the sequencer, then look at Etherscan and say, oh, my transaction was confirmed according to Etherscan. Now, what happens when you have a data feed that's releasing data about transactions in real time? Searchers connect to it. They listen for the transaction. If there's an MEV opportunity, they'll backrun it and send it immediately to the sequencer. And this leads to the rise of latency games. Because you don't end up with one searcher, you end up with 150,000 WebSocket connections. Because whoever gets the data first, whoever gets that transaction data first, is the one who wins the MEV opportunity and can backrun the user. And this is in theory. This happened in the Arbitrum, and I guess it's probably still happening. I don't know. They had this post where they had 100,000 to 150,000 connections because the MEV bots are competing on a latency game to extract MEV, or at least backrun transactions. The short-term solution proposed was to implement hashcash. So you create 50 dedicated connections. The searchers do proof of work. Whoever has the lowest nonce wins one of those connections. And so then, the searcher's game is to do proof of work as opposed to creating thousands and thousands of WebSocket connections. Now, that is a solution, but I think there's a more interesting solution that comes out of this, and sort of motivated by Ed Felton's proposal, which we'll talk about in a second. What if you could combine first come, first serve with the hash-v first? What do I mean by this? So basically, similar to before, the user gives their transaction to the sequencer. The sequencer may collect 1 or 2 transactions and then pass it on to the searchers. The searchers will take this small bundle, extract as much MEV as they can, participate in an auction, and then submit their bundle with a payment to the sequencer. The sequencer will take whatever bundle pays the most money and then confirm that. Now, the point here is that this bundle auction is configurable. The auction window could be really short. It could be 500 milliseconds, 2 milliseconds, 5 seconds, whatever. A really short period of time. And the sequencer can constrain the MEV. The sequencer could say, oh, I'll only let you front-run transactions, or back-run transactions, or sandwich transactions, or all of the above. So what's cool about this is, one, if we have these short, rapid auctions, then we can have fast confirmation for users' transactions. I submit my transaction, within 3 seconds, I'm told that it's confirmed. I may have got front-run or back-run runs, sure, but my transaction was confirmed. 2, you have this open market for searchers. Admittedly, it's smaller bundles that they're working with, so you are constraining, what extraction they can do. But again, you still have this open market where they can probably find the best extraction. And finally, it's configurable. The sequencer can decide what MEV is allowed, as opposed to having this crazy dark forest that's really unconstrained. Now, this is sort of the idea coming out of, I don't want to say sort of, it's basically the idea coming out of Ed Felton's post about time boost. Here, I basically described it as having a queue where you can immediately front run or back run, or of course, sandwich. In this proposal, you could convince the sequencer, with a payment to say, well, here's a transaction ordered 500 milliseconds in the past. And then you could, depending on the timestamps of the transactions, you could front run or back run. So you're paying for time as opposed to a position in the queue. But my main point is, this is a really cool research question, a really cool open problem. And it's sure to get the best of both worlds. Fast confirmations, but still having this open market for searchers. And so I guess that's my last slide. I guess I'm just within time. But I just wanted to present this idea because I've been thinking about it a lot. And I think it's a really cool idea. So yeah. GG. Or GM, I guess, GM.
Awesome. Thank you so much. It was a great talk. We will now be moving on to our next one. We're going to have John Adler come on, and he's going to be talking about MEVconomics for modular blockchain stacks.
Hi, can you guys hear me?
Yep, we got you. You're good to go.
Awesome. Okay, so let's get started. So today, I guess I'll be talking about MEVconomics for modular blockchain stacks. And I'm going to start with what appears to be blockchain 101, but if you bear with me, it'll become obvious why we kind of build intuitions by construction starting from the beginning. So what are some components of any blockchain protocol, not just a modular blockchain? One, it has a leader selection algorithm, and these are some of these things you'll have heard of them from previous talks, especially the ones that we're going to deep dive in today. So this is basically an algorithm that tells you who is permitted to actually produce new blocks. Because a blockchain that can't have new blocks added to it isn't particularly useful. Then tying into this, you need a Sybil resistance mechanism. In any kind of decentralized blockchain, you need some decentralized permissionless blockchain. You need some mechanism to prevent someone from just spamming a bunch of potential candidate leaders, and that's going to be the Sybil resistance mechanism. So things like proof of work, proof of stake, etc. Then you have a block validity function or a state transition function. effectively the rules around the validity of the execution of a block independently of who got to produce it. And then finally, to wrap all of these up together, you have a fork choice rule, which allows you, well, by you I mean the nodes, to distinguish between two otherwise valid chains. So two chains that have the correct leader, that has sufficient Sybil resistance, like amounts, whatever you want to call it, and the blocks are all valid. You need some way of distinguishing between these two otherwise completely valid chains. Okay, and we're going to focus primarily on the first and the fourth one of these, because things like block validity, yes, the specifics of the block validity function determine what MEV may be extractable. For instance, Bitcoin may have less extractable MEV than, for instance, a Turing complete blockchain like Ethereum, but given that just a few days ago we saw a reorg on Bitcoin because of an NFT mint, maybe that's not actually the case anymore. But leader selection and the fork choice rule are definitely things that come into play with MEV. So this is the only slide that will contain theorems and corollaries. So please bear with me. But the first theorem is that in any decentralized blockchain, it's required that the leader cannot halt the chain on their own. Statistically, of course, if we're talking about proof of work, if one person gets really, really lucky, they can just produce every block forever, or censor the whole chain, etc. Why do we want this to be the case? Well, because if one party acting alone can completely and permanently halt the chain, then they effectively have the ability to destroy it, and if they can destroy it, then it's isomorphic to having control over it, as a quote from Dune would say. Now, a corollary to this is that if you're given if an actor is given access to sufficient of like the Sybil resistance mechanism amount, they should be able to become a leader for at least one block in some finite time, again statistically. And as long as this is true, then the system is permissionless. So decentralized permissionless it's all very good. The general way this is done is, there's leaderless protocols like Avalanche, but here we're not going into too many specifics. The general way this is done is that if the assigned leader doesn't act within some finite time bound, then another entity becomes a leader. Okay, so why is this important? The reason it's important is that the leader can capture MEV, either directly or indirectly, through things like arbitrage, front running, sandwich attacks, etc. Now, generally, it's hard to manipulate who is going to be the leader because the leader is tied to a Sybil resistance mechanism. For instance, proof of work. You can't just show up and say, "Hey, I'm the leader." You kind of have to do a whole bunch of work. Similarly, in proof of stake, various proof of stake protocols like Tendermint or Gaspro or whatever have pre-assigned leaders. You can't really manipulate the leader in any meaningful or cheap way. But there's other things you can manipulate, which is going to be the fork choice rule, which works in tandem with the leader selection algorithm. And it could be easier to manipulate the fork choice rule than it is to manipulate the leader selection algorithm. And manipulation of this could lead to things like time-banded attacks, etc. And of course, once you've reordered the chain, then you're also the leader of those blocks. So then you can also engage in front running, etc., within a single block or a sequence of blocks. Now, these may not be that much of an issue in an L1 context, but we'll soon see why there's such a concern and why they're so much more flexible in a modular context. So, what is the modular world? We're moving towards a multi-chain and specifically modular world where you have shared data layers that provide a very high amount of data bandwidth, such as Celestia or ETH2, I guess Ethereum nowadays. And then a number of execution layers or rollups, sovereign rollups, element rollups, whatever you want to call them, things like Eclipse, Arbitrum, ZK Sync, Optimism, Starkware, Scroll, Astria, just to name a few. There's countless of these already in development, many already deployed, etc. Now, in this multi-chain world, or rather, if we're really being general, this multi-domain world, a lot of the current concern is around cross-domain or horizontal, as I like to call it, MEV, where you have MEV that comes from arbitrage and other opportunities within two different execution layers, within two different rollups, or just any domains, really. And this is obviously, a very important problem, etc., but it's not going to be the topic of today's talk, or lightning talk, I guess. It's 15 minutes. We're going to be talking about and exploring what I would call vertical MEV in the modular blockchain stack, which is the MEV relationship between the rollup and the data layer. And this could, of course, extend to multiple rollups on top of the rollup, et cetera, et cetera. But this is like a vertical relationship instead of a horizontal relationship. And now you might be looking at this and saying, well, there shouldn't be any relationship between these two because, there's two execution layers. Trades are being done on one that might create arbitrage opportunities on the other. You can atomically execute transactions on each, et cetera, et cetera. But if you have an execution layer and a data layer, the data layer itself doesn't have any arbitrage opportunities because it doesn't execute anything. So like why would there be a relationship between these two? And this is why this is an interesting problem, because it's not cross-domain MEV in the same way that this horizontal MEV is. It's very different. And for this, we're going to keep in the back of our minds the tongue-in-cheek first law of cryptodynamics that MEV cannot be added or removed. It can only be moved from one layer to another. Or put another way, MEV can't be destroyed. It can only be changed moved around from one layer to another. This is, of course, not actually like a formal law. It's just a tongue-in-cheek observation when dealing with vertical MEV specifically, not cross-domain MEV. So when it comes to building a execution layer, building a rollup on top of a data layer, you need to have some mechanism, just like in any blockchain, to produce new blocks. You need a leader selection algorithm, right? But you would also like to leverage the data layer for security, because if you don't leverage it for security, then you're kind of losing half of what you get out of the modular blockchain, right? You can get the ordering and you also get availability. It'd be nice if you can use the blockchain also for ordering, because if you only use it for availability, now you have like these synchronization issues between one blockchain's consensus and another blockchain's consensus. You would like ultimately all consensus to be done ultimately only on the base data layer, and have everything else use some mechanism of merge consensus instead of their own completely independent consensus protocols. Because then if they use a completely independent consensus protocol, you'd have synchronization issues. So what do you want out of a leader selection algorithm for one of these rollups on top of the data layer? Well, you would like to decentralize the sequencers. If you just have one sequencer, the censorship concerns, there's potential for MEV monopoly and MEV extraction, regulatory concerns, etc. Also, decentralizing sequencers is a very convenient and easy way to introduce a token, right? Just have a token, some stake-weighted mechanism, round robin, leader selection, just like Tendermint has. It's a great way of introducing that. What else you want? You want strong liveness guarantees. You don't want it so that a single sequencer going down, for instance, means that the rollup goes down forever. You'd also like to minimize trust assumptions here. You don't want to trust that a single party is operating, or a small number of parties are operating correctly for the chain to operate correctly. And also you want to minimize waste of the data layer's block space. And waste can happen if there's some sort of contention, etc., where two transactions show up and one of them becomes useless and it just wastes the data layer's block space. You like to avoid that. What you don't want, though, is you don't want the MEV to bleed down to the data layer. And I gave a talk at, I think, some MEV Summit back a while ago, quite a few months ago. It's linked in the last slide of this. If you have access to the slides, it's the YouTube link on the last slide here. That kind of dives deeper into this. So I won't dive too deep, but the intuition is that depending on the leader selection algorithm, you can have MEV bleeding down to the base layer. And why do you not want that? Because now you have a situation where if you have a bunch of MEV bleeding down to the data layer, you have all of this MEV to be captured that instead of being isolated to the individual rollups is all going down to the data layer. And all that MEV to be extracted means there's some centralization pressure on the validators of the data layer to actually extract that MEV. And we would prefer that the MEV be isolated as much as possible to the individual execution layers that create that MEV. Now, there's a problem here, and this is somewhat of a, I don't want to say open research problem, but rather still an open challenge that we would definitely, if you're an MEV researcher or et cetera, if you're interested in modular blockchains, please absolutely reach out to us so we can, brainstorm on this problem. One thing we can't guarantee is that rollups don't necessarily care and aren't necessarily incentive aligned with the best interests of the data layer. They have their own interests, their own economic interest, etc. And they may just do something bad for the data layer. We can't exactly guarantee that they won't do that. Okay, so let's maybe go over a few examples of potential leader selection algorithms / fork choice rules that you could have for one of these rollups on top of a data layer. One of them is first come, first serve. So the intuition here is basically a bunch of people just post blobs that have a particular namespace or that have a that say this blob is for this particular rollup. Basically, that's what I mean by namespace. A bunch of people who post blobs completely permissionlessly. The first person who posts the blob to the Celestia block for that namespace is the one that is selected to be the leader ex post facto. What are some issues here? It means that the leader is ultimately decided by an auction on the base layer. And auctions, as we know, in the blockchain context, well, you either have to trust the auctioneer, or if the auctioneer is permissionless, then auctions can be manipulated. But I guess auctions can be manipulated in either case. It's just a trust assumption rather than a permissionless assumption. Auctions can be manipulated, so that's not great. So this has the issue that it introduces PGA for who gets to be the leader, and therefore bleeds the MEV that comes from the auction down to the data layer. On top of that, it also wastes a bunch of space, block space, because all these other transactions that aren't the first still go on chain. They just don't do anything for the application, so they're useless. Like, they pay fees, yes, but it means now more block space is being used without providing value to end users. Another example, Tendermint style leader rotation. This one is fairly straightforward. It's basically you take just the leader selection protocol of Tendermint, not like the whole quorum and the voting and rounds and all like the P2P stuff, just the leader selection protocol, which is like, I don't know, 20 lines of Go code. It's very straightforward. And then based only on the state within the rollup. So you don't use anything about the ordering in Celestia or anything like that, or the data layer, rather, more generally. You use only the state in the rollup. And the fork choice rule is trivial because, well, Tendermint is fork free. Now, there's issues here, which is that as a safety rather than liveness preferring protocol, this kind of scheme makes it a bit more challenging to have good liveness, because if you use Tendermint on an L1, you can increment rounds very quickly. But if you're in a rollup, potentially you have to wait one or more data layer blocks in order to say, okay, the leader for this slot didn't actually post their block, therefore we will increment them around and rotate the leader permissionlessly. Another one is highest priority first. This was a proposal that was floating around just a few days ago. It would require a protocol change to Celestia or the data layer. It's basically the intuition is introducing a priority field that can be malleated by the block producers, the data layer block producers, and that serves to order the blobs instead of just the fees, for instance, or the position in the block. Now, the issue is that it actually degenerates to being isomorphic to first come, first serve, except the auction, instead of being done on-chain, is done out-of-band and opaquely, which may be even worse. Last example before I close it off is base rollups. Are base rollups based or cringe? So the intuition here is base rollups are based on work that I did, minimal viable merge consensus from 2019, so like basically 4 years ago almost, combined with MEV boost or some PBS thing. And MEV boost is used to prevent waste. Of course, you introduce additional trust assumptions since we know MEV boost isn't completely trustless. So this is maybe a side grade rather than a strict upgrade over the work that I published 4 years ago. Now, sure, you prevent waste, introduce trust assumptions. What are the issues? You still haven't mitigated the use of an auction to select the leader, so MEV still bleeds down. Okay, I was asked by Tina to add a slide on how this ties into MEV economics. someone will have to come after this and tell me specifically and like concretely and completely what MEVconomics is. But I guess this ties into MEV and the economics of MEV bleeding across a vertical blockchain stack. A lot of the work, ideas, thoughts, proposals that I listed here didn't come from me. They actually came from members of the Celestia team and others. I'll list some of them here non-exhaustively. So there's Connor, Rutul, Evan, Callum, and Gabriel. They worked very hard on these kind of things. If you have access to the slides, there's a link to their socials if you click on the bubbles here. So please follow these people on Twitter, GitHub, or whatever. They're very bright, and they're the ones who did a lot of the work on a lot of the ideas and proposals here. And if you want to do further reading, as is tradition in the blockchain space, there's lots of prior art. So I posted a bunch of links here with a variety of proposals, intuitions, counterpoints, etc. Okay, that's about it. Sorry for being like a minute over.
We're running a couple behind, no worries. This is significantly better than we're usually running on these, so we'll take it. Thank you for the talk. So we're going to move on now to James, who's going to be speaking on the MEVconomics of bridging. How's it going? You're on mute.
There we go.
There we go.
Hey, thanks, John. And thanks, other John before that, I guess. Yeah, I'm going to be talking about a specific MEV mitigation within the context of bridging. I think I was required by Tina to put the word MEVconomics in the title of the talk. So what we're really going to be talking about is using the structure of a bridge and partially ordering messages in order to mitigate MEV in the cross-chain context. So I'm James. I've been working on bridging and MEV since late 2017, early 2018. I've been around the block a few times. You can find me on Twitter and GitHub. Generally speaking, when we talk about a bridge, we're talking about two one-way communication channels between blockchains, from chain A to chain B, and a separate system to go back from chain B to chain A. The general pattern that these work in is chain A will dispatch a message. Some off-chain actors will pick up that message and deliver it to chain B. Chain B will do authentication and validation of the message and then deliver it to the application that receives it and handles it. So if you put it on a timeline, it looks a little bit more like this. Each of these steps is atomic on chain or takes a very tiny amount of off-chain time. And then there's these big in computer time gaps between the actions. It sometimes takes tens of seconds for a off-chain actor to pick up a transaction from the blockchain, or they might wait several minutes for it to finalize in the proof of stake consensus. So these gaps between the origination of a message and its handling by the off-chain actors can be minutes. And the gap between the off-chain actors getting the message and its confirmation on the receiving chain can be several minutes as well. As we probably know, MEV is a result of time gaps between committing to what you want to do and that being executed. It's a result of people being able to insert, reorder, or sandwich your transactions after you've committed before they're processed. And so cross-chain bridging has a lot of opportunity for MEV to sneak in because there's such a long time gap from the perspective of each chain. So MEV, in a sense, is about early access to information, and cross-chain bridging, that information is public so long before it gets acted on the remote chain. So everyone has 10 minutes of warning on what this message does and what it's going to do when it hits the remote chain, and how to front run that message most effectively. So from the perspective of the remote chain, the receiving chain, a message and a TX are equivalent. The message comes into the chain, someone off-chain submits it, and it kicks off some amount of computation or smart contract running or whatever. So a message and a transaction can be included in the block essentially the same as transactions. Reordering and sandwiching for cross-chain messages work just the same. But again, you have 10 minutes advance warning instead of seconds. So MEV pushes the ordering of a blockchain towards the maximally extractable ordering. The ordering in the block, which provides the most value to the searcher, builder, proposer supply chain. So everything gets shuffled, MEV transactions get inserted, and the proposer ends up making a bunch of money. So what we want to do is mitigate the impact that reordering and sandwiching have on cross-chain messages, because cross-chain messages are more vulnerable than the average transaction. So we're going to change the message flow a little bit that I talked about earlier. Rather than immediately dispatching to the other chain, we're going to accumulate on the first chain, on the sending chain, a batch of messages. And this should be a batch of messages that touches the same application or the same state. And rather than committing each individual message, we want to commit to a batch. So you take all of your cross-chain messages and you put them into a single unit. And then you dispatch that batch and process the batch on the other end. So what does this get us as a mechanism? Why do this at all? When you are extracting value from the remote chain's block ordering, putting it in a batch preserves the relative ordering of those messages. It prevents the miner or the searcher or whoever from extracting value by reordering the batch. And it prevents the searcher from extracting value by inserting within the batch. So this is a change to the semantic message handling of the bridge that mitigates the ability to extract MEV by preventing insertion and reordering for specific transactions. And we do this by changing the bridge and the way it handles messages. This usually introduces a small amount of latency, but as a result, you can't be extracted from as easily. So we can extend this to reorder batches upon receipt. So when a batch hits the remote chain, the destination, we can reorder that batch on chain using a deterministic but difficult to predict ordering. This can be as simple as just shuffling based on the block hash of the destination chain. Usually you don't want to use a block hash for entropy because it is in some sense predictable and manipulatable. However, we're not trying to prevent manipulation. We're trying to make it more expensive. So what this does is instead of delivering all messages in the order they were dispatched, within the batch, you can shuffle all of the messages using pretty bad randomness and then make sure that the messages are delivered in the shuffled order. And you might be thinking, can't a searcher just continually reshuffle until they get a good ordering that's more extractable? And yeah, they can, but we have a word for that. It's called proof of work. So the searcher now has to iteratively repeat some shuffle hash function and then try to extract upon that blob. And it has to repeat that many times, trying to find the best shuffling. And so searching on these shuffled batches becomes a proof of work problem. It increases the cost to the searcher in a way that mitigates the amount of MEV that the searcher can extract. It is less profitable to do this because the batches can be shuffled by the remote chain. And because all we're trying to do is increase the cost, we don't need good randomness to do so. We can rely on bad randomness that the searcher might be able to manipulate, because manipulating the randomness is equivalent to doing the proof of work. It increases the cost of extraction. So there are a few pros and cons, trade-offs to this. It's easy to implement and very little on-chain overhead. It mitigates specific extraction from cross-chain messages. Like I said, it's the Band-Aid. We're increasing the cost. We're not preventing it. It's a mitigation, not a fix. And in order to be effective, it requires significant throughput. If all of the messages touch a different state, then shuffling the order has no effect on the outcomes. This only works if you have several messages, a significant number, that touch the same state, so that shuffling changes the outcome of those messages. The other major con is that some applications want a specific ordering. They want to know that messages are received in the order they're dispatched. And this does not preserve that property. So this is kind of a quick noodle on potential bridging mechanisms for MEV mitigation. It is not a full solution, and it does not work for every use case. But it's still interesting and fun to think about. So that brings me about to the end of my slides. There are a few things that I wanted to talk about, but this is a very short time slot, so I'm not going to get to. One of the things I wanted to say is that cross-chain MEV is almost exclusively statistical MEV. It has risk involved because it plays out over multiple transactions. And MEV is the cosmic background radiation in cross-chain comms, and that it is going from everywhere to everywhere all at once. Every chain is being statistically arbed against every other chain in every sex at the same time. But you can't use that communication to carry any useful message. I really wanted to make a joke about ordering discretion and ordering indiscretions. So when you're ordering a block, you have discretion. And Tina politely asked me to say the word MEVconomics towards the end of the talk. So this is me saying the word MEVconomics. And that is the end of my slides.
Awesome. Thank you very much for that. I think we have a minute before Shriram is coming on. Something vaguely related. I'm curious for your take on the kind of conversation around, there's been a lot in the last week about rollups and bridges. Are they really defined by the bridge, or is the rollup this completely separate thing from the bridge, and it's all just chains communicating with each other?
So this is something that I fight about a lot. A rollup, definitionally includes a bridge to the layer one. The question that we fight about is whether the bridge determines the correct state of the rollup or whether the nodes determine the correct state of the rollup. And I land very firmly on the node side of things. I think that the bridge cannot force the nodes to accept any invalid block, but the nodes can force the bridge to accept anything. And as a result, I think that the nodes decide what the state of a rollup is.
Great.
In the context of...
No, keep going. Sorry.
Oh, I can keep talking if we're still waiting. I'm really good at having opinions. In the context of bridging, in this sense, rollups are special because they have this built-in bridge. And rollups are a subclass of sovereign rollups, which is a rollup without that built-in bridge. So you take the sovereign rollup, you add an enshrined bridge, and you have a rollup. We just came up with the terminology for these backwards, so the terminology is a little funky. Sovereign rollups are the general type, rollups are the specialized type with the built-in bridge.
Awesome. And
yeah.
I was going to say, just in time, Shriram did just join the room. Since we are running a few minutes behind, we will go over to him. Really appreciate the talk. This was great as always. And we are now going to bring on Shriram for the next talk. He will be talking about restaking and MEV. Thank you.
Hello, everybody. Let me get my screen share started. Okay, window. Okay, can you see the...
Yep, we got it now. You're good to go.
Okay, perfect. just noting down time. Okay. Hi, everybody. I'm Sriram. I'm a faculty member at the University of Washington, Seattle, also working on this project called EigenLayer. Today, I'm here to talk about how MEV intersects with restaking. And the subtitle of the talk is Mycelial Networks at the Root of the Dark Forest. So mycelia are these like fungi that help connect and interconnect the roots of various trees, basically helping them pass along nutrients to each other. So we think of restaking as basically something like that. And in this talk, we're going to kind of examine how MEV intersects with restaking and how we can think about it. Okay, so what is MEV, right? One way to define MEV, there are many different generalizations of this, but one way to define MEV is it arises from the freedom of block proposers to order transactions. So the protocol, for example, in Ethereum, the consensus protocol constrains various actions of block proposers, but there is still a remarkable amount of freedom when it comes to transaction ordering. And this gives rise to both markets as well as some negative externalities. And one example of a clearly negative externality is reorgs. So for example, if there's a block proposer and they see there is some like valuable transactions in a previous block, they may want to reorg the chain because of this. And while something like this is much more likely with proof of stake and much more difficult with much easier with proof of work and more difficult with proof of stake, because there is a certain amount of voting accumulating in, for example, in Ethereum today. One way to mitigate this is by using things like single slot finality. So in proof of stake, what happens is like once you have enough votes cast on a given block, then you can actually move on and finalize that block. And any finality which breaks, if two blocks are proposed with different orders, then the block proposals can be slashed. So one way of thinking about it is the mitigation is possible. The mitigation is possible because there is a certain amount of staking and there is a certain amount of slashing. And one way we can think about this is if we want to generalize this. So what is happening here is single slot finality is basically a commitment from block proposers to hold a certain rule. Even though they have a certain ordering freedom, they cannot exceed a certain bound on the ordering freedom because they've made a certain commitment. In the case of finality, a commitment not to reorg. And a commitment not to reorg is enforced because of slashing. And essentially, one way of thinking about how to generalize this is if there were a mechanism to do programmable staking and slashing, then block proposers can commit to more such rules. And this gives rise to new kinds of credible commitments that block proposers can make. That gives rise to more interesting mechanisms to manage MEV. So before we go and explore some of these interfaces, I just want to give a high-level overview of what is restaking through the lens of EigenLayer, the first restaking protocol. So what happens in EigenLayer is if you're an Ethereum staker, block proposers are Ethereum stakers. So if you're an Ethereum staker, you stake in Ethereum, and then you make a credible commitment on the EigenLayer protocol. It's just a series of smart contracts on which you can set your withdrawal credentials. And when you set your withdrawal credentials, you can basically opt into new commitments with the same stake. So you could be running middlewares, but you could also run more particularly commitments on how to run your transaction ordering preferences. And here, just to give a kind of mental model for how this collective works, is it's really a two-sided market. One side is Ethereum stakers who opt into securing these new services or to holding by the ordering commitments. Each middleware contains like an off-chain container that you download and run. And it also contains a new smart contract that you have to write. EigenLayer itself is just a smart contract on Ethereum, which is a container which holds your withdrawal credentials. And the EigenLayer contracts can talk to any middleware contract and enforce the series of like registration, payment, and slashing conditions. So that's the primitive of restaking. It's called restaking because you're staking in Ethereum core as well as opting into other kinds of commitments. Okay, so what I'm going to do in the rest of the talk is give like a few examples of, what are the possibilities at this interface. I'll also talk a little bit about what are some negative externalities that we want to think about and mitigate in this interface. One example is event-driven activation. So what is going on here is, imagine that there is a lending protocol, or there is, let's say, CryptoKitties. And if you're a CryptoKitty, there's this concept called the birth of a CryptoKitty. In a lending protocol, there's a concept of either refueling your collateral or liquidating somebody. And these are essentially event-driven actions. Event-driven actions basically means if the state of the Ethereum protocol is something, then the Ethereum blockchain is something, then a certain event needs to be triggered. This is like a cron job in Linux. And right now, we do not have a native blockchain framework to do this. Event-driven activations all happen potentially off-chain. And what you can do with EigenLayer is, if like block proposers are restaked on EigenLayer, then they can opt in to fulfill certain event-driven activation services. And basically and if the transaction that you need to trigger is a function purely of the Ethereum state, then what happens is, if the since the for example, in this case, the collateral refueling or repayment or any of these actions is actually a deterministic function of the Ethereum state, then the block proposer who's creating this block actually has made a credible commitment on this event-driven activation service. Then essentially they have to include that liquidation or CryptoKitties birth or whatever that is. Otherwise, the proposer can get slashed. So, what is happening here is there's already markets for this. For example, there is Gelato and Keeper and Chainlink Keepers and so on, which actually do services like this. But there is no tethering between that service and the block proposer. And so what happens is, there is a non-attributability. If a Gelato triggers a transaction and the transaction did not get included, it's not attributable whether Gelato actually triggered the transaction and like the proposer didn't include it, or something else happened in the middle. Because things are not attributable, you do not get like strong cryptoeconomic guarantees of these actions. But once you have strong cryptoeconomic guarantees of these actions, you actually change the structure of the protocol quite a bit, because now, for example, what happens is, like, let's say if you know that like people can set up like collateral refueling within a few blocks because there is some significant fraction of proposers opted into this market, then what could happen is for margin lending or for stable coins or any other protocol, the over collateralization ratio is basically just the time to liquidation. So because you can have very tight time to liquidation, you can actually build much more efficient financial protocols if you had event-driven activation. So this is one example of how MEV and something like restaking can interact with each other. I'll give another example, which I've talked about before, called partial block auctions. We called it also MEV Boost++. And the core idea here is MEV Boost is a mechanism to sell your entire block to a block builder. And instead, we can think about whether it is possible to sell only portions of the block to the block builder. And the main reason why only the entire block is sold in the MEV Boost market is, if a block proposer double signs a block header, then they will get slashed. So by having them commit to signing a block header, we get a credible commitment that they will actually include that entire block. But by opting into something like EigenLayer, a block proposer can express much more fine-grained degrees of freedom. For example, saying that I will include this a chunk with this hash as the prefix of my block, and the remaining I have freedom to fill in myself. So that's the high-level idea. I mean, I can just dive into like one level more detail here. The idea is that block builders can send a certain portion of the block, which is, you can call it the builder part, and a block proposer basically includes the builder part at the front of the block, and the remaining is a freedom from the block proposer to include whatever transactions they want at the end of the block. So instead of the block proposer selling the entirety of the block, they're only selling one portion of the block, and they have freedom to fill in whatever they want at the end of the block. And why is a mechanism like this interesting is because now block proposers can express their own agency in figuring out how to fill the rest of the block. And this, if you look at the whole MEV boost architecture, it is tailored around actually making sure that block proposers remain decentralized. But if the block proposers are decentralized but have no agency in expressing any transactions, then it's not clear what benefit there is. But in a mechanism like this, if the block proposers can express their agency, then you actually get something quite powerful. Okay, so there is a lot more details there I don't want to get into, but I just want to keep this conversation at a high level of what are possible synergies of once you have block proposers in Ethereum L1 restaked, what other things can you start doing? Okay, so another thing that you could do is you basically have a bunch of nodes participating in eigenlayer. Like, let's say a block proposer has opted into this threshold cryptography, then what could happen is transactions that come encrypted to a threshold cryptography method where there is a secret share of the keys among the many nodes which are also restaked on eigenlayer. And essentially what they can do is the client sends in transactions which are encrypted to the threshold group. And once the transactions are committed with the encrypted with the threshold group, an eigenlayer block proposer can take in and sign off that they're going to include only a decrypted version of these transactions. And once they receive the decrypted version of these transactions once the decryption key is available, you can actually go in and include the right version of transactions. A block proposer that commits to an encrypted transaction but doesn't include the decrypted transaction could get slashed. Here, there is an honesty assumption on this keeper group. If the keeper group is majority honest, basically it is possible that the decrypted version of transactions is not included. So one way to protect against this is you would say that if you did not get the decrypted transactions, you have to just waste your block space for that portion of gas that you sold for the encrypted lane. And so this helps protect against, even if a majority of these are dishonest and do not reveal the threshold key, then the block proposer just proposes an empty block. And so it's just there are a lot of ways to tune the incentives here, but high level idea is because the block proposer is committing to include the threshold encrypted transactions, they don't include the decrypted ones, then they can get slashed. Okay, so that's another example. I'll give one more example here before switching to any mitigations. One example is, is it possible to sell block space futures? So block space futures is I want to reserve a portion of block space from this validator in the future. And the idea here is you send your transactions to a super fast MEV chain. This could be something like Suave. And, this chain needs some amount of reorg resistance and some amount of censorship resistance. And you buy block space a priori, and you send your transactions to this super fast chain. And if the transaction gets included in this super fast chain, then a block proposer who has opted into this block space future actually has to include these transactions in the block. And so essentially block proposers can make credible commitments to include transactions from the future block if they get included into the MEV chain. So this is another example of what we can build. And it's possible to take all these different modules and compose them to build a block where some aspect of the blocks come from event-driven transactions, some aspects come from auctions sold to builders, some aspects of the transactions come from threshold encrypted lane, some other aspects come from the proposer having their own freedom. So this is, in some sense, like a modular roadmap for how MEV can be built on Ethereum by using something like restaking. There are also some risks. I want to just spend the last minute on this. One risk is because you may need proposers to be more sophisticated, it may lead to more centralization if you have mechanisms like this. But one way to contain this centralization is by basically, if there is enough of a rich language for the proposer to express their constraints to the builders and to the relays, then the builders and relays can actually satisfy all these constraints for the proposers. There are also other really interesting things that happen with restaking, is because in some of these services, services building on restaked eigenlayer services can only request the more decentralized committees to participate. It's possible for promoting actually decentralization in Ethereum itself. There is the possibility of cross-domain MEV because the same set of nodes now participate in many different domains or services. And again, the solution here is to opt into like rich general purpose cross-domain MEV markets like Suave to actually build these things. And finally, there is risk of actually potentially building censorship markets on something like Eigenlayer. I think this is something we can only keep vigil socially and use social consensus to deal with situations like this. So that's a high-level tour of where I think there are interesting intersections between something like Eigenlayer or in general restaking and MEV, and look forward to having discussing with some of you on this. Thank you.
Awesome. Thank you so much. And this is going to segue perfectly, so you can hang on here. We're going to have a panel now on MEVconomic security in liquid and restaking protocols. So it'll be myself moderating, and we're going to have Shriram. And then we're going to be bringing on Tarun, Ben, and Hasu for this one. How's it going, everyone?
Hi.
Yo.
All right, sounds all working. So your last slide actually segues perfectly into the thing that I wanted to ask for the first question. And it is around that centralization risk, which exists for both restaking and liquid staking, which are both of the topics here. Liquid staking so far has been somewhat limited in the amount of operators that are generally like actually working under the hood of some of these liquid staking protocols. So there's going to be a challenge there. In, Lido has talked about in their V2, things like the staking router starting to use DVT to try to decentralize under the hood. And then similarly for restaking, there is that centralization risk of, ideally we would like to have these super horizontally scalable things like EigenDA that are easy for nodes to run. But someone could also show up and put Solana on restaking. And now there's effectively a massive incentive out there to be a really sophisticated restaker. So where it's supposed to take advantage of staker heterogeneity, does it just then incentivize that kind of lower bound to actually just move up? So I'll turn it over to you, Shriram, to kind of continue where you left off on the last one to start.
Yeah, no, I think if you look at aspects of decentralized trust, there are two distinct aspects of decentralized trust. One is just coming from the amount of economics, and the other one is it comes from a certain amount of decentralization or collusion resistance. And I think different services rely on different kinds of security. Like, for example, if all you want is for example, for certifying that a certain execution condition is valid, and you want somebody to underwrite this risk, as long as there is, a significant amount of economics underpinning it, it is enough. Like if you had $1 billion restaked on like a validity condition, which is checkable on chain and slashable, then it doesn't really matter whether that $1 billion comes from one node or it comes from like thousands of nodes. I'm talking about this from the point of view of services building on top of Eigenlayer. And that for those services, we would expect basically like they would, there is a significant benefit to centralization. So there is like a small centralized committee or just like Coinbase or some like few nodes, which can just opt in and provide these services, which are primarily just economic in nature. And there is another set of services which simply do not, it does not suffice to have economic security. You need decentralization-based security. And some examples there are, you want to have an ordering layer which has censorship resistance. You want to have secure multi-party computation where you're splitting up some secret and information into different nodes. And the core assumption is that these different nodes don't collude with each other. There are other examples like the threshold cryptography we saw earlier, where like you need to split up a key into secret shares. Even things like data availability rely to some extent on an honest majority or like a honest certain fraction assumption. And these examples all demand a decentralized quorum. So what we expect to happen is on more expressive restaking platforms like EigenLayer, people will specify that they only want a decentralized quorum for certain tasks. And this can promote an additional yield to accrue onto the decentralized quorum. And, basically, instead of all of us just, talking about the ideology of decentralization, there is an actual value of decentralization. And if the users can just pay up for it, that's really the best way to promote decentralization.
And Hasu, I wanted to turn to you on the kind of first half of that question. Curious for your take on the liquid staking tokens and kind of the underlying operators of those, particularly because it's unlikely that we're going to have a million different types of liquid staking tokens. So it is important if we want a decentralized validator set, most likely that kind of the underlying components of Lido, Rocket Pool, et cetera, that they are able to more sufficiently decentralize that validator set underneath, and kind of how you see that landscape and how you see that playing out going forward.
Yeah, great question, John. I think that first of all, I agree it's super important that the liquid staking providers decentralize, because there is a lot of centralizing pressure on them because of the network effect of the underlying token. And we have seen a range of different designs from completely centralized providers like Coinbase on the one end to arguably very decentralized providers, but less scalable, like Rocket Pool on the far end, and then Lido maybe to the slight left of Rocket Pool, making another trade-off in more scalability, but less decentralization. And so it comes down to a trade-off, and the question is, will those trade-offs remain, or can we have the best of all worlds, right? Can we have scalability and decentralization? And I think the answer is mostly yes. So there might always be the need for some amount of governance that cannot be removed. But so my favorite mental model for thinking about this is basically thinking of a staking pool as another variant of a lending market, where you take money from stakers and you basically give it to node operators, right? And there's different types of lending. There's one that's secured by reputation, and then you don't need a lot of collateral, or anybody basically can borrow, and then you do need more collateral to secure it. And so I think whenever you want to have scalability, you basically can't have over collateralized lending only. And so you need some way of dealing with this reputation challenge. And I think it would be interesting to see how well we can bring these kind of attestations to someone's reputation, how well we can make that trustless, how well we can bring that on chain entirely. For example, through the use of inspecting, performance stats, building reputation over time, but also minimizing the harm that a faulty node operator can do through techniques such as DVT. And then in the center, I see something like the staking router that you alluded to in Lido v2. That is basically the central hub where anybody can where anybody can add new modules, new combinations of node operators and collateral and reputation and whatnot. And then there's some central mechanism to allocate those and to allocate the ETH that comes in to those modules. And I would be very interested to hear Tarun's talk, because I think he's what Tarun thinks about this, because he's one of the leading experts on lending markets and parameterizing.
Parameterizing.
Yeah. Basically the relationship between the collateral and the borrowers and so
on. Yeah, I mean, I kind of think the Lido model is the end game. The router model is sort of the end game for this. It's funny you mentioned, hey, you could implement Solana on top of a restaking mechanism. Well, I don't think running layer 2 sequencers is that much less difficult than keeping up a Solana node, if we're going to be completely honest. If you look at all the Arbitrum posts, if you look at all the it's like not that different. And I think in the rollup world, sequencers and providers to rollups are going to have to do a lot of operational overhead. So I think the centralization aspect of like, oh, I don't know how to correctly restake or allocate my assets is a problem you will have generically in a decentralized sequencer rollup world. Like those users are going to have to be just as sophisticated. So I guess I see it as less of a concern from the perspective of like, we're already moving to this kind of extremely complex ecosystem of chains. And in that world, you're inevitably going to have to solve these allocation problems, no matter what participant you are. And based on that, I think, yeah, figuring out what the collateralization looks like will change over time, especially if a lot of Lido node operators are restaking to also provide sequencing services for particular rollups. And I think, of course, Ben has wrote a nice post about kind of opinions on that and how to think through how the strategic decisions when you're in a decentralized sequencer. So
yeah, just one thing to add about the question about what if a protocol like Solana, which favors centralization, were to run on Argument, or whether that favors centralization of e-staking? I think it really depends on the relative fraction of value that's accruing to staking ETH from participating in Ethereum itself versus another protocol. So it would only really become an issue for centralization if the value coming from Solana was like much greater than the value, or at equal to or greater than the value coming from participating in Ethereum itself. So it's, yeah, that's just a very important part to take into account.
Ben, do you want to say something about like how lightweight decentralized sequencing can be? I think Thorin's saying basically decentralized sequencing will be.
I mean, from the perspective, yeah, I think this is sort of I think that it's anyways a desiderata of decentralizing sequencers to make it lightweight so that it can be, fully decentralized. I think that's a bit of a different question from the concern that something like Solana could also come onto ETH staking platforms. But yes, you can definitely try to make decentralized sequencing as lightweight as possible, so that and that's what the E3 stakers would be participating in. Like E3 stakers would not be participating in complex roles like proving. They would be participating in the sequencing. You don't need to have E3 stakers participating in proving if they are participating in the sequencing.
Yeah, I think even more specifically, I think the idea that you don't even need to hold the state of the rollup, right? Like you don't even need to participate in execution.
Just ordering and data.
Just ordering, and ordering is a stateless operator. So you just order a bunch of transactions, and as long as you're collecting the fee for ordering the transactions, those transactions are kind of forced to be included. So that's how you can scale sequencing.
I mean, the reason I would slightly push back on this is looking at, say, the Arbitrum example of the sheer amount of network bandwidth that the sequencer had to handle. It very much reminds me of the Solana DDoS level bandwidth. You're talking about people sending 100 gigabits a second to a single entity. So we still haven't gotten to that point where I would say I believe that they're that different to a node operator. I'm sure Hetzner probably can, which is a big data center operator. I'm sure they have the exact statistics on how much bandwidth Arbitrum has had to deal with versus Solana and uptime statistics. And I bet you that's not that crazily different. I especially after the airdrop, I think they're they're not so different in terms of operational overhead. That's sort of my main point right now.
No, I think that there may be one thing to it, but I want to just say that like there is the problem of not having MEV auctions is what has contributed to that, and to segue into your next talk. And as long as the decentralized sequencing system has reasonable MEV management, which Ben has taught a lot about, I think you would not have a problem like that.
I also wonder how much that needs to correlate with the value of staking. Like you could also have as a public good a infrastructure or server that's doing a lot of work in terms of routing messages, but in order to participate and stake in the protocol, you just need to do lightweight operations. And so in some sense, that public service is it's just a public service that's being subsidized by everyone participating. And it's not clear that you need to, by staking more, you can then run that service and therefore profit more. So I think it depends on the relationship between staking and participating in different roles.
Yeah.
Like for example, yeah, John.
I was going to say, the one point I would push back on a little bit from earlier is in regards to how much the rewards actually need to be for something like this to create a centralizing force, where it should be equivalent to or possibly greater than the type of rewards you would get on Ethereum. I would say that doesn't have to be the case. I mean, this is exactly what we see with MEV Boost. And you can kind of think of any additional restaking revenue to be viewed as a form of MEV to any kind of potential restaker. And we see that with MEV Boost where, hey, if I could earn 4% or 5% of my own, but I can earn 6% with MEV Boost, 95% of people are going to run that thing. And they don't even necessarily need to create that value, particularly if that, like this restaked Solana, if they say they have an inflationary token that they're giving to the restakers, and that subsidizes like a high yield for them. So that risk does still exist somewhat in my mind. I don't think there is a perfect answer to it. One of the interesting things that and we have talked about it before is actively incentivizing decentralized committees with higher rewards as opposed to centralized ones, such that there's actually an explicit advantage, which is a very difficult problem to do, but theoretically could be done. And it's a very interesting thing to play around with.
I would have a follow-up question to that. So how do you identify decentralized committees reliably?
Yeah, I think this is going to be a whole another like service, which would basically do it. And just to clear our perspective on this is, Eigenlayer wants to be, one of the paradigms that we lean heavily into is intersubjectivity. Intersubjectivity is that like most subjective decisions are made at the edges, not at the platform. So we don't want to make a judgment saying somebody is more decentralized and somebody else is less decentralized. And each service needs to consider its own like requirements when making these decisions. And these could be supported by decentralization oracles, which then like steer people in those directions and for the particular needs of each of the services. Like a secret sharing is an example. If you sent this, and shares of the secret to the same person, you basically end up getting no guarantee, even if those set of people are geographically distributed. There are other use cases where, for censorship resistance or legal and other purposes, you want people from different jurisdictions to participate. That's a different kind of like a requirement. So each service will have its own requirements, and they will lean on a new ecosystem of oracles, which just try to do this thing. And there are, it's hard to identify decentralized nodes. It's easy to identify the centralized nodes. We will know what the exchange wallets are. We'll know what some of the biggest operators are and so on. And just excluding them just still gives us a long tail of nodes to work with. So there are all kinds of ways that services can do this. And there's no one universal correct good answer. And it's going to depend very much on the service.
So actually, one thing I've kind of wondered as sort of a research direction that towards this, that, I don't think we can do right now, but maybe, in a couple of years, we'll be at the place to do this is, there's this line of research on doing secret leader election in proof of stake with threshold homomorphic encryption. And there's a question that I've always wondered is of like, can you do private elections of committees, not just single leaders, for this type of thing if you had, say, threshold FHE? And like, would that be sufficient for the type of thing you're talking about? Because I actually think you could generalize their method to multiple participants, but no one's done that yet. And that, I think that would like be like the foolproof. Obviously, you know, relying on FHE for anything is always scary, but
No, Tarun, there is two aspects to this. One, if you start with a centralized staking pool and just choose like even many leaders randomly, it's still not going to do any benefit because all leaders are basically the same person. So there is a kind of baseline of decentralization that you absolutely need,
sure,
and
sure,
then
sure,
on
sure,
top
sure.
of which you need like the multiple secret leader election to make it even more protected.
Yeah. Sorry, I agree. I wasn't. Definitely, you need to kind of have the stake distribution be, you know, more uniform over unique identities, not just addresses. But I guess there's a lot of this other stuff that I think has been lying in the shadows around this type of stuff that, you know, maybe we'll see live in 1 to 2 years, hopefully.
Turning directions a little bit, I just got a rather spicy question someone sent me just a few minutes ago during the talk. It relates to, so I know, Shreya, you've spoken in the past how eigenlayer could, particularly later on, be viewed, and restaking broadly, as some kind of like free market upgrade to Ethereum, where particularly as it gets more difficult to upgrade Ethereum, validators can effectively opt into it as a free market and do it themselves. The inverse side of that I wanted to ask everyone's takes on is, does this give a kind of additional unearned governance power to validators, where, for example, if Ethereum developers in the community, there's some upgrade that they view as rather risky, this is not something that we should be doing, but the restakers say, hey, I can make a bunch of money from this thing and we're all going to opt into this. Where do you kind of see that kind of tension between that governance power, which we may not want them to have, versus also that flexibility is a positive thing of being able to kind of free market upgrade over time?
I think the real answer to this lies in the full nodes. Okay, so as we all know, like there is a power in the full node which is not fully specified in just the internal nodes, which is that if there was an invalid state transition, the full nodes can reject it. And imagine now there is an upgrade on top of which comes from something like eigenlayer, which like everybody opts in and all the validators are doing it. But at the full node level, so buying opt-in, for example, at the full node level gives you like a significantly boosted security beyond the economic security that you can get by the stakers opting in. And it is at that threshold that really the buy-in from the rest of the community is needed. And I have some ideas, untested ideas on how a new service, for example, might be able to do it. For example, a service may commit to burn ETH if like all the light nodes upgrade, or full nodes upgrade to, when receiving the fees is not just distributed to the stakers, some fraction of the fees just burnt as a compensation for the externality to the full nodes, which then need to upgrade to not only check the validity condition on the core protocol, but also on this protocol extension. So there are all kinds of interesting things that can be done. But also the flip side is, for example, if there is a censorship market built on restaking, where you just say that like, hey, I'm going to pay to like censor somebody's liquidation transaction so that I can earn the money, I think this can only be dealt with socially by like whatever slashing these these stakers and so on. So it does become more complicated.
One thing I guess I would say is like, in what world have, if we view sort of restaking as sort of bridging the gap between like clients, full nodes, and archive nodes, like, each of those levels had different governance rights in some sense in almost every network. All you're doing is you're taking like this discrete node types and like making a continuous spectrum out of it. And in some sense, light nodes never really had governance rights before, right? They sort of were just forced to eat whatever shit Merkle tree is shoved at them. And I think like, it's sort of the same. All you're doing is just like widening that spectra from these like 3 delta functions.
I would also note that validators do already have the the agency to run another protocol, E3 staking is subsidizing that agency, right? It's saying you already have ETH staked, so now it's less costly for you to run this additional protocol. But they already have the agency to run another protocol, and it's also not clear that by running another protocol, this necessarily is equivalent to an upgrade, because it would only be if that they were running that to the exclusion of running Ethereum itself.
So it's a protocol add-on. You could think of, like, if everybody is running it, you could think of it as a protocol add-on, and that's where I was going with. But full nodes don't check for the validity of this protocol add-on, and so you could ask them to check for it by, like, doing this fee burn. There are some fans of 1559 and fee burn here. So that's basically a compensation for the externality to the full nodes for having to check that they're continuing to do that.
Great. Another question I know that a lot of people have kind of had trying to get their head around is this idea of leverage, quote unquote, in staking and restaking, noting the clear difference in that obviously, you take on a leverage trade or something like that, like you might get liquidated on that due to just market conditions. If you're restaking and you're honest, you shouldn't be slashed, assuming everything operates correctly. But you are increasing the leverage in the sense that you potentially have a very high ratio of value secured relative to the amount of stake actually securing that thing, which is moving in this direction of pooled security. And that works primarily under the assumption where this increases the value of something like ETH with the value that it's securing, because more value goes to it. But the other side of it is something like restaking. One of the interesting benefits is you could do dual staking tokens with it, where there's some other kind of token that captures value. So do those things kind of become at odds with each other at a certain point, where now ETH isn't necessarily capturing that value, which accurately compensates it for the additional risk that it's taking on economically, where some of that value starts going to the second token more and more, and they want to kind of move in that direction?
Okay, so I think there are really different. So like you said, from the staker point of view, if they're honest and if the protocol code is correct, they'll never get slashed. So let's keep the staker out of the picture. From the service point of view, is there are you increasing additional profit from corruption by adding new services on top? I think that's the high level question, and I think this is a lot more nuanced question, and I don't think we'll get to this thing here. The idea is, if you look at Ethereum, it's securing $400-500 billion of value with $25 billion of stake. And first we have to get to the bottom of why is it okay to do this? It's okay to do this because, we are, the total value secured is not what is protected by what is staked. The total value transferable out of the system within a short period of time, within the attack duration, is what is being protected by staking. And by having this mental, this cryptoeconomic model correctly programmed across various services, you can actually get very strong, provably correct guarantees on what the cryptoeconomic conditions are for safety.
John, I think another way of looking at this, that issue that you described as leverage, so just from a different angle, is that because an E3 staker is now participating in many different sources of revenue, right? For an individual chain that it's securing, the value the value that being generated by that chain is low relative to the value of the ETH overall being restaked, because it has many other sources of revenue. And so this becomes an issue of the fact that if the relative value of this one chain that it's securing is low relative to all the other chains it's securing, then the marginal utility is too small for it to care that much about that one chain. So in essence, it's from the perspective of the chain that the risk arises, which, and dual staking can lower the leverage of the E3 stakers, right? And it can it then shifts the security onto another source, what this other token is, and so that is helpful for the chain itself. I mean, it's one different. I think it's the same issue as being over leveraged, but just from a different angle.
Yeah, I would just add, I like thinking of it as, even though I'm sure by mentioning this word, people will suddenly get scared, but I like viewing it as like the sort of like tranche style insurance where like the second token is taking the equity style losses beyond a certain point, and the ETH is not, which is that's sort of this over leveraged piece. Like there's not going to be some like huge restaked ETH liquidation versus like some fraction of that gets absorbed by this other token. Now, the question is, can the other token ever get to a market cap close enough for it to be meaningful relative to ETH? And like that's a different question. That like, will there be enough liquidity for it to actually be this sort of like loss asset? But in theory, that's sort of what you're kind of hoping for, is kind of this split.
I would also point out that you can't really prevent validators from taking on additional leverage. So, for example, we've seen the rise of liquid staking tokens, and those liquid staking tokens are now the primary form of collateral used in Ethereum lending markets in order to borrow anything. And so we already have an implicit amount of leverage in the system today. And so people are blaming liquid staking tokens for that, which is, it's just inevitable. But so to those people, I would say even before that, in proof of work, there was already a lot of leverage in staking, in mining, that is, because all of the big mining farms were all deeply, deeply leveraged. So they were buying all of their machines actually on credit, right? And they were borrowing against their machines, and they were using their machines to collateralize as well as their future cash flows to buy more machines. And so this is something that all protocol designers have to keep in mind, that you just can't control what people do outside of your protocol. And that's why you have to operate with big margins of safety. Like Sriram was saying, like Ethereum protocol does not secure all of the money that is sort of part of the Ethereum state somewhere. It's not even all of the money that is currently being transacted. It's only that which can be controlled by the ordering, basically, because not even 100% malicious validators could force an invalid state transition. That's why I think, the gist is basically leverage is always possible. There's no way to prevent it, and you just have to design around it.
Curious, quick follow on for anyone. If you, and I would agree on this, that something like liquid staking tokens were inevitable in hindsight. Are liquid restaking tokens inevitable looking forward? Where you have a position saying that, I have my ETH staked, but I'm also restaking to these 4 other things, and this like gives me the right to the associated cash flows of those, and there's all these different liquid restaking tokens now with an additional layer.
I think it's much more likely that liquid staking protocols will integrate some of the services under the hood, which means existing liquid staking tokens kind of eat the additional reward by just integrating the under the hood for that certain services which are highly yield bearing, rather than you having to go and create a whole new liquid staking token for restaking.
So I guess I sort of think of it as like, if restaking is successful in the sense that it has hundreds of applications using it, there will inevitably be some notion of like ETFization, where people want different classes of ETH yield. There'll be like the most high grade ETH yield, but it's just pure staking. There's like the slightly riskier ETH yield, which is like maybe staking plus submitting Oracle updates. Then there's maybe the slightly higher risky version, like data availability plus Oracle updates. Like this all depends on what the slashing rates are. So so the relative ordering is not perfect, but I could imagine people basically like fractionalizing like what level of ETH risk do you want? And
I would agree with both of those. I think that the liquid staking protocols will internalize restaking if it turns out to be profitable and useful. And I think also down the line, maybe in a few years, those same liquid staking protocols will come out with different tranches of ETH that give different levels of risk and seniority to investors. I think that's one of the main things that remains in the design space for these protocols after stuff like the liquid staking router and DVT has been figured out, I think.
Great. So one of the applications that you guys are very familiar with that will be secured potentially with restaking and has been talked about a lot in some of the previous talks is something like a shared sequencer layer, something like Espresso has talked about in the past week. Even simple forms of a shared sequencer, aka effectively based rollups, where you're using the L1 as a shared sequencer. One of the interesting points in the value flow of MEV, as Justin was speaking a lot about earlier, is that in the simplest case, that value now effectively goes to the L1 itself. So in base rollups, it would go to ETH. In a shared sequencer, the value from the rollups MEV that they would normally get from their own sequencers, in the simplest case, would go to the shared sequencer layer itself. And so the question then becomes kind of around the incentives for rollups to use those things if they want to keep that kind of value for themselves. And more value should be created in the system because, as I know Shreem had some great tweets about this the other day, is like kind of the baseline is what they would have already had as MEV, and now you should have an additional MEV that's opened up by the interoperability between all of them. So you, in theory, have more value created. But that kind of incentive alignment issue of like, how do we return that value to rollups in some form such that they're incentivized to opt into this thing? And it's not just nobody wants to opt into the thing that will optimize everyone because I want to keep most of the value for myself. So like how we kind of think about those trade-offs and the value flows.
I can take a stab at this if I, to go first. I think there's a lot of analogies here to, you know, like you have a music festival and you have all the bands showing up to the music festival and the music festival is selling tickets, right? And how do you pay the bands to show up? And it's also not a one-shot music festival, it's a repeated game. So eventually if the bands realize, oh, the music festival organizer is taking all the profit, we're just going to run our own music festival. So I think that before we can talk about the economics of shared sequencing and how and to whom the value accrues, it's important to identify like who are the players, right? And I think Barnaby has like a very nice post on this for rollups, which distinguishes three parties like users, a rollup operator, the base layer. And here with shared sequencing, we have another party, right? We have the shared sequencer and the nodes operating it. But I think we should also separate at the rollup operator level between the provers who are actually incurring the operating costs and the governance of the rollup, right? But that has the power to decide two things, right? How do you define the VM, right? And which sequencing layer is the rollup going to run on? And importantly, not only do they have the power to decide that initially, the governance has the power to decide to move away from the sequencing layer. And that gives the governance of the rollup leverage. That governance could be encapsulated, well, it could be a central company, or it could be encapsulated in some token. I mean, let's just call it the governance. So base fees covering the operating costs, like proving, plus some epsilon profit, that can be easily directly programmed into the VM. And they need to do that because they need to get provers to run. But obviously that base fee doesn't capture MEV. And so then it's the negotiation between the rollup governance and the sequencer. The rollup governance wants to know, you know, am I going to make more running on this shared sequencer than I would make running my own sequencing layer, right? And obviously there's a cost of building your own, one-time capital cost of building your own sequencing layer. But ultimately you want to know that you'll be making more, you know, going to the festival rather than running your own show. And so I think it comes down to a negotiation, and that can manifest in many different ways. One way is if the average MEV that the rollup would make on its own can somehow be estimated or simulated, or it can be adjusted dynamically based on historical average, then that can be like hard-coded into the base fee of the rollup VM. But I think that's quite hard, and that base fee would not be covered by users. It would be subsidized by the sequencer nodes. Maybe they go into a deficit sometimes, but on average, they would be able to cover the cost and take the surplus that comes from shared sequencing. Another way would be probably the ideal option, but maybe challenging to perfectly achieve, is if the allocation algorithm, okay, the mechanism that the sequencer is running is transparent, in other words, if there's transparency in the MEV auction or the block building process, and if it can calculate and verifiably report what is the marginal contribution of each rollup to the total MEV, and it distributes that proportionally to each rollup, taking a cut for itself, then that would foster the strongest trust and incentive alignment between the rollup governances and the shared sequencer. But I think that's like an important research question, and like that I think is like the ideal option, but it may be hard to achieve. I think it's feasible.
There is some inspiration from the Atom world on interchain security here, which is basically like doing dropouts, like randomly dropping out like one of the chains and then calculating what the average builder value is, and then like you can use that to calculate or estimate what the looking at the chat here, estimate what the marginal value is for the different ones. Another way is having actually like free combinatorial auctions. And then now I have to segue to Tarun.
That sounds very expensive for the participants, but yes, that's possible.
So I think there's one option that we haven't discussed yet, which is just allowing rollups, not enshrining a single sequencer layer, but just having the ability to profit switch between different ones. And it's a funny thought how sequencing layers could kind of be destroyed and be created on like a per block basis. So I don't know if that's viable or not. But I think definitely in the future of multiple sequencing layers, nothing speaks against these sequencing layers competing on a per block basis for the MEV and just bidding up the value paid to the proposer or to the governance, as it would be in that case, right? So yeah, I think that's another option.
I'll probably get in trouble for asking one more question because we're running late, but I want to ask it. I'm curious for thoughts regarding, it's something that I talked a bit about earlier as well, and Barnaby has discussed in the past, of his idea of Pepsi, the idea of like the protocol being able to enforce different proposer commitments. And like the first part of that abstraction that he's talking about is this kind of idea of an in-protocol eigenlayer, where you can make the protocol aware of these commitments such that you don't end up with this problem where the protocol is not aware that, hey, maybe this person is slashed, and is like not really aware of what's going on with its own security at that point. So I'm curious as to any of your thoughts on, is it helpful to kind of build these things in more to a greater extent to be able to just give the protocol more awareness of like what's actually going on with its own security, or are there other externalities to think about in there where that may not be attractive?
Yeah, I think, the first part to that is how to make Ethereum aware of a slashing event on something like EigenLayer. I think the answer to that is actually simple and thankfully coming up in an upgrade called smart contract triggered withdrawals. Right now, withdrawals are validator triggered, not withdrawal credential triggered. And once you change that, the awareness can be kind of instantaneous. As soon as the contract is aware that there is a slashing, it immediately like goes and triggers the thing from Ethereum. So that's the answer to the first part. But there is a second part of the benefit, which I think you accrue by having it be enshrined as opposed to being on a kind of like a secondary layer like EigenLayer. Is the benefit is that, suppose somebody makes a proposer commitment that I will only include the decrypted version of these encrypted transactions and in the block. But they actually don't include the decryption. On EigenLayer, all that we can do is to slash them for 32 ETH. So the maximum liability is like bounded by 32 ETH in EigenLayer. Whereas if you make it in protocol, I think this was mainly Barnaby's idea. The idea is that if you make it in protocol, it can be part of the validity condition of the block itself that the proposer met the condition or not. This is just a much higher bar. There are ways to, I think, therefore, if and when such a thing is possible, it's actually beneficial. But the problem is that, if somebody writes a bad opt-in condition which had some smart contract bug, it could lead to mass slashing events and things like that. And the only protection we have right now is based on eigenlayer, is based on a subjective slashing veto. And I don't think Ethereum would want to internalize, such kind of subjective committees. So the evolution that I imagine is going to be that initially people play with a lot of these models on a opt-in layer like eigenlayer, and once that is much more like robust and stable, some aspects of it can be basically just enshrined default into Ethereum.
There we go. Awesome. We will cut it there. Thank you everyone for this. This was a lot of fun. And again, we will perfectly transition. We've got Tarun who will be staying on for the next one, who in his own words is going to be talking about how to kill fair ordering.
Sorry, Shriram.
No, I'm very happy about killing it.
Hey, sorry for that. I'm just sharing my slides. We'll take 1 second. Didn't realize I have to allow StreamYard to do this, so sorry about that. Give me. Great. Hopefully shows up in a second. Cool. Cool. So yeah, first off, I want to talk a little bit about the flaws of fair ordering. And this is not meant as a attack on any of the people who've worked on it before. I think like it's a really interesting idea in social to take some of the ideas from social choice theory and apply them to try to make blockchains more fair. But I think there's no way of doing it in the way that people have tried. There might be some other stuff. Hopefully we'll end with some positive notes, but before that, let's bring out the hatchet. So Tina, as previous speakers have also mentioned, forced us to say the word MEVconomics somewhere. In my case, I unlike John and James, kind of sort of wrote a slide. And the idea is that and this is a quote from one of the papers on fair ordering, which is fair ordering guarantees specific ordering in a finalized ledger on how transactions arrive to the network to reduce minor extractable value. Yet virtually all fair ordering mechanisms say nothing about the economics of what they do. They guarantee that like some subsets of orderings will be respected, other ones will not ever happen, but they never tell you the cost of that or whether certain payout functions change with that. So one question is, if we're putting all this extra onus and extra work on top of validators, what's the real economic value of it? Is there economic value? Is it harmful? And that's sort of the main thing we'll be covering. So, what is fair ordering? So fair ordering is a mechanism that coerces honest validators to respect a particular set of orderings of transactions, i.e. first come, first serve, block order fairness, block batch order fairness. All of the papers are not duplicitous. They do all point out this fact that it's actually impossible to attain perfectly. Kenneth Arrow won the Nobel Prize in economics for proving this, which is that in ranked choice voting, so you can think of a ranked choice vote as a validator giving you an order permutation of sequence of transactions, and then sort of aggregating the vote together to construct a final outcome, that it's impossible to get something that doesn't centralize, that doesn't have what's sort of known as a dictatorship. So instead, fair ordering tries to, make algorithms that are approximately the average or majority vote or some type of property for most ordering. So, here I put two different definitions. The other thing that's kind of funny about all these papers is they all have slightly different definitions of whether a batch is fair or not. And they all involve sort of extra data, like some notion of timestamps and some assumptions of honesty amongst the validators. Thank you to John for making this meme. But there's something weird about these definitions, right? These definitions are properties of partial orders. They don't say anything about the economic value per unit partial order. Yet, on the other hand, if you think about MEV, MEV is actually an economic profit, a rent that is extracted. That rent has a size, it has a magnitude. And I think, the three main papers on fair ordering, Themis, Aquitas, and quick block ordering, they had like good intentions, but they completely ignore the economics, and they're like, hey, you do this thing, it's this combinatorial thing, we restrict the sets of orderings, and it gets rid of MEV. And it's kind of a crazy statement to make, because again, you don't quantify the actual amount of MEV or the value, and you're agnostic to all applications, which doesn't really make much sense, right? There's a reason that certain applications generate very regular MEV like AMMs, some generate very spiky MEV like liquidations or NFT auctions. Those are very different things. You can't really tell me that this ordering is universal to all of them. And so that's the thing we're going to kind of explain today, to try to dismantle this kind of shambolic industry of hoping that we can, violate the natural laws of social choice theory. So, is it really a good idea to cause these, to have validators have to do all this extra work when it doesn't really have an economic payoff? And hopefully you'll be convinced, at least somewhat. The full paper will be out soon, so you can see the proof, but that it's actually harmful in some cases. So I want to also give a bit of historical context from other fields. So other fields that use social choice theory, especially things in decision theory, things in AI, have studied order fairness in different contexts, especially with regards to model quality, or like how much you mutate a model by giving some fairness guarantees, and they get these impossibility results. The difference is model quality is a bit like MEV's economic value. There's still these kind of continuous magnitude objective functions, depend on the input data, depend on the particular thing you're inferring, but they all get these impossibility theorems. So why should you not expect that for fair ordering? Okay, so I've had my fun, but now we actually have to go into what it is about fair ordering that's so weird. So to try to dismantle fair ordering, what we do is we consider a two-player game. One player is the fair ordering protocol that is proffering a set of orderings of transactions that are allowed to be executed. And the other you can think of as an adversarial DeFi developer. So someone who is making a protocol that's trying to cause the fair ordering to give a worse value for the users of the protocol. The rough game mechanics are: nature draws a set of transactions, so that's users generating sets of transactions. The developer plays first and constructs a protocol, so think like a DeFi protocol, adapted to a set of transactions. And the protocol is a payoff function. So we'll talk a little bit about what those are in a second, but you can think of the payoff function as the expected value for the user. Then the second player, the fair ordering protocol, draws a set of permutations from the symmetric group, that's Sn, that's a set of permutations. And it draws it from a distribution P. And so one reason that we have this distribution is, of course, in most fair ordering protocols, there's some extra metadata, like the timestamps of when different validators receive certain transactions. That adds some randomness, and that randomness means that there's not a unique ordering. Again, Erra's impossibility theorem sort of guarantees that. So there's this sort of set of orderings, and it'll turn out that the size of the set of orderings controls how well the fair ordering protocol can win in this two-player game. And finally, a value V is realized based on these. So without getting too in the weeds, to the right, you'll see something that defines the value of a protocol P, which we can talk about via its distribution of orderings it generates. And we consider a min-max loss. So if you've seen sort of classical game theory, classical von Neumann, Morgenstern stuff, this is just traditional min-max. And there's a loss function, which takes in an ordering. That's a permutation pi in a symmetric group. and a payoff function f. And this loss function is meant to measure some notion of fairness. And we'll talk about how there are different loss functions will give you different notions of fairness, but you sort of want this game to qualitatively have the same winner, like usually the DeFi developer wins, for many loss functions, even if I perturb it. And so in this game, the value of the game, if the game is positive, the adversary, the DeFi protocol developer, wins. If the value is negative, the fair ordering protocol wins. And of course, this will depend on the loss function, but we'll talk a little bit about that. So why does this represent fair ordering protocols? Abstractly, again, you can view a fair ordering protocol as taking each validator's sets of transactions and some metadata associated to those transactions, like timestamps. And the fair ordering protocol outputs a single permutation of those transactions in the set of allowable transactions, H. But the thing is, there's many of these H, and the key thing we'll find out is that fair ordering protocols don't make H that small, and that's where the adversarial developer can take advantage of them. Again, the randomness comes from network latency, user demand, etc. And how do we bound V, this value of this game? Well, there's combinatorial constraints that arise from the set H. Another way of looking at this is, given enough noise or entropy in the sets of permutations you're allowed, you can almost surely construct a payoff where if I restrict to those sets, I get a worse value than if I am unrestricted. And basically what the proof does is we explicitly construct a DeFi protocol whose rules for when liquidations are allowed to happen exactly is optimized to be bad on these permutations generated by the fair ordering protocol. In fact, the liquidation rules draw a lot of inspiration from a protocol many of you might know, which is Liquidity, LUSD. They have a staking pool that auto-liquidates LUSD issued assets. And the only difference is that instead of giving pro rata rewards, we give fixed rewards, but it's a little bit more complicated to describe. And what this sort of says is fair ordering preferences particular applications. So this application that looks like a DeFi protocol that has particular liquidation rules has a worse value for users under fair ordering, which means that other protocols that have the same value, are sort of preferenced. And so there's sort of this very interesting thing that a fair ordering protocol is sort of picking winners and losers implicitly. So now the next question is, what is this notion of a payoff? So a payoff represents the economic value each user gains from a particular set of transactions. A user payoff is a function from the symmetric group to the reals. You can decompose any payoff into this kind of sum over indicator functions. And this, some of the end results we'll talk about at the end, which I'll just sort of give a preview of, rely on sort of some of the decomposition properties there. So what are examples of payoffs? One example is just an AMM payoff. And in this paper earlier, we analyzed sort of how MEV payoffs for sandwich attacks look under permutations and sort of get some bounds there. The other example is liquidations, and you can think of a liquidation as really an indicator function that's parameterized on a price and a threshold. So if the value of the asset's below some threshold, that's the indicator function, then you realize a profit, and if it's not, it's zero. And you can sort of look at this as a barrier option as well. So the real question is, how do you choose this loss function? Well, there's a couple of different ways to define sort of fairness. One version of fairness is the extremes. What's the difference between the best case ordering, like the one that maximizes social welfare, and the worst case ordering, the one that minimizes social welfare? That should say best, not Bayes. The other is sort of mean. So what's the deviation of a given ordering away from sort of the average? Like is a particular, how much do the orderings fluctuate around the average? We want to choose L, this loss function, in such a way to be robust to perturbations. And an interesting thing is that, for finite groups, there's actually ways to generate kind of lower bounds on things like V, like this value of this game that we talked about. These are uncertainty principles. They're sort of these finite group uncertainty principles are similar, but quite different to the uncertainty principle you might have learned in a physics class or a real analysis class. But the interesting thing is that you may now ask this question: is there an uncertainty principle for MEV here? And there's a very interesting, that's sort of the final thing we'll see, is that there's sort of this trade-off between how much you restrict the set of orderings and how manipulable a payoff function is, and that trade-off you has sort of this lower bound, and that's sort of this hidden cost and sort of complexity cost in MEV, which is the reason these fair ordering things sort of can fail. So now let's find out how much orderings cost. So the claim is, suppose I have the distribution P that generates orderings, and suppose that with very high probability, the size of H is omega of n factorial. That means it's a percentage of the total number of permutations. And if L is deviation from worst case, so the extrema, then you can show the value of the game is bounded by a positive constant, which in word says if the number of fair orderings is sufficiently large, then this minimax value is positive, and this sort of DeFi protocol we constructed always sort of does worse when you use fair ordering. Another way of viewing this is fair ordering is actually discriminatory to particular protocols. So you might say, okay, well, is it really realistic that a fair ordering thing generates omega of n factorial permutations? Shouldn't it just be generating like constant in the number of transactions? And where this logic sort of falls apart is if you actually look at random ordered elections, or random elections, and this was studied in 19th century by some actually French sort of philosophers who also did social choice theory, and this guy Guilbaud, who kind of proved this very bizarro formula that in a random ranked election with 3 candidates, there is a 91% chance that you don't have a Condorcet paradox. A Condorcet paradox is candidate A beats candidate B on a pairwise election basis. Candidate B beats candidate C on a pairwise election basis, but candidate C beats candidate A on a pairwise election basis. And so when you have those types of loops, then you have no perfect ranked ordering, and that's sort of like the simplest version of this. And again, to the credit of Themis and Aquitas and all these papers, they admit that this is a flaw of theirs. The problem is such a thing guarantees that with enough randomness, your set of orderings is still omega of n factorial. It's still a percentage of the symmetric group. And so that sort of says the hypotheses here are pretty likely to happen unless your timestamp distribution is really, really degenerate. Okay, so I've given you all this bad news, and a lot of it involves like game theory, math, whatever. Is there anything we should be happy about? And what I would say, maybe the positives you should take out. There are probably ways to do application-specific order preferences. So there are 2 results in this frame of mind. The first one, which released yesterday by Theo and Guillermo, is basically they looked at the kind of Arbitrum first come first serve mechanism, and they only looked at the top transaction. So they don't care about the whole ordering; they care just about the top transaction. And they were able to write a linear program, be able to bound its gap, and they were able to get a lower bound on the ratio of the price from the optimal ordering versus the sort of like first come first serve ordering, and show a lower bound so that it's always worse under some conditions. And so that's a kind of very nice simple version. It doesn't capture all MEV, but it kind of gets you at least kind of the minimum viable example. And then these papers from us that basically construct an uncertainty principle, and these uncertainty principles give you this lower bound. The uncertainty principles actually show you things akin to the following, where you can bound sort of the worst case part of the minimax loss by lower bound by a polynomial in something known as the Fourier degree of the payoff function, and also upper bound it in terms of Fourier degree. So what this says is you can actually control the fairness measured in these in sort of like the deviation from worst case by the is related how well you can actually achieve some fairness is related to the sort of inherent computational complexity of the payoff function specified by your program. And I think that's actually a really interesting thing, because it basically says, hey, there's a reason people optimize smart contract programs for being less complex. They actually have less of this worst case unfair bound, the upper bound in this case. So with that, probably did go over time, so I'll answer some questions in the chat.
We are running a bit over time, so I'll again just direct people. You can send your questions after the conference on that Flashbots forum link that we had posted earlier, and we'll all be checking that after. But otherwise, thank you very much, Tarun. I'm sure no one will ever try to do fair ordering again or call it that. And now we're going to bring on Tom for his next talk.
Cool. Hi, everyone. Can you hear me?
Yep.
Great. Sweet. Hi, everyone. My name is Tom. I'm a general partner at Dragonfly. We're a global crypto venture fund. We've done a number of investments and sort of been writing about MEV for a while. We're early investors in Flashbots. And, I sort of want to walk through, I guess, maybe more of a VC's perspective on what's happening in the MEV space. I think there's been a lot of discussion, a lot of research put into how do we design fair, order flow auctions? How do we incentivize people to, extract MEV in a way that is like not malicious? And I think the mechanism design research has been going on has been great. I think the problem, of course, is how do you make sure that the market recognizes maybe the outcome that we want, the mechanism that we want, and versus sort of having the market and sort of what the market decides be sort of suboptimal. And so when we started talking about is sort of the different actors that are circling on different parts of the MEV stack, and how we might go about sort of preventing any single actor from maybe seizing a part that we don't really want them to. So I think so far, all the sort of discussion around MEV, all the research around MEV has been sort of related to sort of the world that we live in right now, where users sign a transaction, it hits the public mempool, searchers see these transactions, they assemble bundles, send them to a builder, and then it eventually gets validated. And I think unfortunately, like that sort of state of the world is slowly sort of changing over time. There's this really good tweet from Block Native where they basically try to drill down and figure out, what percentage of total transactions that we see actually aren't going through a public mempool. They're going through some other method that sort of breaks our mental model of the world, such as a private mempool that would sort of necessitate a change in how MEV and the MEV supply chain is being structured. And so we found it at 3.8%. This is older. I think it's actually much higher, and I'll be talking about that a little bit later. And so the problem is, like, we can design really great auctions, but if we don't have incentives to encourage people to participate in the auctions, they kind of end up going to waste. And so this sort of gets back to this topic of like, I guess, block centralization and builder centralization. And actually, John has this really good flow chart talking about, so the inherent centralization and sort of positive flywheel of private order flow. And I would argue this is already kind of happening already, as we'll get into a little bit. And I think so far, again, kind of the discussion in the MEV community has been sort of finger wagging. Oh, this is bad. Oh, we shouldn't, have private order flow. We shouldn't have this sort of centralization of builders. And instead, I'd like to sort of, think about it more in the sense of, well, how do we encourage and incentivize the people who maybe are privatizing order flow today to make it public and sort of get back to this sort of censorship-resistant, decentralized, open world that we want to sort of live in. And so this is very somewhat famously, classically, Stefan's MEV supply chain, going from user to wallet to searcher to builder to validator. But I would argue this, again, is like almost too abstract. And this part right here is actually kind of where all the activity is happening right now in the MEV space. And one thing you might notice from the supply chain is that basically the further back you go in the supply chain, the more leverage that party has. So the wallet actually has a lot more leverage over the searchers, and the user actually has a lot more leverage over the wallet. And so this isn't quite as simple as sort of how we think about transactions historically. And so to get into this, we'll sort of break down, classically, how does a transaction get formed? So you have some sort of UI. They send a signature request to the wallet, to the Web3 provider. The wallet then asks the user to sign. You get one of these little dudes. You click OK. The user sends the transaction. The wallet then sends this signed transaction to an RPC endpoint. And then that enters sort of this public mempool. It gets routed across all these different nodes. Eventually, either through the traditional means of just validator finding it, including it in its block, or a searcher sending it to a builder and then getting it included in the box. It somehow gets validated, and then the dApp sort of updates its UI. But all these sort of different components of this life cycle, they all want to increasingly capture MEV for themselves, and this flow sort of started to break down. And so you got some memes that kind of describe what's going on a little bit. Just got to get these out of the way, unfortunately. And so there's a couple different camps here, and you can see why every different camp, every different stack will sort of conceptualize why they actually think they deserve the order flow and why they're actually trying to go after it. So I think right now a lot of people think of order flow, they think of RPC providers, and there's been a lot of effort and a lot of development being put into having a sort of custom RPC provider, which we'll get into some examples in a little bit. I think in practice, this is like a really tough entry point for new companies and new projects. A lot of wallets won't even let you choose your default RPC provider. This was not the case for MetaMask until recently. It's super clunky. Users don't really understand what's going on. I think there's also even questions around how this actually monetized and how this actually gets paid. But in concept, one sort of way of entering the supply chain is basically, when the wallet actually sends the signed transaction to an RPC, I'm not just gonna send it to sort of the conventional ETH mempool. I'm actually gonna sort of replicate what that interface looks like and then do something kind of funky with the transaction. So one angle here is you sort of convince people to use your RPC because you sell them on some sort of security angle. So Harpy, which is a Dragonfly portfolio company, is going down this route. So you can send them all of your transactions. You can send your RPC to them. They intercept and scan every single transaction. And depending on the level of security that you choose with them, they can either ask you for a 2-FAC for every single transaction. So they'll email you or they'll text you and have you approve the transaction. Or if it's something that their simulation picks up as potentially, scammy or malicious, then only then will they actually, ask you for 2-FAC. And so it's sort of this nice little add-on or module into how people use an RPC today, which is again just sort of you blast it into the mempool and sort of hope for the best. And I suspect this is kind of the path that like some of these other simulation tools are also kind of going to go down of basically, hey, I'm sort of like Norton antivirus. Send me all your transactions before they hit the public mempool. I'll make sure they look good, and then we'll sort of send them on. Another way to sort of think about this is RPCs that go after this sort of ease of use. So it's all these usability UX wins that in aggregate just make it strictly superior to just sending it to Infura or someone like that. So example would be GasHawk. They basically try to model out gas price fluctuation and then send your transaction when gas prices are lower and sort of save you money and sort of pocket some of the spread. It's even something like Flashbots Protect or the 1-inch rabbit hole. They wait to make sure that you're not paying for failed transactions. You can pay in arbitrary fees, etc. Both this and the previous category, in theory, should be strictly superior, and everybody should use them just using a standard Infura, for example, RPC endpoint. But for a lot of the reasons that I mentioned earlier, it's just really, really hard to get people to switch over if they can't even switch over at all. And so this sort of goes back to this other option, which is, well, instead of having users switch their RPC over, what if we just sell directly to wallets, right? Because wallets, again, they're further up the supply chain, they have more leverage, and then we'll integrate with them directly. So in concept, this is great for wallets, right? It's a new monetization path because you can sort of benefit from some of the MEV that your users are generating. You can outsource the MEV extraction to somebody else. So maybe it's a bit simpler for you logistically or from an engineering perspective, or maybe users are actually going to get some of the MEV directly as well and sort of create stickiness. And so we're seeing some development down that path as well. But ultimately, this all is sort of, again, downwind of wallets. Wallets really have a lot of leverage over which RPC endpoint an order is going to get sent to or a transaction is going to get sent to. Wallets, obviously, they need to monetize. Not everyone can have sort of the MetaMask swap style money printer. And so they're all looking for ways to sort of think about alternate sources of monetization. Wallets also have really great order flow. Not all order flow is created equal, right? Like order flow from a bot MEV or order flow that is toxic, order flow from a professional trader that might have some sort of alpha. That's not something where there might be that much MEV that you can extract. But if you're catering to people who are less price sensitive, less time sensitive, that is actually order flow that can generate a lot of MEV, and therefore is pound for pound more valuable than other types of transactions that you see. So again, this is a sample from MetaMask where they're even starting to pursue this method of sort of swallowing up the RPC providers, and instead of having their own layer on top of them, where they can, again, provide a lot of these UX security benefits as well, but also potentially extract MEV. So before stuff even hits the public mempool, they can sort of do whatever they want with it. They can do it themselves. So it's like a tweet interaction between Bert and Mike from Rainbow from a while ago, discussing the idea of, hey, what if Rainbow actually just extracted MEV from user swaps itself, or partner with somebody else, or potentially auction it off, which is I think how a lot of people conceptualize it. The question is like, what reason do they have to do that, and how do you sort of make those economics actually work for wallets? You have to actually cater to them and sell them a product that they want because they have so much leverage in the ecosystem. I think the silver lining here is I think wallets are actually finding that just charging on these sort of swap products is actually a much better monetization strategy than MEV extraction. And so it might just be that they might sort of leave some juicy fruit sitting on the table instead of trying to extract it themselves, because there's so many other ways for them to actually make money. Again, all this sort of discussion so far has been sort of presupposing the current sort of stack, right? Like the RPC providers sort of assume that users will be able to switch their RPC endpoint, and wallets are sort of assuming that, well, I will actually be able to receive transactions from users. And that, of course, is also changing over time, as we're seeing that like sort of the conventional way people sign and create orders is actually changing. So this whole sort of bit is kind of what I want to drill into a little bit. So dApps really kick off this whole process of a user clicks something or taps something on a UI, and then the dApp says, hey, wallet, please sign this transaction. But the transaction itself doesn't have to be a conventional Ethereum transaction. It can be an intent-based transaction, right? It can be like a OpenSea order or like a 0x order, or this is the case from Sushi, where you're basically signing a hash that represents your intention, and then that doesn't even enter the wallet. Like there's no transaction to relay. That just goes back to the dApp, and then the dApp can do whatever they want with it. So in this scenario, Sushi has a partnership with Manifold, where they have this product called Sushi Guard, where basically when you swap on Sushi, you sign this intent, it goes to Sushi Guard, they can extract MEV from it, and then that can go back to Sushi. So the wallet doesn't actually see the transaction in this flow, and therefore the RPC providers don't even see this transaction. I think this is kind of not optimal because it's really confusing for users. You don't really know what you're signing. You're signing this hex, which can obviously, as we've seen with sort of the permit style attacks and other types of attacks, actually be malicious in some scenarios. So people have been sort of conditioned to be on guard when they're signing a transaction, less so when they're signing a message. But a message can, given certain conditions, also be kind of malicious. And of course, this also sort of depends on the dApp. So a lot of dApps, obviously we're talking about the protocol layer as well as maybe the UI layer. It really depends on what percentage of your volume, what percentage of your activity is going through your first-party interface or versus third-party interfaces. So if the majority of your volume is going through an aggregator or a third party, or maybe just bots, you probably don't actually have that much leverage in terms of how do transactions actually get generated. Whereas if you have a great site, or maybe you are slowly vertically integrating and creating your own wallet or creating your own app, you actually have a lot more leverage in terms of again choosing where orders are being routed and sort of where order flow is being generated. So this is like a screenshot from Thicky Thought, who's one of the founders of Friction, basically looking at the percentage of toxic order flow on Uniswap, which you can think of as sort of a rough proxy for the percent of volume that is going through or not going through the Uniswap UI and instead being generated programmatically or going through some sort of third party. So I think, zooming out a little bit, all this is to say that the sort of the land underneath MEV world is shifting pretty rapidly. And so, building a product that assumes that people will be able to find a transaction in a public mempool and then, engage in some sort of searching process for it, I think is not probably going to be long for this world. So the question is, how do we make it EV positive for these different players to cooperate and participate in an open auction that is fair to users, as opposed to relying on their benevolence to not generate malicious MEV, not self-extract. You don't really want a world where the majority of transactions are going through MetaMask. MetaMask does self-extraction, and then they also maybe become a builder, and it becomes all vertically integrated, which is kind of the trend that we're seeing. I think there's also a question of where will that MEV actually end up? Obviously, everybody's trying to go after it, but there's also a question of why doesn't this end up with users? There are efforts to push the MEV that is being generated back to users versus going back to an RPC endpoint, going back to a wallet, or going back to a dApp. But I think that ultimately relies on competitive pressures across these different players to do so. No one would willingly do it, but it's sort of like credit card points, where if everybody else is giving some sort of kickback, you're sort of forced to do so as well, even though it sort of hurts your bottom line. And then I have a research piece coming out soon that sort of has more data on trying to map out and quantify the public mempool or the private mempool problem. But if you want to collaborate, feel free to DM or email me. But I think in my mind, we're sort of in a state similar where we were maybe 2 years ago before MEV Explorer, where we know there's a problem and we have some sort of little snippets, through different papers or through one-off research pieces, but we don't really continuously monitor this or track this. And, based on some of the anecdotes as well as some initial data, it seems like it's a growing problem if we want to live in a world where, there aren't all transactions aren't just going through a private mempool effectively. So ultimately, I think when we sort of look ahead, the big takeaway here is the people further up the supply chain have more power. And so naturally, everybody is trying to move further up. But it's tricky given some interests are sort of already entrenched. And so, everybody's acting really rationally. Nobody is trying to be malicious here. And so we can't just really finger wag and say, hey, you should not be privatizing order flow. You should not be self-extracting. Instead, we should make it economically reasonable and rational for them to give up their order flow and participate in an open auction. And I think that's where I'd like to see more sort of discussion happening versus just sort of assuming that it will happen. I think things like MEV Share are a great step, and obviously make it more accessible for people to participate in an open auction. But I think ultimately the question we need to make sure we're answering is whether or not it makes sense for these different actors to open up order flow to an open auction versus, again, sort of keeping it private. So that was it. I kept it kind of quick. Happy to answer any questions if people have them. Actually, I realize I don't even have, I had to close the tab so I don't get echo, but happy to answer questions.
We are running a bit on
or the time. That's right. I always forget.
We're still behind on time, so we are just going to move over to Quintus. But thank you, the viewers who are confused by Tarun's equations. Appreciated the break on this one, and we will turn it over to Quintus now, who's going to talk about cats. I think.
Can people see me? Can people hear me? Am I going now?
You're all good.
Okay, cool. Okay, hi everyone. I heard there's no Q&A because we're running short on time, so I can say whatever I want. So hi, my name is Quintus from the Flashbots research team. Today I'm talking on auctions, privacy, and a cat. And my motivation is sort of to take this discussion about MEV and this discussion about distributing MEV back to users and ground it in like a mechanism or like a class of mechanisms that people have been talking about implementing. And so the real point I'm trying to make is that the design space is bigger than we realize, and there's much more to explore, and I'll sort of give a direction in which we could go further. But first, like a brief overview of what I mean when I say a mechanism for distribution. Okay, so starting from basics, we have a user trying to interact with a blockchain or blockchains. In this case, I just put Ethereum because it's easy to think of. Right, and so the user has some intent. Something they're trying to accomplish on the chain, but they don't understand how the chain works. Most of us don't understand the intricacies of it, and don't understand what the best way of interacting with all the different smart contracts is, etc., etc. Similarly, the mempool is very hard to pass. Many different transactions in there. It's pretty much only like searches and like a couple of like very like technical parties that can reason about this well in the time frame required. And so the user's confused. And that's like me and you. And here the idea of an auction comes in nicely. I am just giving it my own definition, which is a mechanism for price discovery through competition. And then once you think about it for a little bit, it doesn't have to be price discovery. It can just be discovery, like in a reverse auction or something. It doesn't have to be a price that people are competing on. And that makes a lot of sense here because we actually need some discovery because we don't actually know how to do what we're trying to do. And so the sort of beautiful end case would be to have this magical auction in between the happy user and the blockchain, solving all of our problems. And that's the direction we're going, or I'm proposing we go at least. Right, and just to be clear, when people hear auctions and MEV, they think of PBS usually. That's not what I'm talking about, right? This PBS and the searcher, like build a relationship and all these things. That's like it takes part of what you can construe as like one large auction where the beneficiary is the proposer. But really, like the mental model I'm working with is like an auction that logically precedes all of this, where the benefactor is the user. Right? And of course, like in implementation, these could be much more integrated, and maybe like if you really want to reason about this perfectly, then you should think of the whole system as a whole. But for now, we're just going to focus on the order flow auction, which is the green bar on the left, if you haven't caught on yet. And so, just to give you like a rough idea, I took a slide from a presentation I gave at ETHENVA with like one taxonomy you could give, breaking up the different archetypes of auctions. And like this really isn't like super rigorous, and you can definitely propose a different way of dividing things up, and maybe it'll make more sense. But just to give a rough idea, you can have these kind of like auctions, which I just label here as a priori, where the winner is determined like way in advance. It resembles sort of like TradFi, PFOF, and these kind of things. What I've called auction house, because I don't have a better name for it, but that's not an official name. And there's like different variations where people bid either on like single items, right? And these items are going to usually be like users' intents, right? Among other things, but like it's the items are related to the user's intents because the user's trying to execute something on the chain, and that's what we care about, right? You can have combinatorial auctions where people can bid on subsets of items, and batch auctions are somewhat of a continuation of this, where the batch is fixed. You can't like pick and choose a subset, of course, with some caveats. And then Dutch auctions and like I guess English auctions and whatnot are all run over time. So anyway, so this is like one way of dividing things up, and I've explained it all to you, and thank you for listening, but it's not what we're doing today. So the point I'm trying to make is that there's an argument, or so there's a dimension that is missed in this taxonomy that is quite interesting, and that we should be thinking more about. I think it's like a large design space we haven't really explored much, and that's kind of like control over memory. What does that mean? Well, if we think about, that's not good. So there's supposed to be some little robots over there, but I guess they're not showing. I guess maybe it's because you're making me run Chrome. Anyway, just imagine at the end of these bubbles, there are a bunch of robots. The point I'm trying to make here is that in an auction, the idea is to communicate that an item is being sold to as many bidders as possible because we're trying to get up the competition. And of course, they need to know about the item being sold to bid on the item. But I'm going to argue that this is actually not desirable and also not the only thing that we need to do necessarily, or the only thing that we can do to have this discovery through competition mechanism. Okay. So in order to do this, I'm introducing another character, or I guess the first character in the story, Schrodinger's other cat, right? With half a sibling in expectation, I guess. And again, we have the same setting with the bidders, which are now invisible, but I promise they're there, and an item which is being auctioned over. But now we introduce as well a cat and a box. And the cat here acts as a auctioneer, and as you can tell by its hat and stick, it is a magical cat. And so the cat controls all of the actions taken in the box, and more importantly, it also controls the perimeter of the box. So what this means is that the cat can control what information leaves and enters the box. So what can we do with this? And again, you can't see it, but there are a bunch of bidders outside the box, I promise. And there are bidders inside the box as well, which you can't see. But the idea is basically that the cat can allow bidders to submit emissaries, copies of themselves, right? If we're talking about bots or some version like that, that can do the bidding on the auction for them. And so the idea is that you inform all of these emissaries on the inside, but not necessarily the bidders on the outside, what's happening in the auction. If the boundary of the box is fully transparent, the outcome is that at the end of the auction, all of the bidders outside of the box are fully aware of what transpired in the auction. What the item was, perhaps even who won the item, what the largest bid was, who knows, but there's at the very least, they're aware that this item was auctioned off. But this may not be desirable. And there's some other outcomes which we could have as well. Like, for example, we could have an outcome where only the winning bidder is aware of the item which was auctioned off, right? Or going even further, no one is aware of who won the item until some other point in the future, and the actions taken on the item are taken within the box. Now that's very abstract. So to make it a bit more concrete, let's imagine we're auctioning off a big trade. Someone's trading a very large amount of a shitcoin. They're going to move the price. There are different variations of how we could do this, but let's imagine we have some sort of RFQ system where bids come in the form of commitments to giving a certain price, right? And so these emissaries within the box offer their different prices. Well, what happens if the barrier of the box is transparent? Well, at the end of the day, the winning bidder now has to execute this order, but the knowledge that this order will be executed is now public, or at least many entities are aware of it. And so there's competition to execute this order. If they're going to move the price, maybe someone else is trying to price this in, and it's not desirable, or it's not the best conditions for this bidder. And so they might actually want this information. They'll have to price in this competition when they give their bid, knowing that when they're trying to execute this order, someone else might have already tried to price it in. If we change the setup so that only the winner is aware that they won the auction, they're the only one aware this big order needs to be executed, then the situation is much more favorable for them, and that should mean that they are able to bid higher in the auction. But let's imagine that Do Kwon is actually swapping on Uniswap, and he's asking to be backrun only. That's one of his conditions of the auction, or maybe that's what the auctioneer wants. I'm leaving aside the question if that's actually the setup we want. Well, in this case, the cat has no control over what's actually happening outside of the auction. So it's very hard to see if the bidder is actually, what the bidder is going to do about the auction. However, if the outside bot or bidder is never made aware, or is only made aware at some point in the future, what the outcome of the auction was, and the action taken on the order, like the formation of the bundle in which the order is executed, happens inside of the box, then the cat has control, and we can make sure that the bidding is along the lines of this user's utility function or whatever it is. To put it like plain in this example, there's no front running, right? Similarly, we can think of an Oracle update. You can imagine many people are lined up for liquidations, and the Oracle sort of like on the cliff. We don't know if they're going to be liquidated or not. If the auction's running in the clear, all of the bidders are aware of this Oracle update, whether the people are being liquidated or not. But only the winner is able to like backrun it, for example. Right? However, if we make this barrier, less transparent, somewhere else on the permeability spectrum, and only the winner is aware of this, they now have incentive to bid more for this information as well, because it gives them an edge in the market. They know something that their competitors don't, their competing traders don't. Right. And so I'm running out of time. So just to briefly go over like the kind of things that I covered here, what we can do with information. One is we can select for desirable competition that drives up revenue, but not competition that is detrimental to the users, the user's wishes or their intent, right? Monetization of information, like the Oracle example covers that quite clearly, I think. And then like control over action taken on information, right? If we have control over what happens inside of the box but not outside, if we can keep sensitive information within the box, then we can stop things which we don't want to happen from happening, right? And I gave a very specific instantiation of like the cat in the box. But actually, like the point I'm trying to make is that we can combine many boxes, we can combine many cats. You can get dogs, you can get triangles, you can go crazy. My point is that there's like a lot we can do with privacy and like how information flows and how we control things. That cryptography and distributed systems have allowed us to do, and we haven't really I don't think we've explored the full design space, and so it'd be interesting to see what people come up with. So that's why I always say it's not if you know, you should ask yourself, what action can I take on what information? And that's pretty much it. Over time, I think. And so just highlighting a special cause. A lot of homeless cats out there. Do your best to donate or adopt. Cool. I think that's it. There we go.
Awesome. Thank you. We're still waiting for Daian to join in just a minute.
Questions.
Yes. So you probably get one or two. One of them that was asked is, how do you control information access here without leaking?
So I think the answer, which I guess so here's one very basic example, right? You could just have a bunch of people submitting scripts which are encode their bids, right? You take as input the item, you give as output the bid, and have that run on the server, and some trusted party calculates the bids for these people. That's one way of doing it. A lot of trust assumptions there, and then you can scale up Flashbots exploring the SGX route, either via one central SGX. I'm not a cryptographer. I'm not going to talk about the trust assumptions there. But then moving outside of that, maybe you can have multiple parties running these SGXs. Maybe you can have the bidders themselves running different instances. I'll leave the answer there before I say something that doesn't make sense. Yeah.
Well, that's perfect timing. Daian just joined in now. So thank you again, and we will go over to the next one. Thank you, Quintus.
Thanks, everyone.
And next we have Daian, who's going to be talking about quantification of MEV sharing design and order flow options.
Hey, everyone. Just give me 1 second to find the right link for. Okay, great. Cool. All right, sharing screen. Cool. Okay. So hi, everyone. My name is Daian. I'm a data scientist at 0x, and we are a DEX aggregator platform where basically we handle users' intent to trade across DEX and access the AM liquidity, which is where MEV happens across the DEX or MEV order flow. And that's why this is very interesting, topic for us. And this presentation is more of an open research in collaboration with Flashbots, and a lot of data are coming from Flashbots, and also I can find. So shout out to them. And so for my agenda today, I want to share more like about, first of all, what's a MEV sharing workflow look like? Let me check the chat. Okay. How does the workflow look like, and what are the roles there, and what are the values there that we try to identify first of all? And then is like, how is the MEV revenue split across each row today? And we will review some numbers that can potentially have an overlap with what Ellen shared earlier. So I'll go quick there. And then next is that looking at this funnel of this revenue split, where can we potentially quantify and extract the user share back potentially? And we will share two approaches here today. One is by looking at the searcher's on-chain profits. The other one is by looking at the validator's bid surplus, or sorry, this is actually a typo, builder's bid surplus. So this is a, how to say, like a diagram of common workflow of OFA today that we learned about. So basically, we have this user have an intent behind a dApp or a wallet, or you can say also RPC provider can be also the entry point. And then they want to make a trade that's accessing AMM liquidity. And then there potentially will be this OFA or like a MEV share service, potentially. We can call it matchmaker or solver or resolver. And then they will send to a pool of searchers, and the searchers will try to bid for this transaction to basically send a bundle with bids, and so to win this transaction. And if there is no searcher response with this transaction, potentially this service will just fall back to the mempool, so to make sure the execution quality. And then once the MEV share service figure out which is the highest bundle, which is the highest bid for this transaction from one of the searchers, they will send bundles towards block builders. And then there is this normal flow of block builders bidding for a block towards the validators through MEV boost. So there's a bunch of like variables or like numbers we need to identify first. So first of all, there is this, now we're talking about how much potentially revenue for user can be from this whole MEV flow. And potentially in the future, we will see probably MEV share service as a middle layer will take potentially a fee as a batcher revenue. And then we will see revenue from searchers that kept to themselves. And for this part, potentially we can see some of them that's on-chain, but a lot of them can be potentially unknown or off-chain, like, for example, like across centralized exchange and DEX. And then next is like how much revenue builders will keep. And then we will see relay, but most of them, basically as of today, there's no revenue for them. And then there will be the revenue for validators. So to summarize this whole thing into like one table, we have this like table here basically to summarize all the rows, and it's sort of like a comparison of like how it was in the past and then right now with MEV Boost as present, and potentially in the future with MEV Boost and also OFA sharing design in the future. There you see like more and more people are taking this piece of cake, and we will see how we can potentially split further. And this is on top is a simplified, how to say, workflow that's from the order flow auction article from Frontier Research. So one thing very clear here is that basically searcher now is, how to say, segmented or separated from directly accessing wallet or builders, but through the order flow auction. So to look at the numbers or basically trying to quantify the scale or total values, we want to look at this funnel chart here that I'm trying to propose for framing all these things. So first of all, what's the total MEV here? Potentially there is an unknown part that's off-chain we won't see ever, that's kept to searchers. And then the visible parts on-chain potentially we can see is what we'll call it like on-chain profits from the revenue for searchers. And then after that, the next step in the funnel is how much they given out to builder and validators all together. We will basically have that data from MEV Boost proposer, payouts, rewards data. And then the next is after the builder layer, there's another layer of bidding markets, which is bidding for block. The previous one was for bidding for bundle. And the next is, so we don't know for sure how much builders want to keep or given out. But as of today, it seems like most of the builders will be competing to give most of the rewards to validators. And potentially there could be a extra amount that's outside of this whole MEV value that can be coming from builder as subsidy. So this is a funnel of how this value actually is split step by step or extracted step by step. So let's look at how big are these bars are today. So quick revisit on some numbers that Elaine mentioned earlier, and this is also a call out to her slides here. which is basically emphasizing again that we will not have a way to pretty much know how much is happening on centralized exchange or DEX. What we can see is how much on DEX and across DEX platforms. And centralized to centralized exchange is also another sort of MEV, but this is outside of the scope of our discussion today because we're talking about how much we can potentially give back for DEX users. And the centralized to centralized exchange MEV isn't involved with any intent from the DEX users. So yeah, next data is coming from Eigenfi, and this is a pretty nice breakdown of different type of MEV. We can see that like on this scale, we can see roughly like around daily of 50K to 100K of MEV on-chain profits that can be attributed to the searcher's addresses. And apparently this is definitely will be under-indexed compared to what's really happening in the reality, because based on all the heuristics, it can only index, for example, like atomic. So there can be a lot more to be indexed. But next is like, so we want to look at how is the split across builder and validator. And it could be pretty tricky because of different type of behavior patterns of builders. So I think a normal flow as how we are looking at on the data of the builder's behavior is that a lot of time searchers will put the Coinbase transfer, which is basically a payout of the MEV address to builders. And then builder as the person who is basically the fee recipient on the block is like basically the fee recipient of the gas fees. And then basically builders can potentially collect all of them, but then decide how much of them out of all the total they want to transfer to validators. So we will see a transfer usually at the end of the block, which is the payouts builder goes to validators. So with this approach, we can potentially index, but there are some sort of like different, I would say, behaviors from some of the builders. For example, we could see some zero profit builders, like they just don't take anything. And usually sometimes searchers can also skip builders. They just put the validator's fiat recipient directly in the transfer in the bundle. And builder will also sometimes just put the fee recipient of the block as the validator's address. So in this case, builder is not even shown in those block production, but actually they were actually handling the block. There could be also builders that's actually subsidizing. For example, they can just give the gas fee, set it to a proposer's fee recipient address, and even an extra transfer at the end of the block. So yeah. And so I was gonna say basically it's pretty tricky to split the the split between builder and validators. So we will basically just look at them together as a whole and look at the scale. So this is like just like generally when we talk about like a daily total of how much proposer revenue look like. It seems like there was some interesting difference compared to end of last year, which is the first 3 months of MEV Boost Alive, and then also the first 3 months of this year. The daily was around 600K, and now it jumps to like 1 million per day. And then I did some cross-check with the data on MEV Boost. It seems like they also have this same scale shown. And then so using another piece of data from MEV Inspect, where we can clearly see how much is the transfer out is versus how much they keep. It's also interesting to see like this clear timestamp cutoff, where like in the last 3 months of last year, the split was more of like 70% to the searcher and 30% to the proposers as a whole. And then starting from beginning of this year, it totally changed to another, like basically shifted towards much less for searchers, but much more for builder and proposer together. So these are some basic numbers that we know as of today. Next question is like, okay, now as all the application teams and wallets who have the direct access of users' order flow, thinking about entering and potentially take more autonomy on users' order flow, where and how much, like where can we even extract users' kickback, and how much would that be? So thinking around these questions, I think there is a few things to point out that can be potentially the data that's also accessible that for us to be able to quantify. Looking at this flow again, one thing we can know is that like when the order flow auction take the order information from the application team or the users, they will be able to also know maybe how much the user already request or they want to be shared back. So user can potentially share a request of how much they want to be shared back and deliver that information to the bidders or basically searchers here. And so to see how this whole thing play out. With one thing they can account is basically if they are able to see all the on-chain profits from the searchers, then they can potentially even say, hey, I'm an exclusive order flow. So like it's only plus value for you. So can I just get like 99% back? It's possible. So we're estimating more like an upper bound here. And then the next place where we can see actually some sort of number that we know for sure that can be potentially enforced is at the block bidding market, which is when the block builders are bidding across competition to get validators get their blocks. MEV Boost actually have this open data set from the relay that they know what's the submission of all the block builders look like. And one thing we can know is that like basically the first bidder and the second highest bidder, the difference we can call it potentially as like a bidding surplus, where if we subtract that part, the top bidder is still the highest value validator can access, and they will still accept the block. And so that's a potential value that we can basically cut and give back to users. So to fit the ideas into this funnel chart, we can basically see like one thing is OFA infra can potentially allow user to request some share that's visible on chain when they are giving out the order flow information. The other is like MEV share infra. Oh, sorry, that's actually MEV Boost infra can basically cut and return a surplus of the highest bid that's above the second highest. So now we have this two approach to potentially quantify how much MEV reshare can come back for user. First thing, let's look at this searcher on-chain profits data. It doesn't really matter the scale here because, as we said, it can potentially be under-indexed as well. But when we look at the margin on all these, arbitrage profits out of the total trading volume, we actually are able to quantify, like say, how profitable per MEV attacked transaction or MEV victim transaction can be, or basically how much MEV can be extracted on a margin like bips base per transaction. And we can see actually like it's interesting to see arbitrage in general is can be potentially more higher margin than sandwiching, and but on like a median stats. But then when we're looking at like the higher bound of 95 percentile and 99 percentile, there seems to be coming into the same trend. And these numbers can be like huge variance for for example, like the median looks like around it's 3 bips, and 95 percentile is around a few hundred bips, and then 99 percentile, which is basically the upper bound or like the max number, is around like 1,000-ish. And then if we look at the breakdown of the margin distribution, we actually could see like at least clearly half of the trades that were attacked by basically MEV bots can potentially produce 0 to 5, which is like we know the median is 3, and so fall into this bucket, it's around like 5 bips at most. And so Tina asked us to put some number here, so I'm just putting some bold numbers here. If we think about concretely, say now the wallets are actually entering the game, and based on their base volume per month, if we look at this like 2 biggest players, for example, if you have like around 200 million volume per month, user can potentially expect a total of like say 100K based on the 5 bips point data set. And potentially maybe 2 million as like a really huge like upper bound kind of estimate using the 100 bips that we saw on the 95 percentile. And if your platform has like a 1.2 billion volume per month, then the number can go up to like 600K on a 5 bips estimate and 12 million on 100 bips per like bold estimate. So, but caveat here is that this is like a totally an upper bound because it's not all the base trading volume will be MEV extractable, because like say it's like super small trade of like $2, and I don't think that can really produce like even 5 bips of MEV value. So yeah, this is an upper bound. The second approach we want to check is basically the block bidding surplus. And on the right side, this diagram shows like what that means. Basically, on each slot or like per block, all the builders, they have like the latest bid, and we will check like what's the highest bid per across the builders and what's the second highest bid builder. And then the difference between them, as we described earlier, is considered as like a bidding surplus. Basically, if you extract any percentage out from the highest bid, it will still be the highest bid, and validators had no other choice but to accept it as it's still providing the highest value for them. So this is a methodology. We will check the freshest bid from each builder, and then take the highest two bids and take the the difference, and that's like a estimation of the surplus for users kickback. And then caveats is that it's definitely a lower bound. For example, we could say like, why not just take a higher percentage of all the payouts for the proposer? And second of all is like, it's probably a very practical and enforceable portion that can be implemented through MEV Boost. So yeah, trying to look at like how much is that BIP surplus look like. I've encountered some limitation on working on this data set because it's too big. So I had to actually take only every time a slice of data of like a day. But then like I checked across time frame, and they seems to give like a pretty consistent number here. So averagely, actually, we can see like per block, the reshare estimate, which is basically the surplus amount between the first and second bid, is around 0.003 ETH, which is $5 as the price of today. And the median can vary, vary around like $1-ish. And then if we look at like 1,000 blocks, it will be around 2 ETH. And then if we just do some paper math, it will be like 25K per day. It seems like not that exciting, but it's like a lower bound estimate. Another way to look at this is basically, okay, what's the percentage of this surplus outside of the the total amount of the highest bid, which gives the answer around like a 3%-ish or like a 2% to 5% range. Seems like out of the total bidding amount. So yeah, it seems like they're giving us a sort of like a pretty consistent result. So what does that mean here? So if you want to put some concrete number here, if we look at like a DEX trading volume total flow, and say just quantifying by the percentage of the DEX market share you earn, say if we look at the total bid surplus per month, basically across all the blocks in that month, the total will total up to like 750K. And if you own 5% of the DEX market share, you will get like 37.5K. And if you own like 50%, it will be having like 375K. Again, it's a lower bound. It's the enforceable part that's coming from the block bidding layer. So putting them all together as a full picture this is what I'm like thinking in my head or to share here. When we look at that MEV revenue split chart again, we saw that shifting of the 30% for proposer to 70% of today. And if we just put that 5% of surplus bidding as a purple part, we kind of like can split them further into the numbers that we can quantify here. You would see that the bidding surplus as a lower bound estimate for daily will be 25K, and then monthly will be like 750K. And if we and then on the builder proposal revenue part, I put like a red X% question. So that is like the part that we don't know how much we can request, but potentially you can put a number there. But then the search on on-chain profits part is like through the OFA design, we know that users can already specify how much percent they want to give it back. So that's like a green X% mark there I put. If we total them all together as the on-chain visible MEV revenue, we can see a daily of 1.4 million as a upper bound, and then a monthly total of 42 million as an upper bound. Nice number. And then another thing to point out is definitely the iceberg part that's below the water, or basically off-chain. We will never know how much that will be. I think there are some simulation potential sort of service that can potentially run across a centralization exchange versus DEX, and so to tell you potentially how much that is. But I don't think that data is like going to be very widely accessible in a near term. So I put a question mark there. And one thing to keep in mind is that like potentially with this OFA design coming up, this how to say iceberg percentage versus the one that's above the water can be changing as well, like shifting up and down. So yeah, that's a full picture of the numbers that I've studied on this topic. And last notes is thanks to Eigenfinds data, Flashbots data, and Tina, Elaine, Sarah, Xingyuan, and Robert and Tom for the help. This meme here, I just want to show that like I think from the user's perspective, like this is our MEV. We want to get a percentage back potentially because we are the value originator. Thank you.
Love it. Thank you so much. Again, we're not going to have time for questions, so we are going to move right on to the next presentation. We're going to have Kshitija talking about staking, lending, and MEV.
Excellent. We'll just can you see what I'm sharing?
Yep, you're good now.
Great. So yeah, so today I wanted to talk about sort of this idea of MEV redistribution and what it means for the economic incentives of validators. I wanted to present sort of a very simple model that might help us think about where this MEV revenue should go and how it should be redistributed to validators. So roughly, the model is that we have sort of these validator pools or sets of validators that are facing different sources of return, from where they can earn money. For example, they can earn rewards from staking. They can participate in lending. Of course, there's MEV, which is sort of the topic of this conference. They can engage in staking derivatives. There's this whole variety of places that they can collect returns from. And the frame that I want to sort of have for this talk is that they're going to view how much they participate in each of these different sources as a portfolio. So they're going to hold a portfolio over these different sort of sources of return. And in effect, what this means is that there's competition between these different sources. And so this is not a new idea. This is sort of going back to work on a security of proof of stake protocols, maybe all the way back to 2018 or 2019. But there's this idea that these different sources of returns are competing with each other based on the portfolios that these validators are constructing. But sort of the really important thing to note here is that one of these sources of returns is not like the others, because staking serves sort of a dual purpose, in that it's a source of return for the validators, but it's also securing the chain. Staking sort of acts as a privileged source of return because it controls the economic security of the underlying chain, and at the same time is competing with other sources of returns for the validators. So I always want to have this frame in mind that we have this portfolio, but sort of one part of this portfolio is important in a way that the other parts are not, because it's securing the chain. And yeah, so there's this question, which is, can we use MEV as an incentive to, in some sense, improve the security of the chain, or other desiderata that we might have, and can MEV act as some kind of an economic lever to induce security, and can it be used as a way to get validators to avoid some bad economic equilibria that might arise? So we want to answer this question, so we should just set some terminology. So we're going to have sort of this very standard model of a proof of stake protocol, which is going to hold some token supply, denoted by SFT. It's going to have some reward inflation schedule given by RFT, and then it's going to hold some kind of frozen liquidity. You might think of this as liquidity that's either protocol owned if this epsilon is positive, or it's burned if epsilon is negative. And then you have a very simple sort of update for how the supply changes over time, which is just you take the supply last time step, you add however much reward got inflated, and then you add or subtract the protocol owned or burned liquidity. And the perspective we're going to have from the validator side is that, again, they're viewing this as a portfolio optimization problem. Right? They're thinking about, I can collect returns from all of these different sources. What should I do? This is, again, sort of a well-studied problem. They're going to do some kind of a mean variance trade-off. Right? They're going to look at the sources of return that they can get. So suppose those sources of return are, I can earn from staking or I can earn from lending. They're going to compute a mean return for each of those, each of those sources. Of course, this could include other things like derivatives if they're engaging in those. And then they're going to trade off the return against the variance of these assets. And then here, of course, you have a risk parameter that tells you how you want to trade these two off. But the point is that this is an optimization problem that you can solve if you have good estimates of the mean returns and of the variances. Sort of the important thing here is how does this choice of portfolio actually update the returns that you're accruing from staking, lending, MEV, etc. So here's a simple sort of model that's been we've been looking at recently, which is that every validator is going to have some staking yield that's going to come from two sources. So one source is just the natural inflation of the rewards, and another source, which I think is of interest, for this event, is what we're calling sort of this MEV bonus. Right? This is like any additional value that comes from the application layer that is then redistributed back to the validators. And this is going to be redistributed back in sort of a pro rata fashion relative to the portfolios that they're holding. So I look at all of the rewards that come from just from the inflation of the token. I look at all of the MEV that I'm trying to redistribute, and I send it back to the validators proportional to their portfolios. And then you have a analogous sort of lending yield. So you have yield that just comes from your favorite lending protocol, which takes on sort of this form that depends on the utilization. So you look at how much borrow demand there is, and then you scale it up by sort of some risk-free rate, and you update the lending yield at time t sort of accordingly. And so these are some sort of staking lending dynamics that you can try to analyze. Of course, here I'm just modeling sort of the deterministic part of these dynamics. I'm not actually modeling the randomness, but you can sort of add that in. And what we're trying to understand is how do the portfolio decisions of these validators, namely by solving that optimization problem in the last slide, and the fact that you have some control over this parameter, how much MEV you want to redistribute back into the system, how does that affect the incentives here? And in particular, does it help us avoid some bad outcomes that we might otherwise have if we didn't do this, if we didn't redistribute this MEV back? So let me just sort of do the first part, which is it's been known since sort of around 2019 and 2020 that staking, which is this privileged sort of source of return that is securing the chain, is competing with other sources of returns like lending and derivatives. So in particular, this paper in 2019 by Tarun showed that if you want to avoid sort of staking percentages going very low or below some threshold, you really need these inflationary block reward schedules in order to achieve this. If you just have sort of constant block rewards, and certainly if you have deflationary reward schedules, then you're going to end up in situations where all of the validators are roughly moving to lending, and no one's staking, so the security of the network sort of breaks down. And this implies that sort of proof-of-stake protocols need to actually incentivize validators to keep staking and avoid looking for other sources of returns. They might look for them. Of course, they might look for them off chain, but we're not modeling that right now. We're just modeling sort of how much they can get from activities that we can actually monitor. And this is also turns out to be true for staking versus derivatives. So it turns out that there's certain kinds of phase transitions where the validators are the derivatives are in fact parasitic on the proof of stake system. And so this sort of sets the stage for, well, if we want to solve this, of course, one way to solve this is just to inflate the rewards and then just keep validators staking that way. But we have sort of another lever available to us now, which is MEV. And the question is, can this MEV bonus in fact act as a way of bypassing this problem of having inflationary reward schedules or having to inflate your token too much in order to secure the network? And so the question is, how does this, sort of the mathematical question is, how do these dynamics sort of depend on this parameter alpha and on this schedule, on this MEV extraction schedule Q? So one assumption that you can try to make is that this Q, this MEV extraction schedule, is in some sense dependent on the lending, on the yields that you're getting from lending. And what is the reason to believe this might be the case? Well, because lending yields are roughly correlated with the rates at which liquidations are happening. And you might want to say something like MEV in the future is going to be correlated with the number of liquidations that are happening in the past. You can sort of try to put these modeling assumptions. And actually, this did turn out to be the case during, say, the Terra collapse in 2022. But we want to understand how these dynamics behave as a function of this alpha. And one can do sort of similar kinds of experiments and sort of theory. But the upshot here is that you can show that if this alpha is sufficiently large, if you're actually doing this redistribution back to validators, you can avoid having to do this inflationary, sort of highly inflationary reward schedule. And in fact, you can get away with things like constant inflation, and even in some cases, deflationary reward schedules, so something like a Bitcoin reward schedule, which the staking sort of and lending papers of 2019 said would not work. So if basically validators are allowed to be incentivized to stake from sort of this application layer value that's collected by the protocol, then you can sort of massively reduce the requirements for necessary to incentivize validators to stake. And this is sort of very interesting because otherwise you would have to find some way of keeping them keeping them engaged and trying to maintain security. So what I want to say now is that MEV redistribution sort of can act as an incentive mechanism to prevent people from pulling stake away from the network, and in some senses acting as a mechanism more generally to incentivize, can be used as a mechanism to incentivize good behavior in proof of stake protocols. So usually we think of MEV as sort of this parasitic sort of thing, but it has these use cases as trying to incentivize staking, for example. But of course, this is not the end of the story, right? Because all I've said is that if you redistribute this thing back, it might sort of help secure the network. But the way that you do the redistribution and sort of the mechanics of this redistribution actually matter a ton. So it was noted that if you have these validator pools that are doing this smoothing or redistribution, where they're paying out MEV rewards in some proportion to the amount that everyone has staked, this can actually reduce the variance of the returns that validators are collecting. So basically, the smoothing is allowing validators to have some kind of predictable recurring revenues. And this also, because if you recall, sort of the way we'd set up this portfolio optimization problem, they're trading off risk reward. It might sort of have, it might cause validators to have less propensity to shift their portfolio allocations radically, or they might have more stable allocations over time. And this might be desired for various reasons, not including, you don't want them to move around their stake too much. So there's this predictability problem, which is, how do you do redistribution to reduce variance? But I now just at the end just want to end on some future directions that redistribution sort of needs to think about, or redistribution research needs to think about, which is the first one that immediately comes to mind is what are the centralizing tendencies of this redistribution? If I'm taking this revenue that's being collected by the protocol, I'm just passing it back to the validators. Does it set up some kind of bad feedback loops that sort of end up centralizing stake or end up centralizing certain validator pools? And I think this is a very important problem that I think should be studied a lot more. And then the next kind of class of questions that I was thinking about future directions is, how can we use sort of these existing transaction fee mechanisms that are already present in proof-of-stake networks? They can be such that they can be modified to implement redistribution in practice. And why does this matter? Well, if you're doing this redistribution, you need actually some way to ensure things like off-chain agreements are not happening. Off-chain agreements between validators themselves or validators and other parties. And sort of this is roughly the question, which is what is the cooperative game theory of validator pools? Do they have an incentive to actually stay in the pool and collect these rewards, or do they have an incentive to defect and collect rewards in some other way and not do the redistribution? So I think the game theory is sort of the cooperative game theory of these validator pools is sort of relatively understudied. It would be very interesting to see how this redistribution actually affects people's propensity to participate in these pools. And then broadly, can we prove things like sort of the closed loop incentive compatibility of this mechanism, that I'm going to do this redistribution after already collecting MEV revenue from users? What is sort of the closed loop incentive structure of this process? I think that would also be very exciting to study. So roughly what I wanted to end on is MEV redistribution can act as a way of incentivizing good behavior, at least from an economic security perspective, in proof-of-stake protocols, and can sort of allow you to avoid these really bad inflationary sort of exponential inflationary reward schedules and make them sort of better and perhaps even constant or deflationary in certain environments. However, this comes at a potentially comes at a big cost, which is you might end up centralizing the validators, and also there might be other kinds of game theoretic phenomena that are happening, like off-chain agreements between validator pools or between members of a validator pool to defect from the redistribution that they're earning. So with that, I will just end here, and if there's any questions, or if we have time for questions.
Awesome. Thank you so much. We don't have any extra time for questions, so we are going to move on now to our final panel. We've got a stacked panel for the last one. We've got Eric Budish, Tarun, Phil, and the other Michael Jordan, who will be talking about latency for this one. I'll leave it to you guys.
Thanks, John. Hey, everybody. I'm Michael Jordan. No relation to the Berkeley professor, basketball player, or actor. And so my parents just have a sick sense of humor. We're lucky to have three awesome people on this panel today: Tarun, Phil, and Eric Budish. I think Tarun and Phil have spoken today, so you have a context, but I don't know if people know, but Eric is kind of the Michael Jordan of HFT, latency, and market design. He wrote an incredible paper that I highly recommend, and we will crib a lot of this out of. But I wanted to start on this concept of eliminating the latency wars. Eric, I'd love to hear the intuition of how you started thinking about this problem, that the latency wars is not in the execution, it's not in the trade tape, it's actually hidden. And that the first step is to understanding it is seeing it. So I wanted to start there.
Great, and no one's ever called me Michael Jordan of anything before, so I'll take it. I think what got me started on this intellectual journey was almost 15 years ago at this point, but was reading about some of the very early investments in speed technology and fast connections from one geography to another geography, like the Chicago, New York high-speed fiber optic cable that's become kind of famous, and genuinely not understanding how such a small amount of time could be worth so much money. And we're talking fractions of the time it takes to blink your eye. What gave my collaborators and I the idea for the paper you're referencing that used message data, and this is the work with the UK Financial Conduct Authority or with researchers there, was once I figured out in that earlier work how to think about why milliseconds, or really millionths of seconds or finer, are valuable in modern financial markets. You realize a lot of the value is around race-based arbitrage. It's around arbitrages that are sometimes very simple to the naked eye, but the complexity is capturing them quickly. And then realizing that, well, geez, traditional financial market data doesn't actually let you see races. That's part of why it took some theory to uncover this issue, is you can't actually see that Phil Tarun, Eric, and Michael Jordan are all racing for the same arbitrage opportunity within a sub-thousandth of a second of each other. So what we got in that England study, in that UK Financial Conduct Authority study, was the full back and forth message traffic between market participants and the exchange, in this case, the London Stock Exchange. So it's just very cool kind of data that no one had ever studied before, that lets you see in all its glory, just trading races. So you kind of count them up, how frequent are they, how much money is at stake. So it was just a multi-year project, and I was I'm sorry to be a little rambly, but the thing that was most striking to me in that study, I had a prior that a lot of races would be for small amounts of money, and they were actually smaller than I would have guessed. But the volume of races was just astonishing. It was like 20% of all trading volume, and this is in the UK equities market, was trading races. The modal race, the difference in time between Phil and Tarun would be 5 millionths of a second. And in crypto trading, I would get, I don't have the data. I'd love to speculate with this group what kind of data you'd find, but my prior is it could be even higher, just because the shenanigans you can do with reordering time in crypto markets. Phil and I are going to get philosophical about time. That's promised. It's even more stark than in traditional finance. So it's a long-winded answer to a great question. Let me stop there.
Yeah, well, I wanted maybe let Tarun take a stab at translating between the message and execution tape of a market to what we see in crypto. What's lit and what's unlit? Like where are we seeing evidence of the burden that these latency games exist, and where they stress the systems? I think recently we saw this with Arbitrum Sequencer, was a place that I think they had to flag that this was happening, but no one was really aware of it other than people running the infra. So I'd love to hear Tarun take a stab at translating Eric's message analogy into the crypto world.
Yeah, I mean, I think the Solana world probably is where we saw the most latency games. Obviously, they made particular choices in how their protocol works, such that it prioritized, low block times and kind of effectively forcing all the validators to be in Hetzner or some very like high-end data center. I think the on-chain stuff is still less than lit US exchanges or Eurex by like maybe 3 to 4 orders of magnitude in terms of message volume. But I think it definitely can get there. The centralized crypto exchanges are a little bit more interesting because it's, most of them are actually cloud hosted. They're not actually hosted in on-prem, like on the fixed data center. And so you have all these games of people like starting 500 nodes at a particular AWS zone, pinging the matching engine endpoint, seeing which node had the fastest relay time, and then submitting your transaction, which is very similar to what happened in the Arbitrum case. But this type of cloud-based endpoint is actually, ironically, the way the normal market is working. So most exchanges are actually moving away from on-prem hosted data centers, except like CME, because basically futures trading is much more latency sensitive in the US. Equities trading, people already internalize all the order flow, so it's sort of like this like very weird, not as latency sensitive. Like it started very latency sensitive, and then once wholesalers bought all the order flow, it became like way less latency sensitive. So the long story short is, I think on-chain stuff is still a bit far. I mean, you can do a lot more things, but it's less about pure latency games. It's a little more like online ad auctions, where yes, there's like a pretty frequent auction frequency, like tens of milliseconds. But the dimensionality of the objects you're bidding on is very high relative to other games.
Yeah, Phil, I'll let you respond to either anything that Eric or Trent said, but I would like to add a question, which is, you're designing a lot of these systems, and I know a founding tenet of Flashbots is eliminating such that we can understand what's actually happening. And so how do you kind of think about elimination when you're designing some of these ideas? Like the fact that what pieces of data do you need to be able to see, and what piece of data do you not want to be able to see, such that we understand really where these games are being played?
Yeah, no, great question. So maybe I want to riff a few things that have been said, which are just kind of random trolling / high level fuel on the fire here. Agree with a lot of the points that have been made so far. I think the interesting thing to me, one point that hasn't been made, is like latency games can kind of be roughly divided into two categories. One that are kind of winner takes all kind of race style arbitrage games, where you have a market structure that incentivizes along like a certain axis of economic activity, low latency, and then kind of determines outcomes of like kind of rent games based on this axis. So this is kind of the most extreme form of latency game. It's what we see in TradFi, and it's what Eric's paper talks about mostly. There are a lot of other more subtle kind of latency games and interactions, even in kind of the solutions that are proposed to the latency games, like batch auctions. So in Eric's paper, there's kind of like an analysis and a discussion of the latency games that happen at the end of the interval for each batch, which still exist. The argument being that like the economic value of like those latency games at the end of the interval is much less than like this extreme kind of winner takes all form of game. So I think when we're in crypto, it's really important to think about specifically what type of latency game and what type of latency activity are you optimizing for. I think the winner takes all race model is by far the most centralizing, because it means like physical infrastructure participants that have microwave towers like take all the arbs. And we've seen in TradFi, and we know the market dynamics of that market are super centralized. So riffing then onto where this shows up in crypto, I think the case that this shows up the most in crypto is two places today. Number one is if you have a first come, first serve sequencer. So if you have a first come, first serve sequencer, there are kind of two options. Either you have low fees or you have high fees. So if you have super low fees, like it's basically free to make a transaction, then your zero sum arbitrage game moves into spam, basically. At that point, latency is not actually profitable, because if you just spam, you'll always beat someone who sends like an actual latency sensitive transaction, because you've sent like an uninformed packet like a minute ago, and that spam will just be like ahead of them in the queue. So what that does is it pushes more arb logic on chain and pushes the like actual economic auction into like the spam externality bucket. On the other hand, if the fees are high, doing this spam is just unprofitable. So you'll never actually do it. And that's when you see like these latency participants have like the arb edge from like reacting first. And this is what you see in sequencers like Arbitrum, for example, which have like relatively high fees compared to something like Polygon, I believe it was, where we saw more of a spam attack, or Avalanche, which also had very low fees, which saw spam attacks and then raised their fees and saw latency games. So this is like kind of the trade-off landscape: high or low fees, spam or latency. But I do think it's important to also make that zero sum distinction. We don't see it a lot in ETH because of the size of the batch, because ETH has been kind of intentionally designed to allow for this global slow MEV auction underlying its block. That being said, there's still an edge game. So in the relays are a latency game article or whatever, it really like quantifies this edge game, which is, again, important to note, very different from like a winner takes all game that you see in TradFi. So that's my full rant, and that's where we see them. Oh, one more thing. So that's one place, which is FCFS sequencers. The second place is sexes, which has already been mentioned by Tarun. I think there's a fun corollary here, which is in the cross-domain MEV work. And what that work says is basically like the bad drives out the good in these markets. So if you have super latency sensitive systems that are very centralizing, they actually also impose centralizing pressure on decentralized systems because they add latency edges to whatever latency game is there through cross-domain MEV. Fun fact, we already see this with centralized exchanges. So there are certain entities that have very efficient routing between centralized exchanges and already play that latency game. And because of, for example, where our infrastructure is on like a cloud service provider having some overlap there, we're already seeing even in our decentralized systems or permissionless MEV markets like this latency competitive pressure from existing TradFi routes. So it's not like a theoretical issue. It does kind of creep into decentralized systems. How do we think about illuminating it? Do research, do data, have conversations, and keep kind of putting out philosophical pieces. So I have one on geographic decentralization I really want to plug. I think that's like an important piece of the latency discussion, and kind of trying to come up with definitions and data around that as we speak. So sorry, that was a very long ramble, but all the fuel I have to add to that fire.
The funny thing is the common thread of all three rambles was this non-agreement on the nature of time. We have discrete time, continuous time, we have relative time, we have absolute time. And Eric has this incredible point about the challenge of discrete time is that you always have a relative edge. Or continuous time trading. And so I wanted to start there when it comes to time. Eric, I'll let you start on what you observed in traditional markets between continuous and discrete time. And then also feel free to comment on what we see in these systems that are designed without the kind of concept of relative time, which is actually the underlying latency games across different data centers and other things we see.
Yeah, great. Let me answer that question, and also I want to respond to something.
Yeah, please.
Phil said that I think is really terrific that I want to riff on. So in a continuous time market, if there are arbitrage opportunities in a continuous time market, that will very naturally incentivize competition on speeds. That's a very relativistic kind of competition to be faster than the next guy. In this empirical study with the FCA researchers who quantified it on the order of millions of seconds of time difference between winners and losers. Actually, in a chunk of races, about 4% of races, Phil will get a kick out of this, the difference in time between the winner and loser of the race was negative, because it's like you show up at two different chips, and my chip happens to process a little bit faster than yours. So I win the race, even though I kind of got to the finish line after you. So there's a tendency towards relative competition, as relative time rather than absolute time being important. So we're fighting over tinier and tinier and tinier slivers of time. I like Phil's point that can have a tendency towards winner-take-all competition. We do find that in the empirical study, the top 3 firms in our data. I don't know the identities of the firms, to be clear. That's anonymous, but we can link firms over the data, and the top 3 firms win over 50% of races. The top 6 firms win about 85% of races. So you're relatively centralized, to use the terminology here. So the idea of frequent batch auctions that I've advocated for in the context of traditional financial markets, that CowSwap that I advise is working on in DeFi, the idea there is to make time discrete, and then that enables re-engineering the nature of the competition to be competition in a more productive dimension. So competition on, in the case of an auction, competition on price instead of competition on speed. And that you can kind of go through the economic chain of why that leads to a more liquid market with less wasteful rent-seeking activity. The thing I wanted to riff off in Phil's comment that I thought was very interesting was this idea of some kinds of latency games might be winner take all, whereas other kinds of latency games might not be. I mean, different different parties might discover tiny corners, tiny little arbitrage corners. And that, for whatever reason, reminded me of the real estate industry. So the real estate industry is another industry with tons of rent seeking. The fact that it's 5% or 6% of your house value to sell a house from one person to another is a ridiculous rent seeking activity. The way that plays out economically is you have lots of small real estate brokers, each fighting for their little scrap. But there is a centralizing tendency in that market, which is the real estate lobbies. And the real estate lobbies help preserve the kind of flawed economic arrangement of needing a broker on the buyer and the seller side, and all the little subtle stuff that kind of keeps us stuck at 5 or 6% fees. So that was just one that struck me. I was like, yeah, we do see some winner-take-all rent seeking, which naturally creates a concentrated dispersed dynamic in the Mansur-Olson sense. But even in these cases where we see very dispersed rent seeking, like in real estate, sometimes the dispersed rent seekers find a way to band together nonetheless.
Is there, Eric, is there a good place to look at research on the consolidation? It started as a broader, more competitive market, and then once we had discrete changes in the rules, the technology stacks, whatever it meant, that it was return to sophistication, return to capital, different types of forces, of consolidation forces. As Tarun and Phil think about kind of the design space, it's good to understand what type of technical shifts drive consolidation and centralization.
Yeah, the best scholarly work is by Donald Mackenzie, who's a sociologist based in Edinburgh. And he's over decades made a mark studying the sociology of finance. So he did this amazing study on the Chicago Mercantile Exchange, and he put out a book, I think a year or two ago at this point, called Trading at the Speed of Light. So that's the best scholarly work. And the best line is in Flash Boys by Michael Lewis, where he said, I used to worry, about 1,000 guys making $1 million a year, and now I worry about one guy making $1 billion a year. And I can't remember, there was some stereotype baked into that quote that I don't remember and won't try to recall. But that was sort of the best anecdotal nugget on that tendency just described.
And Tarun and Phil, as you've seen the block kind of production supply chain get much more sophisticated, how have you seen the number of actors, whether they've grown or consolidated, and how do you think that's related to whether it's latency or any other type of like technical sophistication edge?
Happy to take a bat on this first. I think, I have this troll theory of markets, which is like any competitive market will land in some degree of oligopoly, and it's about like managing the externalities of this. And this is my troll. I've never seen a counterexample as many times as I've trolled like economists with this. But we do see that to an extent in MEV. I think the dangerous thing, at least the way I reason about it, is like how much consolidation pressure are we talking about, and like how many counter forces are there for actually maintaining like the meta properties that allow this thing to exist. So like geographic diversity, decentralization of capital, whatever, not like a plutocratic staking set, things like that. I don't think we can ever remove these centralization pressures entirely. That being said, I think the MEV market is super interesting. So there are certainly a few large firms and entities that do very well on specific MEV verticals, especially when you look at certain types of DEX designs like AMMs. There's a few kind of centralizing or consolidation pressures we see there. A big one, and I think like the most powerful in today's market, is the ability to take risk. And this kind of looks like traditional market making activities in TradFi, because a lot of it relates to like sex-DEX arbitrage. That's like one of the #1 fire hoses right now. People want to make trades on a DEX, but like the liquidity on DEXs inherently updates slowly. So how do you bridge the gap between this like sex liquidity that's gated by like KYC and regulation and, custom like custody rules that people may not trust, to this interface that people actually want to trade on? That's just where we've seen the most activity and the most maturity, just because of the volumes. It's not inherent to MEV or anything. It's just what people use Ethereum for today. And there you see this like ability to take risk as for sure like a powerful centralizing pressure. Before that, we saw gas golfing as another fun one. So the early generation of the Flashbots auction intentionally kind of gave you a huge boost if you were able to be more gas efficient than other bidders to try to drive down kind of the network externalities of the auction in terms of like how much block space was being used by the auction. And this led to people kind of really looking into super arcane tricks to save a little bit of gas, because the gas game kind of became almost a winner-take-all style. But instead of competing on latency, they were competing on like gas used in the system. So that was another example early on, although I say that one has kind of faded away with maturity of the market. And now we're looking at much more things like ability to warehouse risk. Another category is latency for sure, especially in sex-sex arbitrage, complex sex-sex DEX arbitrage, or arbing against like domains that are latency sensitive like Solana or Arbitrum. We've seen that one less, I would say, just anecdotally, my intuitions in the market so far, just because a lot of the MEV today is on less latency sensitive markets like ETH. But we're starting to see that kind of creep in at the edges and also compound with the risk pressure and like together form a centralizing force. So for us at Flashbots, it's a question of how do we kind of minimize the impact of those on the decentralized system.
Yeah, Phil, you brought up a good point, which is about the adaptive nature of the network. Eric, I looked through some of your prior research and showed in the 90s, a lot of the benefit of tighter spreads and stuff came through just general electronification. And now we're at this like, petabips of war. How have you seen markets evolve where they go from this big step function and then the competition gets very tight because we get smaller and smaller, and that becomes a bit of a centralizing factor?
I think that's an important just fact to understand about the evolution of traditional financial markets. So let me just make sure the fact is clear, and then we can discuss it, which is that there was this transition that played out, and again, I'll point to Donald Mackenzie's work as kind of the scholarly work to look at. There's this transition that played out from the 90s into the early 2000s when a lot of financial markets still had a large role for human participants. So think pit traders in Chicago. This is the 1,000 people making $1 million a year that Michael Lewis was joking about, or specialists on the New York Stock Exchange floor running. So humans facilitating trades, running a market, running a limit order book the same way that a limit order book in a way was run since the 18th century under the buttonwood tree. With aided by computers, but fundamentally a big role for humans. And then there was a transition in the U.S. stock market. It was really facilitated by regulation, national market system, which I can grab a copy of. It's big. I got a copy in my office. But that facilitated the transition to electronic markets in the fully electronic trading in the U.S. stock market. It's pretty clear if you look at the historical data that the transition from human-based trading to electronic trading meaningfully improved liquidity and efficiency. There's a famous study of this by Hendershot, Jones, and Menkfeld that's very widely cited. But my read of the data, and I have a lot of references to this in my work, is that you can see this kind of step change as we went from humans to computers. Computers are a good idea, but then all of this additional relativistic competition on speed has moved the needle precisely zero on the market's cost of liquidity. So if you look over like the last 15, 17 years of financial market data, it's hard to see. There are big gains in the transition from humans to computers, and then it kind of flatlined. What that implies for crypto markets, I honestly don't have a confident view. It's a newer domain, but that's what we saw in traditional finance.
Yeah, Turin, you always talk about how Reg NMS and NBBO really changed equity market structure, and how whether it's order rules, those are regulations, but we have things like regulations, which are, hey, there's a new AMM launches with very specific rules or curves. And we see that those things really change market structure. So I think it'd be interesting to comment on what Eric just said around the actual material performance, layer in this added co-evolving nature of the regulatory landscape and kind of bring it over to crypto, where we went from this very naive, unsophisticated world to things like SEP, Wintermute, much more sophisticated on-chain people, and it's just really changing the market.
Yeah, I mean, I think the weirder part about crypto maybe versus traditional markets is like traditional markets actually had a contraction in number of venues since Reg NMS, because a lot of venues like basically couldn't make the economics work given their volume, like places like Philadelphia Stock Exchange, which you'll still have to connect to, but like basically doesn't do anything. Crypto actually has the exact opposite problem, where there's constantly new venues of different types, and there's new venues because there's new chains, so there's new rollups, so it's creating more cross-domain arbitrage. Centralized exchanges obviously have had huge calamitous changes in the last 6 months, which have created a bunch of arbitrage opportunities. Certain things that were collateral that was not expected to move out of a particular range in terms of its value in numerator terms. You had things happen like that. So there's sort of a very different dynamic in the sense that there's this like kind of proliferation of venues in crypto that were versus the like contraction in venues that you had in the normal world. That does change the dynamics a little bit. And this is one of the reasons I actually I would say like the last year of crypto has basically made me more convinced that this actually is going to end up in a different state than traditional lit exchanges, where you kind of had the like Reg NMS happened, then the financial crisis happened, and so like a lot of algo trading firms did well then, and then you had the kind of like boom up to 2012. Then after 2012, it got extremely competitive, and people realized like buying order flow was better than becoming faster alone. And so then you kind of had this like the number of competitors decrease after that point. I think crypto is actually kind of weird because the number of products is growing really fast. Like the number of different places you can trade the same product. Just think about every new roll up. Think about the Arbitrum launch, right? Like when the coin came out, that just like basically DOSed a bunch of venues. And so there's sort of this interesting thing where this is the reason I make more of a comparison to an ad auction, in that you have, on the x-axis, a number of different assets that are growing. On the y-axis, the number of venues that the assets traded at. And then sort of on the between the two of those are actually like growing, like the density of those is growing at the same time. And it means sort of that the dimensionality of the products is higher. It really does mean that like trading ARB on Arbitrum versus trading ARB on ETH versus trading ARB on OP, they're actually kind of not fungible products, because the amount of leverage you can get on each chain is different. The amount of security you're willing to take when you go across the bridge is different. And the MEV auctions are different in terms of like how much you have to bid, the gas rules. And that sort of high dimensionality for products that are sort of fungible creates a huge sort of arbitrage opportunity, where people hold portfolios of what's supposed to be the same asset, but then they kind of like, they're doing this like weird risk warehousing statistical arbitrage type of stuff. And yeah, that's where I see the crypto markets actually deviating quite a bit from traditional lit markets, and it's going to be kind of interesting to see that evolution.
I think that kind of just
sorry, go ahead.
In response, I think that's fascinating, and it sort of relates to what I was initially so confused about 10, 13 years ago or so at this point, which is you from a distance think of arbitrageurs and quant trading firms as doing something really fancy and sophisticated, because we have as economists or finance researchers think that there shouldn't be technical inefficiencies in financial markets. You've all heard of the efficient market hypothesis. To beat the market, you have to know something the rest of the market doesn't know. Economists are very dismissive of technical trading opportunities. But then you just look at what arbitrageurs are actually doing. A lot of it is like the same shit, trades on lots of different venues, or when the prices get out of whack. And it's actually like grandma could notice the pricing, could notice the pricing discrepancy. All the complexity is just in technologically exploiting the thing. So then if you're right, and there's this just proliferation of venues and very closely related ways of trading the same risk exposure, that's an arbitrageur feast.
Yeah, and it seems to only be growing because like token issuance is like sort of still growing even in the bear market.
I think yes and no. I don't think it's an arbitrageur feast in the same way you think about like HFT sniping or something like that. To me, this looks much more like market making and competition on risk, which is actually what you probably want in like these ARB markets. So it is a very different nature. I think there's two interesting effects here I also want to point out that do kind of add to this and make it very different from TradFi. Number one is like the way you can interact with these venues. So in TradFi, execution relies on trust, and it's kind of like a human-based or a technologization of like a human-based process, right? So like if I want to place an order that's like a combinatorial order of like, I either want like these 3 orders to execute on like the New York Stock Exchange, or like take this other one like to this other venue, or etc. It's kind of very hard to do those orders, where on a blockchain you have like more programmatic ways to express more complex preferences, and like this, something like using 2 different venues at the same time is not mutually exclusive if you can like structure the right aggregation or meta transaction. Cow swap is like in some ways an attempt to do this. So that is I think one difference. And the other difference I think is like the profiles of the people taking the risk. So like assuming this is true, what I said, and we have competition on risk and we want that, I was having an interesting conversation recently about like the stablecoin depegs kind of last week during all the bank failures and things like that. It turns out during these stablecoin depegs, all the sophisticated actors and the active liquidity, even though there was a ton of money to be made and so many ARBs across these combinatorial venues, basically, a lot of them sat a lot of these opportunities out if you look at the chain. And if you look at where the MEV distribution actually went, like passive LPs in these protocols made a lot of money because like the active LPs disappeared, and this was like the backstop, right? And who are these passive LPs? They're like degens who are taking like, they have their own risk profile. It's highly bespoke. It maybe isn't even rational to like a market making participant, which is why those participants did the rational thing and backed off. But it kind of does add this like robust liquidity backstop because you have like a risk segmented rather than a zero-sum game that makes the system more robust in downturns. So anyway, that's my rant about how maybe things are different.
Yeah, Eric, do you have any comments or thoughts on that kind of resiliency and robustness question? I know in the US we've had Volmageddon and some other things where there's different causations, but a lot of what happens is too much of the liquidity has the same kind of profile and same type of structure and strategy. They're running stat arb, mean reversion. When it gets 2 sigma, they just turn off. Whatever the thing is, it can cause market fragility. So any thoughts there?
I think that's a big topic. To some extent, when I see a flash crash, I think prices change. To some extent, I think markets could be more robust. Markets could be more robust if designed differently. So I worry. Let me kind of walk back something I just said, because I think it was a little bit imprecise. The thing I kind of worry about, I use the phrase fast and thin crowding out smart and deep. Or slow and deep is probably a better way of putting it. So I worry that if you have a market that in good times or in relatively stable times it's very profitable if you're technologically sophisticated picking up nickels, and that in a way crowds out deeper liquidity, but that is less technologically sophisticated. So this probably makes the most sense thinking about the treasury market. If you have some firms that are very sophisticated technologically at proprietary trading, and they're faster, and that crowds out some of the some deeper pocketed, slightly less technologically sophisticated investment banks. But if when the shit goes down, pardon, I shouldn't keep cursing, I'm a professor, but when there's
wait, when was the rule professors aren't allowed to curse made? Just checking.
I try to be dignified, right? It's but I worry that it is the deeper but slightly less technologically sophisticated liquidity there in a crisis. So I have made the argument that discrete time, batch auctions, slightly slower market design, level playing field, that those kinds of properties could have a robustness benefit, it's honestly very hard to model in a way that's convincing to skeptical economists. It's a hard nut to crack, and my guess is someone will figure out a way to study it using a diverse set of tools. I think it's a good. I sort of sympathetic to the hypothesis. I haven't figured out how to prove it.
All right, Eric, it seems like you have a good question for Tarun before he has to go. I know Tarun.
I have a question kind of for. So this might be, and Phil prefaces every question with this is a trolley question. So I think this is a trolley one, which is at some level, if you read Nakamoto, the problem it's solving is a time stamping problem. Is how do you compare Nakamoto to Haber-Stornetta in the 90s doing a blockchain-like data structure where they were using hashes to link data over time and ensure that data hasn't been tampered with. Part of what Nakamoto was solving relative to what Haber and Stornetta did is creating in effect a decentralized time stamper. But suppose that you had, I kind of wonder if, well, a lot of MEV manifests in the trading of crypto financial assets. If there was a trusted time stamper, and there was a decentralized exchange that made reference to credible, trusted timestamps, I think that might be that's the trolley premise of the question. Could you solve a lot of MEV problems? Just you can't rearrange transactions because we know what it means to rearrange transactions is to fuck with the timestamps, and you got to process transactions in order. And then you could talk about, do we batch process? Do we make time discrete? Blah, blah, blah. But the fact that you can rearrange the sequence, is what's so appalling to me as a scholar of financial market design.
I mean, I guess I'll give you the sort of economics version of this, which is, the decentralized thing doesn't work because of the errors and possibility theorems of the world, right? I have many validators having to pick an ordering and agree on it. And obviously the only sort of social choice function that works in all cases ends up being dictator. And so these kind of very weird social choice things around if we do really want to be decentralized, then you run into these kind of problems that come from just the nature of the symmetric group. Though those are very, very kind of, you can't get around them. But in the centralized case, of course, it doesn't matter. The errors and possibility theorem says it's a dictator, so all you're doing is picking the dictator in some sense.
So would time stamping alone that would
I don't think it would remove everything for the record, because it's not just time stamping, it's also adding and removing around particular transactions, which is akin to the adding a ton of cancels in front of a big order that's going to run you over. Mm-hmm. So there's still some of the adding and removing part that I think it still probably is an issue, not just the ordering.
And are you assuming that time is a zero bound, that you can't do any speculative transactions? I know in the European markets, there's a thing called speculative triggering, that they actually start firing orders off of messages so fast that they're just starting to see the first bit string. They're sending out messages on the other side before they've even confirmed that this is in strategy, and they start canceling them. Creates this insane amount of load on the centralized server, and they've actually banned the issue of speculative triggering, meaning that they're sending pre-confirmed transactions. It's insane.
Oh man, I have so much trolling to do here. I want to let Tarun hop into his train if he has to, but yeah. I'm gonna line up the baseball bat and let her rip.
All right. Thanks, everyone. See ya.
Amazing. Thank you so much, Tarun. That was super fun.
I'm glad to set you up with you. You look so happy.
I'm so happy. I'm so happy.
The last time we met on a panel, you asked me towards the end if we could get philosophical about times. This is my.
I know we need hours though. We need hours. But anyway, so I will say a few things that are trolley responses to your trolley question. First of all, I think let's assume you had the world's most perfect timestamp system in the universe and it had no problems that I could possibly complain about. There's still the fundamental physical limit of the special theory of relativity. So, you know, in the early 1900s, there was this idea that if two things happen at the same time, the observation of like a third observer of like the order in which these two things happen depends on like the reference frame of the observer, right? So even if we had a perfect timestamp system, the best we can possibly do is approximate FCFS, which, as we've said, either creates like a spam. This is what Michael Jordan was just talking about. These preload transactions is like some form of spam, or a latency race, right? But then who wins this latency race, who wins this winner take all game depends on like the third party observer, which here in theory is like a decentralized protocol that's supposed to be fair and universal, right? So like if these two people legitimately send their transaction, their ARB at the same time, and they're not in the same place in physical space, the network still has to sequence that. And like one of those two people is going to be feeling left unfair, right? Because, oh, we sent it at the same time, and because of the network's reference frame, this person's transaction got in before mine. So that's like, even if you had a perfectly synchronized, like to the absolute physical limit set of clocks, you wouldn't achieve fairness. Like the best you can do is approximate FCFS against some reference frame. You know, for TradFi, this is like, they kind of wave around this by saying, okay, our reference frame is like this address in New Jersey, and like the game is like build a cable there. But you know, that doesn't really work as like a reference frame for like a distributed permissionless network. So one more thing I had to say, this is like a trolley idea that I had many, many years ago when I first started studying MEV that I've talked about to a bunch of people, but I feel like it might be worth mentioning publicly in the context of this. This was one of my first intuitions when I came into MEV, was like, wouldn't clock synchronization just solve this? Okay, how do we build decentralized clock synchronization? Okay, let's assume we have SGX. Let's like give ourselves as much ammo as we can. Can we still build something useful here? So I actually had this idea of a DEX that works based on like this SGX nuclear football. So you can imagine basically a portable, like in a briefcase, SGX machine that has like a long-standing key that can't be rotated. So this machine has to stay up for the exchange to kind of work. Then you travel from place to place around the world to all the participants in your market. Maybe once a month, you synchronize their local SGX with the football, right? So like if you put the football physically right next to their SGX, you can get tighter clock synchronization bounds because the latency between this trusted football clock and your local chip is like super low. Then you're kind of approximating as close as you can within like real physical constraints, this timestamping thing. Still doesn't solve fairness, still doesn't solve MEV. What does it actually give you? It gives you basically a shorter block time, right? It lets you have this uncertainty in the same way that kind of fair ordering protocols do, with a smaller window, which in your batch model is the same as like shortening the batch essentially. So all a trusted timestamp would allow you to do in a decentralized context is shorten the batch. Is shortening the batch desirable? Now it depends on like the meta argument of like the rent extraction against the batch. How meaningful is the end of the batch? How much does latency matter? What's like the actual participant distribution, etc. So TLDR, is it useful? I think it's interesting. Like certainly you can tweak some parameters, and like building this SGX football thing I think is kind of fun. Maybe if I had like infinite time, I wouldn't be against like just YOLO and trying it and seeing what properties we get. At the same time, like solving MEV, to me, like MEV is intentionally unsolvable. So like it's very hard to solve. And maybe I'm wrong about this. This is like an open hypothesis. It's like one of the reasons that I like that other people are studying this, because maybe there is like a best design. But my intuition is this is not a solve, because like someone's still going to be left like feeling the unfairness, and like whether or not that's decentralizing depends on like the power dynamics of your system, basically. So sorry for the long troll, but
can I answer with just an open question, which I think of the solving MEV as something you could try to do at call it the application layer or at the protocol layer. And at the application layer, I think frequent batch auctions properly implemented solve MEV. We can debate that, and let's take that offline. I think the really cool open question is whether you can quote solve MEV at the protocol layer. Is there some tweak to blockchain design that my intuition is it comes from just not being able to rearrange stuff, but then that raises, between the two of you invoked Arrow and Einstein, so I got to think a little bit harder about it. But
My ultimate question is like, who gets the rent? You know, like that's
eliminate the rent. That's why I mentioned the real estate agents. Why who gets the rent? Why not shrink the rent?
No, I think shrinking the rent is great. And I think that is where frequent batch auctions are super useful, but I don't think they eliminate it because there's still kind of how do these batch auctions interface with the rest of the world, which is like, you know, the part that's like really hard to model, especially if there are a lot of like continuous venues. I think this is where like a lot of the crypto research and like the global solve needs to go. Specifically, for example, like I don't think frequent batch auctions solve MEV even for DEXs for one like very simple reason. And I say this as someone who was in 2018, like Uniswap, guys, frequent batch auctions solves MEV for DEXs. Why are you not using this? I think people do actually, some people want things that can only come with reordering. So like many people want the ability to do complex dynamic transactions that depend on like the specific state a transaction is being executed on and are conditioned by this. One example might be like a protocol that wants to like liquidate tokens on Uniswap and then do something else in the same like call frame atomically. And maybe this gives them some security property they otherwise wouldn't have or something like that. So as long as you have these people, they can't use the batch because their like requirements are simply incompatible with like waiting for it. And I think that solving MEV for that class of users looks very different as solving MEV for the people who can wait 2 seconds or something, where I agree like a batch is totally fine and like a great way to reduce. So I think all these like plug away at ways to reduce MEV, but the reason they can't happen at the protocol is because of like wrangling with all these fundamental limits. My last piece of trolling is I think the Flashbotch auction, I remember I said this last time we had a panel and I got so much pushback, but I'm going to say it again because I think it's true, is actually a frequent batch auction solve of you know, MEV at the protocol layer, assuming a lot of timing things about the ETH network. It's at least kind of looks like that if you squint hard enough. So
Phil, is that not an important assumption? The assumption, because you wrote about the importance of geographic diversity. Geographic diversity is antagonistic to fairness because you're just increasing the actual amount of time for the network to coordinate literally. Like if we're all in one box in NY4, then our coordination time is very different than if we're designing a system such that the replication is happening across physically large areas.
Yeah, this is why I hate fairness as a word, because everyone has their own pet fairness definition. Like for some people, I have to wait a second longer because like some guy in Australia wants to trade with me. That's like super unfair. It's like, man, if I just cut that guy out, like I don't care about his economic activity. You know, it would be way better for everyone I care about if like we could just trade instantly and like not care about that guy from Australia. Whereas like if you had that, the guy from Australia would be like, this is super unfair. There's like this cartel that I just can't like access without like submitting myself to like the US government, you know, hegemony or whatever. So yeah, I agree with you that like there is a tension there with fairness, which is why I think geographic diversity is like, I'm not implying it's more or less fair for exactly that reason. Like, I don't know whether people will agree with that. My argument for why that's good is much simpler. It's like, if we don't have that, we will just be like subject to like a very single specific set of regulations. And like, you know, the rent game will look exactly like TradFi. That's my 2 cents. But yeah, no, I agree. Like even parameterizing this time, right? Like, do we do 9 seconds or 10 seconds? Do we do 10 or 15? Like there are fairness arguments there that like various people make because the impact is like on the actual distribution of the rents, which is like where people actually like feel the fairness, right? Like ultimately fairness to me is like, are the rents like sanely distributed? And there's no clear way to define that really.
Eric, did you do any work on conditional orders? There's in HFT, there's a concept called ISO orders, which is you can sweep across multiple venues with one order, and you're able, because you do have to trade within the bid-ask spread legally. If you trade outside of it, you get fined. That actually moves across venues. Now, the venues may all physically be in the same place. In crypto, our venues are just kind of different, a very different concept from what we're describing. But I know your LSE work was done just on the LSE. Have you done any of this kind of cross-venue latency considerations?
It's a great question. The closest I've done is in this work with Robin Lee and John Shim, where we've pulled together a bunch of empirical facts on competition in the U.S. equities market. And the way I think about the use of ISO orders, this intermarket sweep order, is if you're most of the time, if you're trading not in a race in response to some algo signal, but because you happen to yourself just want to trade some stock, but you don't want to leave an algo signal for others to exploit, a way to trade, you want to trade across multiple venues all at once so that responders to your trade after you. And ISOs are one way. So sweeping the market is one way to do that. There's also a Reg NMS compliance issue, which is super in the regulatory weeds, which is a reason why some firms use ISOs. So that's the closest I've gotten. I think the conditionality is very interesting. I kind of take Phil's point that at the application layer, for certain kinds of trading needs, frequent batch auctions eliminates MEV, but there are more conditional trading needs, which intrinsically need to rearrange stuff or condition. I do A only if B and C happen. That strikes me as more of an open question. So let me kind of put two open questions out to the audience, which is, what can you solve at the application layer, and what, if anything, can you solve at the protocol layer?
Go for it.
I think we're also seeing this super interesting effect in this direction, which is a lot of, so there's two theses in crypto. One is like the general, or at least in smart contract chains, and I'm like being very high level here, but like, do you have a general purpose chain which tries to optimize for like anything anyone might ever want to do and like have some reasonable compromise for the consensus across all these use cases? Or do you couple your consensus much more closely with like the actual economic activity that's happening on the chain, and then make more like activist design decisions in like the consensus itself? I think this is kind of a version of that same question. So like in the chain world, you could have like a batch auction chain, which like only purely allowed for batch transactions. And then there would be very clean abstraction boundary to reason about the rest of the world. You'd still have to reason about it. And like, you still, in my opinion, need to do some reasoning to fully solve MEV, because there's still some MEV that's introduced by like arbing you across other venues. But there's like a very clear boundary that the DEX itself can control. Whereas when you look at something like ETH, something like CowSwap, trying to do these DApp kind of interventions on a more general purpose chain, that boundary becomes like the Flashbots auction, basically, which is like trying to stuff everything but the kitchen sink into like the block production. And then it's a question of like, how do you align your thing with this block production algorithm so that you still get the properties you want? I think which approach it makes more sense is like a religious question, as Tarun put it a few months ago, which I really enjoyed. But there's certainly a lot of experimentation to happen on both. And my rough trolling is like, I consider batch auctions in like the general purpose ETH model almost like a cartel. And I say this not in a negative way. To me, cartel is not always negative, but it's like a union. It's like a union of users that are like, we will kind of execute together and like throw our full economic weight behind this system that works a certain way, and define a boundary to like the rest of your auction, so that like the same way we would normally define one against like the rest of the world by having a venue.
It's like a cartel, but with the sign flipped. It's people getting together saying, let's collectively not get screwed.
Collective bargaining. Yeah. The sign is, that's why I'm saying I don't say cartel as like a negative thing. Like my troll pitch for Flashbots for like the first 2 months was like, let's make a cartel of people who work in MEV who like aren't profiteering assholes. So like it doesn't all go to crap. But then I realized maybe I shouldn't pitch like a company I'm making, like using the word cartel, because like certain people have very strong reactions to that. But you know, yeah, a union I think is a better framing for sure.
Speaking of cartels, Phil, how do you think about the fact that the more complex application and kind of protocol logic we want, kind of the more exotic and expensive hardware we might need? And so there's a lot of different things of centralization causes of hardware. And in the HFT world, we have FPGAs that can do sub 50 nanosecond full trigger to target type loops. And that's very expensive and complicated to design. And so if we want to do some of this more rich and interesting state transformations, we might create a cartel that's the hardware developer, and they might be able to create some type of thing. And so how do you think about the hardware layer when you're making these decisions? Either Eric or Phil.
I think this is one of the $1 trillion questions of like the next 10 years of crypto finance. I think it goes very deep. I think you're totally right in that, like, in some ways, just the complexity and the dimensionality that Tarun mentioned is already enough, even without throwing more fuel on the fire, that like this effect exists. Especially if you push the latency, it like makes it way worse, right? Like if you look at Solana, for example, you need to use an FPGA on Solana to extract MEV, which like most people don't even understand, but it's true. And like the strategies you can do are much simpler, and there's a huge hardware edge. If you have like a slightly better FPGA, you can do more complex strategies, include more transactions, and directly kind of winner takes all the MEV game. I think there it's a very complex space, so I won't give any like prescription. I think there's a few things that we need to be mindful of. Number one is like make sure the hardware is doing something that is actually valuable and like indispensable in a way. So like if the FPGA centralization force is just there because like some protocol parameter like kind of induces it, is it really needed? You know, is this hardware edge for these manufacturers really needed to make the system work? Probably not. That being said, for some MEV systems, maybe there's like a fundamental trade-off of like the state space is just really complex. The more decentralized we make it, the more complex it gets. There's a hardware edge here. If that's the case, then like how can we decentralize this? I think that's what we're thinking about with Suave. It's like in some ways a decentralized computation network for MEV, where we're going to try to distribute this like as much geographically as possible. I think this is like an activist thing though, and it's like very much an open question, right? So if you like play out one obvious roadmap of Suave, it could be that like Intel suddenly is the MEV company, and Intel like wakes up and they're like, shit, why are we making processors that are like for general purpose? If we just use all these nice fabs to like make better MEV hardware, we'll be like $1 trillion company rather than like, you know, $100 billion company or whatever. So yeah, that's a risk. And I think the crypto community needs to be really careful and probably like actively invest in like distributing hardware, supporting alternatives, making protocol choices that make sure like one hardware mafia isn't principled over or privileged over like another. I don't think there's like an easy fix there other than be super mindful, make sure the hardware is doing something actually useful, and then try to actually decentralize that if it does need to be there and there's no other way. But yeah, it is risky. And I have this troll, this super troll, which is that MEV turns any proof of stake system into proof of work, which is very depressing. But, you know, noodle on that for a second, which is kind of a corollary to your question. Proof of work was the most extreme version of this, where like
I'm not fast enough to figure out that fortune cookie, but I did want to.
Yeah, well, it's because you need to optimize this combinatorial problem in real time. It's very computationally complex, and if users want to push the latency bounds like lower, it gives edges to people who have hardware that like optimizes this better, and they need to be doing like a lot of also. Not useless, it's less useless. I think it's like more proof of useful work because it's actually doing something useful, but it's still like a grind. You still need to grind all these like uncertain orderings and like run these like combinatorial algos and shit. So, you know, and there's hardware externalities there. And when we saw this in proof of work, the ASIC manufacturers were such a political force. They basically dominated the politics. So there is a risk in the future that like MEV ASICs exist, and like MEV ASIC companies are like a super politically important force in MEV. I think we can mitigate a lot of that with like sane parameterization, but yeah, the fundamental force is there, and there's no clear answer to say like that won't matter or that's not going to happen right now.
I wanted to just echo your point about useful versus non-useful competition. I think profits incentivize all kinds of innovative behavior. I always have emphasized and deeply believe that we should try to align private profit incentives with what's socially useful for markets, for society. So that my criticism of latency arbitrage is it's kind of socially wasteful or neutral to negative. And then there's a lot of private incentive to capture it. But hardware innovation isn't per se positive or negative. It's in service of what? So if it's in service of rent seeking or socially negative activity, that's one thing. If it's in service of curing diseases or making the world a better place, you know, that's quite a different thing. So I like to focus on what is the source of the innovative incentive, and making sure that that's a positive, not zero to negative force. So the alignment of private and social is kind of an economist riff.
I think we can also achieve that with MEV. So like the ideal system in my mind under this model is like you know, living in fantasy world, it's like one where you get paid to deploy hardware into places that like aren't already hardware rich, and that deployment directly benefits the user, like commensurate with the amount of money you're spending. So it's not like an adversarial situation where you're like spending it and they're getting like exponentially screwed the more you spend. It's more like spending it and you're relatively aligned with their outcomes, and maybe you make more rent from the protocol because like you're optimizing user outcomes better. There's a fee for you that's sane, and like this is all aligned with like the actual social welfare function we're trying to optimize. How do we get there? I actually think batch auctions are a fun key to this. So if you take the framing of like unions that we had earlier, like I do think we need to build protocols that support the ability of like various geographies to like unionize. And the protocol still works and is in fact more effective when this happens rather than less effective. This is like my geographic decentralization trolling and push. Because the worst case is we centralize to like the US or Europe or something like that. You know, but like the best case is like there actually should be computation in New Zealand, right? Like if there are users making transactions there and the system doesn't predatorily advantage those transactions being optimized in New York, then why not do the computation where the transaction is actually happening? So I think this is where the care has to be taken. Make sure the system doesn't push those unions to like the central place and instead allows them to like exist in like their natural local geographies. Yeah.
Eric, I think it'd be interesting to use that as a comment on what happened with fiber. I think a lot of people became aware of HFT's investment when they started to see physical places coming between Chicago and Secaucus or wherever the amount of fiber that was laid. And then we went to the more advanced stuff that even I know that bird droppings had issues. In the McKenzie book, he comments that, but the world does need fiber. So it'd be interesting to hear what your thoughts on how was that useful at all? Was the fiber laid for this, or was it literally just for latency edge?
I mean, I'm open-minded that there can be unanticipated benefits that the innovation incentivized by high-frequency trading activities might have some spillover benefit, but I haven't seen any specific reason to see. I have this time-lapse data that I had some very dedicated research assistants build, where you could see, I called it the latency arbitrage triangles. You could see using federal, I think FCC, Federal Communication Commission applications for microwave licenses. You could see the line from Chicago to the New Jersey equity markets, and also from both of those locations to Washington, D.C., get straighter and straighter and straighter. So DC, because I see your eyes raised, like it's government data that moves financial markets gets released in a data center on K Street. I mean, where all the lobbyists are, just by coincidence. So there's this latency arbitrage triangle that you can see in the microwave applications data, and straightening the thing by a few extra feet. I mean, it doesn't cost that much money, so like I don't want to get up in arms about it. But also to find social value in that, I think is nuts. The fiber, I mean, transatlantic fiber or transoceanic fiber, that seems useful. I don't know what the delta is if there weren't an incentive from latency arbitrage. It
does come maybe to this idea of the social welfare function being a reflective of the fact that speed in this world was so relative. If Phil has a 4-second connection and Eric has a 3-second connection, you'll pay infinite dollars for that 1 second edge. And so there is no like socialization of the welfare function. It goes all to that one spurt.
Yeah, very relative. And then so the social value is probably based on the absolute, getting from 5 microseconds to 4 microseconds it's hard to see a ton of social value in that. But again, it's not like I have a proof. It's just a strong economic intuition.
I feel the same way. I would like gut check it at like 5% benefit versus like 95% burned for zero sum. And like my guess is like, had you emulated the latency game in like a simulation universe where they could all like invest this money and like get the same edge, like there would be little difference actually. And again, this is just like a gut feeling. I do think there's some utility to speed. I think the tricky thing is like the types of links they're incentivized to build like don't have high throughput and they're not like usable by the public. So, you know, that's like where the winner takes all thing comes from. So yeah, I see a little bit of social utility, and certainly there's externalities of like, if you get a better routing technique, maybe that propagates to like other switches in like Google's data centers or something. So, you know, very hard to like throw the full baby out with the bathwater when you have like thousands of engineers working on any pursuit. That being said, like, I don't know if it's like super aligned with like the actual outcome of efficient markets, which is like, that's, I think, where the zero sum thing really like takes it from being much more aligned to like much less aligned. If there was a way for us all to like improve the latency of markets together and like, you know, we actually each were able to express our individual welfare on that in like a mechanism that then optimized the social welfare, I think you'd get to like a better social welfare with less investment. So like I see it as like a coordination failure, basically, that like a lot of that money was burned. But that's just my own political opinion. And again, this gets highly controversial with HFT people. I've certainly had, you know, face turning blue in conversations about this before. So you kind of have to make your own judgment there. I think the relevance to crypto to me is just like not even asking the value question. It's just like, do we want a global system or not? And like, how do we want the rents to be distributed in this system? Let's just like come up with something that we don't put value judgments on, is like a much easier place to go than like, oh, this thing is bad, so like therefore let's like moralize it. I think we also see a lot of that in MEV, and like the truth is usually a little more subtle. There are trade-offs. Like we should actually engage with like the subtlety of like how much money is going where and why. Like that to me is like the question that a lot of these things sweep under the rug by like popping to these different layers of abstraction, where you lose like the core thing of like, where's the money actually going?
Follow the money is a good just general purpose instinct. So where's the MEV money going? That's what I want to.
I mean, we have data on this. The MEV money is going largely to validators right now. Certainly, there's some going back to users in the form of like transactions being mined because of MEV that otherwise wouldn't have been. I would expect that to increase as users get more sophisticated and kind of leave less on the table in the transactions they're making to be extracted by the searchers and the validators. We're seeing trends in like all sorts of DEX designs for that. Some of it is going to the searchers, but on net, I would guess the searchers, and this is not data, so this is just my gut feeling, it may even be a negative sum game where like most searchers are losing money, and like the new entrants are like subsidizing like the profits of like the few that are making some edge, which is not great. But you know, it's not like the searchers are like raking home bags full of cash, unless they have like a substantial edge on sexes, in which case they'd probably be raking the same bags of cash regardless. So that's kind of where the MEV money is going today. A lot to validators, some to searchers, some to users. The middlemen like Flashbots, some of them take some rents today, we don't. So it's a pretty race to the bottom-y market, and I don't think anyone's really making a killing there or like extracting huge rent or anything.
Eric, that's a great thing to end it on. Follow the money. I think that if we had to say something about today's incredible summit, follow the money. I know that the Ethereum rig group is focused on some of this stuff, and I think that's going to be some really cool stuff to come out of that. So hopefully next time we talk, we can do that. This is the last talk of the day, everybody. Eric, thank you so much. Really appreciate it. That was awesome. Phil, good to see you. Everybody, these are going to be recorded, chopped up, and put on the internet, and we'll see you soon.
Can't wait to collaborate more on this stuff. See you all soon.